Yep, there we go. All right, welcome to day 2 of CPP. It's my pleasure to kick things off by introducing Jennifer Paikin as our second keynote speaker. Jennifer received her PhD from the University of Pennsylvania in 2018, and she's worked on a number of topics from domain-specific languages to linear types, and is perhaps best known for her work on quantum programming and logics for reasoning about quantum programs. She's worked both in industry and in academia. She worked at Galois and then at Intel, and is now an assistant professor at the University of Vermont. And I'm delighted to have her here today. Welcome.
Thank you so much. Thank you so much. Thank you for the introduction. Thank you to all the organizers for inviting me. Really happy to be here and tell you all a little bit about verification of quantum programs. Is the volume in this okay? Okay. Good. So I wanted to start off with a little bit of a workflow. If pretending for a minute that you are a quantum engineer implementing and running an algorithm on a quantum computer, what does that sort of thing look like? So first of all, you are not writing your algorithm in an ordinary classical, what we call classical programming language, since your quantum algorithm uses quantum-specific operations and abstractions. So we're going to use some kind of quantum domain-specific language. So here, which you should not be able to, don't worry about reading, but like here I've written something in Qiskit, which is a quantum computing library embedded in Python. But there's lots of other quantum programming languages that exist and support slightly higher level or slightly lower level features. We had a whole workshop about it yesterday, blank. But I will say that almost all of these quote unquote higher level quantum programming languages are going to be compiled to some kind of intermediate representation, which we typically think of as quantum circuits or something in the quantum gate model. So these circuits are not circuits in the hardware sense, but they're basically just sequences of primitive operations applied to qubits, the quantum bits. So the idea is that these gates correspond to primitives supported by real quantum computers, which do in fact exist. Sometimes we have to clarify. They're not quite useful for real-world applications quite yet, but there's been a lot of really exciting progress in terms of building these machines that we've seen just in the last few years. But our quantum computers of today not only are small, so they're on the order of like anywhere between 10 to a few thousand qubits. They're also extremely noisy, so they introduce a lot of errors. They only support like short-lived execution times, coherence times, and they have other constraints depending on the underlying technologies. So in order to actually run our quantum circuits on these devices, not only do we compile them to circuits, but we also need to apply optimizations, make the circuits as small as possible, but also obey the constraints of a particular quantum device, such as layout, placement, things like that. And another example of a type of transformation pass is something like an error correction pass, which enables us to adds layers of detecting and correcting errors that are introduced by these devices. So alternatively, if the circuit is small enough, then you can simulate it on a classical, in a classical program, a classical simulator. But by definition, general purpose simulators like that scale exponentially with the number of qubits. So this can only be done in small cases. And so for example, the best simulators right now might support 30 to, at the maximum, I think like 60 qubits. And that's all that they can simulate. Okay. I want to note also that executing a circuit on a quantum device is not like a one and done deal, because quantum programs are inherently probabilistic, not to mention all the noise introduced by the devices. You are going to need to execute your circuit run a bunch of shots. So it's like hundreds to up to like millions of shots per run. And then the output of this is a probability distribution of measurement results. Okay. And of course, that's for like a single instance of running your algorithm. And plus, I will point out that the quantum computers of today are expensive to use. A lot of them are available via the cloud, which is great. I think the public cost of cloud time on like one of the IBM devices is somewhere between $50 to $100 a minute based on the plan. Right. So the question that I have for you is the typical motivation of formal verification of software systems. How do you know that your quantum program is doing what you think it should be doing, right? I'm sorry to report that the state of the art in industry is manual analysis, pretty much. You as a user are going to compare these probabilistic results against what you expect them to be. Maybe you have, a specific probability distribution that you are expecting, and you're going to analyze whether what you got out from the device is like close enough to what you were expecting. And so if they match, then great. And if not, then there's very little to tell you where the problem came from. Like the problem could be in your implementation itself, of course, or it could just be a problem with your expectations. So maybe you're not correctly accounting for the error models of the device that you ran this on. Perhaps there's a bug in one of the optimizations that you ran, or maybe the optimizations are just inefficient, and then they compound like the approximations that are introduced by some of these optimizations in a way that skews the measurement results. So I'm showing you this workflow, like not to criticize, but just to give a glimpse into the value of formalization and verification in these quantum systems. So my goal for this talk is to reflect on some of these circumstances and point out some of the open questions that exist in the quantum formal verification space. I'm not going to do a totally comprehensive survey of the literature, but I will point out especially some of the projects that are being or have been presented this week, because I think that's a nice tie-in. So with that, for the rest of the talk, we're going to follow the following outline. We're going to start with a basic overview of some of the math of quantum circuits, just to sort of get a foundation on that. And then we'll go a little bit deeper into a few different verification techniques, and sort of highlighting some of the pros and cons of different approaches, and then we'll wrap up. So that's like high-level overview. Before we start, though, I actually want to start with step 0, which is a little bit of a vocabulary lesson. So when I say formal verification, and probably when a lot of you say formal verification, I'm thinking about something like machine-aided mathematical and logical methods that I'm using to prove that some program matches its specification, or maybe in the case of like hardware formal verification, to prove that a system matches a formal specification, right? But if you go and talk to a physicist and you talk about verification, there might be a mismatch, because they might be thinking about quantum verification. I'm not 100% positive on where the boundaries between all these phrases lie, but generally, quantum verification will refer to the idea that a quantum experiment or a system or like computer actually demonstrates quantum behavior that can't be achieved in a classical way. So this is a really interesting like theoretical question of, is this thing quantum? And then of course in the quantum space, we're also talking to a lot of engineers who are maybe building quantum computers. And so then there's like also a mismatch between formal verification, as I'm thinking about it, and maybe a broader perspective on verification, and like in terms of like verification and validation, where verification can refer to formal verification, but it can also refer to just like other methods for asserting that some system matches a specification. So simulation, testing, things like that. So it's when working in these interdisciplinary fields, as I'm sure a lot of you know, it is really important to like get on the same page, and that can even start with language. Okay, so let's talk a little bit about quantum circuits. So here I have the picture of a quantum circuit that we saw before, and it's made up of, as I said, qubits, which are represented by these wires, the horizontal lines, and then gates, which are like primitive things that a quantum computer can do. So let's start with qubits. Mathematically, a qubit can be represented, the state of a qubit can be represented as a superposition of bits. So a single qubit is a superposition of the 0 bit and the 1 bit. And this syntax here, if you haven't seen it before, this like half bracket around the 0 and a half bracket around the 1 is pronounced ket. It's like the right-hand side of a bracket. And that's just referring to like the classical basis state corresponding to 0, classical basis state corresponding to 1. When I say superposition, I mean that this is a complex linear combination of the 0 and 1. So alpha and beta here are complex coefficients, and they satisfy this property that if you take the norm of alpha and square it and add the norm of beta squared, you get 1. And like, I think this is, you can kind of think about this constraint very, very roughly as this is almost like a probability distribution. And in fact, when you take a qubit and you measure it, what you're doing is effectively sampling from that probability distribution. So if you have a qubit in this superposition and you measure it, you're going to get out the bit 0 with probability norm of alpha squared, the bit 1 with probability norm of beta squared. So where the power of quantum systems, a lot of it comes from, is when you have not just a single qubit, which is a superposition of 0 and 1, but multiple qubits, where if you have n qubits, your quantum state is a superposition of all 2 to the n bit vectors of length n, right? So in the 2-qubit case, that's a superposition of 0, 0, 0, 1, 1, 0, 1, 1. Right, so this like 4-qubit system here is always going to be represented by 2 to the 4 sized vector of complex numbers. Okay. So we talked a little bit about qubits, we talked about measurement. Let's talk about these other operations, these what I'm calling unitary gates. And the semantics of these unitary gates is a complex matrix, so its action is going to act on these state vectors. And the condition of being unitary says that it has an inverse, and its inverse is its own conjugate transpose. So it's like easy to compute the inverse from the matrix representation. Okay. So this is sort of a very like first day semantics of quantum programs. Okay. And you know, there's this is kind of leading us to the first like open problem that I want to point out, which is like, how do we represent this semantics in a way that is scalable, sort of, and suitable for verification enough? So like the first option is vectors and matrices. This is very commonly used. And because we can, take advantage of existing structures for reasoning about linear algebra, things like high-performance computing, computational linear algebra. One downside is that these are, complex vectors, and so, I can tell you from experience that floating point numbers are not precise enough to capture the semantics of non-trivial algorithms. And of course, also, this is definitionally not scalable. So a state of n qubits requires a vector of size 2 to the n. So are there any other options? Well, of course there are. Oh, what happened there? So I'm going to just highlight a few creative representations. So one is the quantum decision diagram, which represents a linear algebraic structure like vectors and matrices as a graph, and that allows us to repeat subterms and shared nodes. And so in the worst case, the complexity of a quantum decision diagram I don't think is any better than the corresponding matrix, but in practical cases, it can be quite a bit better. Here's another example, which is the phase polynomial representation, which encodes operators like Cliffords and measurement as maps from the basis state, like x, so this is on the right here, to an algebraic formal sum of other basis elements, that's a sum over y, with some coefficients. And so the phase polynomial representation, one, looks like a math equation, which is really nice for working with mathematicians, but it's secretly a formal structure that can be simplified and transformed according to some well-defined rules. And furthermore, because these symbolic variables, and in fact all the components in the underlying formal structure are just bits, it's actually really well suited for automatic equivalence checking with S&T solvers. So really, this good choice, phase polynomials. Here's one more representation I'd like to mention, which is the ZX calculus, or the ZX calculus, which is a categorical formulation of quantum states and operators. So this is a diagrammatic representation, which means that states and operators are represented as diagrams, which correspond to very, very closely to morphisms in an underlying category. And equivalences in the calculus are represented really nicely in pictures. So it can be nice to work with on paper. So equivalence in the ZX calculus is not tractable in the general case, again, but a lot of work explores how to build tractable subsets of rewrite rules and heuristics for diagrams of particular shapes. Okay, so with that, I want to go a little bit. Let's start talking about verification. Right, we talked about representations, we talked about semantics. Let's talk about verification. And to sort of introduce this idea, I want to use a particular line of work, which I'll refer to as Inquire, because that's the name of the GitHub repository. So this is work that I was involved in early on, but since then has taken off under the direction of Robert Rand and a whole bunch of other collaborators. So Inquire and its first iteration, which was Quire, is a system for formally verifying quantum programs in Rock. So let's start off with a simple example. So here we have a simple quantum circuit defined in Quire with the sort of diagrammatic circuit on the right-hand side. And this is a very simple operation which prepares a qubit in the 0 state, and then it applies the Hadamard gate, which sort of puts it into superposition, and then applies a measurement. And so the result of running this circuit should be 0 with probability 1/2 and 1 with probability 1/2. So the question is, well, how do we specify and verify that this is the behavior of the coin flip circuit? Okay. Well, I'm sorry to say that the simple semantics that I showed you like 2 slides ago is not the semantics that we're using in this situation. And the reason is because that requires probabilistic steps. Certainly, we all have lots of techniques for reasoning about probabilistic systems. But one technique in the quantum space is actually sort of a nice way of moving around this. And so not only is this nice, but it's also the way that physicists and mathematicians think about quantum computing in generality in many cases. So rather than qubits being represented by vectors and operators like unitaries being represented by matrices, qubits are now going to be represented by a matrix itself, which is called a mixed state. And what a mixed state is essentially is a probability distribution over the pure states, so over these kets. So this is just like the usual trick of changing a probabilistic step relation into a relation, a deterministic step relation over probability distributions, but done in a way that can sort of like combine all of the probability distributions into one matrix. So rather than matrices as sort of the semantics of unitaries and measurement are these specific kinds of maps on these mixed states, which are also called density matrices. And we can have a deterministic step relation rather than a probabilistic one. So if we look at this specification of the probability distributions of this coin flip circuit, as a mixed state, we can represent it as this following matrix. It's a probability distribution, 1/2 being in the state 0, in the pure state 0, 1/2 being in the pure state 1. And so this is the representation that we use like directly in Rock, using nice notation tricks. We sort of say that the semantics of the coin flip circuit produces this particular mixed state as the output. And the proof, while written shortly right here, does applies a bunch of custom tactics that do matrix manipulation in Rock, which, as you might imagine, takes a little bit of finessing. But the tactics, Robert has built up a very nice library that can do quite a lot. Okay. So this approach of reasoning sort of directly about the semantics of quantum circuits can get you pretty far. So another use of this sort of approach is Vox, which is a verified optimizer for quantum circuits. This is a paper from 2021 by Kesha Halada and Robert Rand, and some others at UMD. And so this is in this workflow, this is a very optimizer, right? So it's able to take equivalences of circuits, verify their correctness using this semantics, and it also has verified like other kinds of optimization passes, like hardware-aware passes for circuit mapping, layout, routing. So fully optimized verifying compiler. Fully verified optimizing compiler, that's what I should say. Okay. So with that said, we're skirting a little bit. I'd like to bring up this open problem number 2. So far, I've talked about quantum circuits, but at the very beginning, when I was talking about this workflow, we had a difference between quantum programs written in some domain-specific language and the quantum circuits they compile to. So in addition to the quantum gates, these quantum programs have a bunch of things, like they might have interleaved classical and quantum computation. They might have classical control flow, like loops, certainly higher level quantum abstractions, and even things like parameterized circuits in terms of, or parameterized programs in terms of like the number of qubits that are the input, or some rotation angles, things like that. Perhaps surprisingly, expressing the semantics of these quantum programs compared to quantum circuits can be quite challenging, because of the mathematical foundations of the quantum circuits don't, by themselves inherit the structure of the classical computations. So one evidence of this is a great line of work on the protoQuipper family by Neil Ross and Peter Selinger, among lots and lots of others. But I'm pointing this out because in terms of formal verification, this is really important. We don't just want to verify a quantum circuit on its own. We want to know what the overall algorithm is doing that might call out to these quantum circuits or interact with them in non-trivial ways. So additional evidence that this is an important problem is all of these papers and talks that we've had this week focusing on verification of programs rather than just circuits. So here's an example that touches on just a little bit of this problem. So here we have a circuit. This is an example in Squire, which is one of the follow-on languages following Quire, a simple quantum IR. So here we have a description of a parameterized circuit. So this is the quantum Fourier transform, which is defined on any number of wires, so any number of qubits. And so because we're working in rock, we can simply define this as a function from natural numbers to circuits. So this is kind of like a cheat code for integrating classical parameters with quantum circuits. And so the result that we could get out is a lemma that says, okay, for any number of qubits, right, if you interpret this circuit as a unitary and you apply it to an arbitrary basis state, x, what you get out is the following pure state, which is the usual presentation for the specification of the quantum Fourier transform. Okay. So the specification is pretty readable. And why I call out this example is the part that's probably not interesting to most of you, which is that this property holds for any number of qubits at any basis state, right? Because that's the way that we prove things in interactive theorem provers like rock. But this is the part that consistently impresses physicists and engineers with whom I share this idea. The fact that formal verification is not limited by the scalability of the number of qubits in the generic case is consistently mind-blowing. So I just like to throw that out there. So this is a concrete value to quantum computing developers. So of course, there are a lot of trade-offs to doing formal verification using rock or other interactive manual theorem proving tools. So trade-off number one is the trade-off between the powerful reasoning techniques that you get with the fact that requires a lot of expert knowledge, proof developers, and relatively limited automation. So this is, as always, a very important discussion, and there's lots of work, pushing for more automation. There's work that's pushing for being able to capture these more powerful reasoning techniques with more automated interactions. So a lot of really interesting work going on there. Another trade-off, is about the way that we express specifications. So if you're thinking about proving that two circuits are equivalent, that's a specification that's very easy to understand. That's easy to show somebody and say, this is what this specification means. If you're looking at a specification that says this circuit transforms this density matrix into this other density matrix, that can be harder to interpret. So I think the open problem number 4 is, how do we actually express specifications in a way that is formal, readable, intuitive, and well suited for formal verification? This is also a problem that a lot of people are actively working on. It's really interesting ideas. I'm just going to point out yesterday the keynote at Planck by Christoph Charton was about this very problem using path sums, using the path sum representation. So one more trade-off that I want to point out. There's, of course, lots of really interesting, it's important to capture not just functional specification of these quantum programs, but other kinds of properties. So one example is after you've gotten to a certain point of the program, are these two qubits entangled or are they disentangled? Is this qubit restored back to the 0 state, which is something that you need in order to use ancilla properly, and so on. So this is a point in favor of having really powerful expressive reasoning principles, such as in ROC. But there's still a lot of kinds of properties that require more work and effort. So things about probabilistic algorithms, when we talk about the interaction of classical and quantum data, we sort of have to go beyond the mixed state formalism that I described before. And so the best way to do that's definitely an open question. And also when we want to reason about errors, such as the errors introduced by quantum devices. This is a really important point of discussion. So there's been a lot of discussion about that this week as well. And that question about errors is what I'm going to focus on in this next little case study. Specifically, I'm going to talk about a paper that I contributed to, but was definitely not the primary contributors. Specifically, the primary authors, Qin Chen, Yuhao Liu, and Guxu Li at University of Pennsylvania. So the goal here was to verify error correction, but more specifically fault tolerance. So let's give a little bit of a scope to this problem. So as a reminder, error correction can be thought of as this circuit transformation to protect us from errors that occur on the quantum devices. And this is really important right now, specifically because just in the last few years, we've seen the first demonstrations of successful error correction on real devices. So we're getting to a point where these quantum computers can actually handle doing some error correction, which is a really important step. So here's a very, very high-level overview of quantum error correcting codes, QECC. So similar to classical error correcting codes, we're going to be embedding a logical qubit, so that's this like input on the left here, into a larger code space. So there's some sense in which we're like duplicating information to distribute the information of the logical qubit among the larger code space. I won't get into the mathematics of how that works exactly. But the idea is that once you're in this code space, once you're in this larger space, if an error occurs, there is a procedure to do some kinds of observations and computations on the state space that doesn't change the state, but does output some classical bits, which is called a syndrome, that tells you if an error has occurred, and depending on the code, what error it was and how to correct it. Okay, so once you have that sort of syndrome information, you can potentially apply an error correction, which reverses that error that occurred and brings you back to the state that you were in before and brings you back into the code space. So we also want to be able to do operations on this code space, which act as though we had done them on the logical qubit from the beginning. But we want to do those operations on the encoded space so that at the end, we end up in another state in the code space. So in the last few years, we've seen some really interesting efforts towards verifying quantum error correction codes using automated techniques like SMT solvers and symbolic execution. And this has been quite successful, I think, in large part because many quantum error correction codes are built out of a well-behaved subset of quantum operations called the stabilizer formalism. So if we look back at our different possibilities for semantics of the language, we saw pure states and mixed states. The stabilizer formalism is an alternative, which only applies to certain kinds of operations in the quantum space. But rather than vectors of exponential size or matrices of exponential size, states are now represented by a set of Pauli operators that stabilize the state. Okay, so what's going on here? So a state is characterized by the set of some operators S, such that when you apply that operator to your state, it doesn't do anything. It stabilizes that state. And these operators are drawn from this Pauli group, which is a very well-behaved subset of unitaries, which I don't have the definitions on the screen, but one thing to note is that the Paulis can all be represented by bit vectors themselves. Okay. So each Pauli operation can be represented by a bit vector. And this stabilizer set is actually always going to be a group, so you only have to record the generators of that group rather than the entire thing. And the operators that act on these stabilizer states can be described in terms of what's called a tableau that basically describe how you transform the generators of that Pauli group into other Paulis. So like you're basically mapping this function over your set of generators. So because this tableau is just talking about sets of Paulis, that can in and of itself be represented as a bit vector representation. So ultimately the story is that all of these things, the stabilizer formalisms can all be reduced to bits. And furthermore, not that many bits, because instead of having exponentially many complex numbers, we only have something on the order of n squared bits in this representation. So the stabilizer formalism is actually efficiently simulatable on the classical computer, which contributes to the fact that we are able to analyze it using classical analyses in a pretty efficient way. So that's error correction. Certainly, verification of error correcting codes is not a solved problem, but in this paper that I was referencing, we want to go beyond error correction and talk about fault tolerance. So while these error correcting codes tell you how to correct errors that occur sort of in between these blocks, in practice, what happens if an error occurs sometime within one of these blocks? So within syndrome computation, within the error correction itself, or within a logical operator. So the solution, using a lot of good math, which I will not get into, is that we implement each of these sort of blocks as some fault-tolerant gadgets, which are sort of, enforce the property that we're able to still detect and correct those errors sort of after the execution of the gadget. So for the purposes of verification, though, this presents a problem or a challenge, because now these fault-tolerant gadgets themselves don't fit directly into the stabilizer framework. So they will include things like potentially unbounded loops, like repeat until success loops, and classically controlled variables. So verifying the fault tolerance of gadgets takes some additional steps. So first task, formalize actually what fault tolerance means in a way that is suitable to checking, so formally enough to sort of express that property. Now, you could try to verify those properties, like manually in Rock, so it's sort of in the style of Squire. But in this work, we aim to reuse as much of like the automated advantages obtained by the stabilizer formalism verification as we could. So our approach was to use symbolic execution of circuits with added symbolic quantum faults. So anywhere that a quantum fault could occur, anywhere that an error could occur, we add like a symbolic error, and then you add a bound that says the total error in the circuit is going to be limited by some bound. The paper has special cases for symbolic execution rules for repeat until success. So you can't just unroll this loop, of course, indefinitely. So you need to have some kind of structure, some kind of guidance into what it means to symbolically execute a repeat until success loop. And as an additional case study in this paper, we talk about magic state distillation, which is a protocol that builds upon fault-tolerant primitives in order to produce certain states in a fault-tolerant way. Okay, so I'm gonna start wrapping up. I want to summarize some of the open problems that we've talked about in this talk. So open problem number 1, we talked about the structures. How do we efficiently represent quantum semantics in a way that's sort of well suited to formal verification? Open problem number 2, we talked about how do we actually verify more than just circuits, but verify quantum programs that have all of the useful programming features that we can dream up. Problem number 3 is sort of the trade-off, the usual story of the trade-off between more automation versus more control over the things that we're verifying. 4, how do we actually express quantum specifications? I didn't get into this question as much, but it's a really, really interesting question. And then 5, verification in the presence of errors. I'm going to bring up one more open problem, which is how do we encourage adoption? This is, always a challenge, especially for domain-specific verification problems. What I've seen from the quantum computing space is that successful verification projects, successful programming language projects as well, can never come just from the classical verification world. They always have to build up from the mathematical foundations of quantum computing to like really make the biggest impact. And so, the best way of doing that is to build collaborations, to build really deep collaborations between formalization experts and domain experts. And that's not easy, right? There's like real differences in motivation, what people care about. There's these language barriers, right? That really do show up when having conversations across domain boundaries. But bridging that gap is extremely rewarding, and I definitely encourage people to try it. So I'm, I think, a little bit early on time, but that's all I have. So I'm happy to take some questions.
We have time for questions.
Thank you for the talk. In your list of open questions, most of them you could replace quantum by classical and it would still make sense. But there is one that I don't see in this list. It's the issue of scaling. Is it because you don't care about scaling to larger circuits or things like that? Or is it not yet relevant? Or?
No, it's definitely relevant. Yeah. No, absolutely relevant. I mean, I was a little bit thinking of that in terms of the problem number one, but of course it's a different problem. We especially care about scaling in quantum computing because we cannot simulate. You can't run classical tests on large quantum circuits, and so whether that's doing the verification on concrete large circuits in some scalable way, or whether that's like reasoning symbolically, like in the example in Rock that I showed, it's extremely important to keep that in mind. Yeah, thank you.
I actually had a clarification question, possibly naive. At some point, I thought you said that when you use these poly tableaus and stabilizers, that you could simulate with just a quadratic number of bits. Is that for a certain class of quantum programs? Or?
Yes. Yes.
And which class is that?
Stabilizer programs. So in the purely unitary fragment, that's Clifford's. But you can also add measurement, and you're still able to classically simulate it.
And so what kinds of programs would fall outside this class? So the Clifford class makes up like a very large percentage of basically every quantum algorithm, but most of the sort of introductory algorithms will have other things as well. So like a universal quantum gate set, one common universal quantum gate set is like Clifford plus the T gate. So T is a gate that is not Clifford, and just by adding that one gate, you can sort of expand the Clifford set into all to a universal quantum set, so any possible unitary. That's also true of like, instead of the T gate, an arbitrary rotation around the around any particular axis, like a Z rotation. There's definitely a lot, yeah. Right, thank you.
A lot more other people could say.
So you described the possibility to scale reasoning because of having parameters as we are used to see in classical verification. And you also said that simulation, especially with the first representation, was not practical because even the floating point numbers are not big enough to get the precision you need. But you might still consider having simulations for the small examples and then scaling up using the induction capabilities. Is this something that is this a line of research that is really active right now in the domain?
Yeah, absolutely. I think that the line of research in rock, sort of following this Quire-Squire type of work, that's generally the approach. Is you're reasoning by induction, and the base case is you'll sort of use tactics that will
You can use
do the
brute force
simulation.
for the base cases?
Yeah.
And
Well, because in rock you can reason about, you can use actual complex numbers rather than approximate, right? And then induction to get sort of all of the cases. So that's definitely a popular technique.
but you can also even use floating point expansions and things like that to increase your precision if need be.
Yeah. And people do simulations using floating point numbers. That's absolutely absolutely what people do in practice. Yeah.
Thank you for the very nice talk. The slide of yours here lists some open problems at an abstract level. Is it possible to give an example of a program that you would consider out of reach with respect to this current state-of-the-art of verification techniques in terms of, I don't know, features or size or whatever?
Yeah, that's a great question. I believe that I don't necessarily think that there's any algorithms that are like conceptually out of reach. If we're doing like in terms of functional correctness, I mean, in terms of if you're using an automated technique, then certainly some approaches will work, up to a certain size, and then will time out. If you spend a long time doing like formal verification in rock, I think you can definitely push it, as far as you want, given given how much time you want to spend on it. I think that especially when you're I don't really know the current state of the art, especially when we're talking about like some of the more probabilistic or approximate algorithms. That might be something that is not fully explored yet, but yeah.
We still have time for another question. If not, let's thank Jennifer.
Thank you.
A business meeting now, perhaps after a short break, maybe around 5 minutes.
Just about some figures of the conference and discussing about the future of CPP. So the PC chairs, as you may know, were Nick and me this year, and Catherine will maybe arrived or will be there today, and Yannick, maybe Yannick is in another here. Okay, and Yannick will have been the conference chair, so trying to find sponsors and make things work with the ACM. So this year we had 178 registrations, which, as you can see on the graph, is the most popular CPP session ever. So it's good, it's great. Maybe because of being in France or in Rennes, or maybe because of something else, I don't know. But that's a good thing. In terms of submission, it has also been slightly higher than the previous best conference, which was chaired by Catherine, was there, yeah, in 2020. So as you can see, after during the lockdown and everything, there have been a slightly decreased number of submissions, but this year we had a high number, and we managed to keep the quite well-balanced number of accepted papers. So we had 75 submissions with a light double-blind reviewing. So compared to the 51 submissions we had last year at POPL Denver. And we accepted, so we decided to accept 27 papers, which make the program quite dense. So that's why, for example, the business meeting is in the middle of the conference, which is pretty unusual, but it was hard to fit the program with 27 papers in 2 days and 2 invited talks, but we managed to keep something quite balanced, I hope. And so we had 2 months for reviewing and discussing the paper, and before that 7 days for bidding. So I hope it has not been too high workload for the PC members. And because we had more submission than expected, we also allowed more external reviewing to help PC members to get nice expertise on all papers. Oops, what happened? Yeah. So regarding the kind of proof assistant, so we usually do kind of analysis of which proof assistant are used in each paper and the kind of balance between accepted and rejected paper, just to give an idea, even if it's not considered at all when we accept or not paper. And so as you can see, it's almost well balanced. So for some reason this year we had maybe a bit less. The acceptance rate for lean paper is a bit lower than for rocks paper. So this is maybe something we can try to analyze and to improve. So maybe people from the rock community are more aware of the expectation of the way we write papers for CPP or something. So this is, I'm just kind of raising some ideas, and the idea is to discuss during the breaks and during the rest of the conference, because the business meeting is before the end of the conference. We can use the breaks later to maybe try to improve, and maybe you can have suggestions for the next PC chairs to kind of modify a bit the call for paper. We tried already to improve the call for paper 2 years ago with so Brigitte and Sandrine tried to improve it, and we did another round with Sandrine last year and with Nick again this year, but maybe there are still improvements to make really clear the expectation of the conference with respect to the way we write paper. And there's not that, I mean, you could have expected maybe more lean submission than in previous years, but in the end, we have almost exactly the same number of lean submission than the last CPP session. And regarding the amount of math formalization submission, so it's one third of the submission, and the acceptance rate is exactly the same acceptance rate as the global acceptance rate of the conference. So even if we didn't kind of enforce this by just letting things go, it went quite well balanced. And very few ACDA submissions this year, yeah. So, as it is common now, we have 3 distinguished papers for the conference. So the first one was the talk of Sébastien yesterday. So he's not here today, I think, because he couldn't manage to stay. But let's... So I don't know if someone will be able to give him the kind of sheet of paper. Where's it?
We'll email it.
But he's from Rennes, so maybe if I leave it here, I can take it back in some days. Yeah, so the average, so we are allowed to give like accepted papers for 10% of the conference. And so we have two other papers. So the other one was presented yesterday by Jean-Christophe. So yeah, Jean-Christophe is here. And if I understand correctly, it was quite an ancient work, like 5 years ago. So it's great to have a distinguished paper after 5 years of hard work. And the last one will be presented later today. And yeah, so it's a paper by Yann and Clément. We have only one printing, but if you need another one. Thank you. And I don't know where your talk is scheduled. When is it scheduled? This afternoon. So please come this afternoon to see the nice talk. I also want to thank all the PC members for the hard work. So 2 months is quite short. And everybody tried to do its best to make it work. And we had also this year a lot of external reviewers, and they also make it possible to get quite nice expertise on the paper. So let's thank the external reviewers as well. So we had so many that it didn't even fit on one page, so sorry to make it that fast. But that's also something we may discuss, whether we want to kind of change a bit the way we deal with external reviewers. Do we have an explicit pool of external reviewers as it's done in some conferences up front, or do we kind of select it after the fact? I don't know, maybe something to discuss for the future, because I really do think that it makes sense to also make use of the expertise of the whole community, but it's also in a double-blind process, maybe a bit of a tricky thing to do in less than 2 months. So maybe having an official pool of external reviewers up front is also a way to manage conflict a bit in a nicer way. I don't know. And also thank you for Sandrine and all people organizing this year program. And also thanks for the steering committee and Kathleen really managing this with a lot of energy. Thank you, Kathleen, for making this. So as you have noticed, we have now 2 PC chairs and 2 confirmed chairs. And I think that's my next. Sorry, no, that's not my next. This has been set up by Kathleen in 2020. So I was the PC chair last year with Sandrine. This year I'm doing it with Nick, and Nick will do it next year with someone else. I will tell you in a few minutes. So it's very nice, because then it's really lower. I think Nick can confirm that it's not as hard when you start from scratch. You learn everything, and at the end of the year you kind of lose everything because you start from scratch again. Now this rolling stuff is really nice. And thanks for the AV team that managed to make it work even in a rush this morning for Jennifer's talk. But yeah, hopefully they're here, otherwise we'll have been a bit stuck. And a big thanks to all of you. We want to thank JetBrains. It's our only remaining sponsor, so thank you, JetBrains. We still have one. I hope the next conference chair will be able to find others, but we'll see. If you have idea of possible sponsoring, please tell us. And so next year CPP will be co-chaired by Nick and Cyril, right here. And in the same way, so Yannick is staying, and now Sophie will be. I don't know if Sophie is. Yeah, Sophie will be sharing with Yannick. So please find new sponsors. And maybe now it's time. So there will be also a business meeting for POPL on Thursday. If you think about stuff later, you can send, of course, an email to Nick and me. But maybe, what time is it? 10:15. 10:15. So maybe we can try to take few minutes to try to exchange about the reviewing process, about the fact that maybe the area has changed a bit in terms of submission. So do we handle it in some other ways? There are some proposals also to maybe do some collaboration with journal on formalization. Do we do it in the POPL PLDI way, having journal first submission? Do we try to set up other kind of collaboration with journals? It's quite open, but I think we could find better way. And also, do we need to improve or change stuff in the call for paper? Did you find anything to? I mean, we can collaboratively improve this the way we kind of crystallize the expectation of the conference. So even if it's hard to provide expectations, whether it's program verification, math formalization, and so on, having a common guideline is very helpful in reviewing and in writing papers as well. Because sometimes people are submitting papers that are already outside the community and they don't really know the habits of the community. So please, if you have any, yeah, that's mics from the back.
Thank you. So I would like to comment on an item that you've put on your previous slide about the importance taken by formalization related to math, where I guess math is taken in a rather broad sense. And
math was just the tags put by authors on their paper.
Yeah, sometimes it's a bit hard, of course, to distinguish between math formalization and program verification, for instance. But let's take it a bit informally. I think this is great, of course, but I think also maybe it raises some issues about what we expect from a paper which is talking about math formalization in a conference like CPP. And also maybe there's a dual question, which is what authors expect from a paper being published in such a venue on their records, because for young researchers in particular, of course, this is going to be kind of an item that they can provide in their applications and so on, so as to explain that they have some visibility in this community. And if we're talking math formalization, then we're talking about welcoming a new community of researchers and scientists and so on. And in math, there's nothing like conferences with proceedings in such a way we have them this week. So we have to be a bit careful about how this publication will be recognized and understood by peers in the communities. And it's great that people working in math formalization are working in math departments and also in CS departments, but unfortunately these two places don't value the same kind of publication. So this might in part explain why there are some discrepancies between what is expected by PC members and sometimes the way people write their papers. But I think you highlighted the importance of having a common guidelines. I'm not sure this is possible as of today. Maybe it will become possible later, but for now, I think there's a difference between math papers and computer science papers. That's life. And so maybe we could have a way to welcome the two styles. So you've mentioned this possibility of having a partnership with journals. That could be a way, because the standard for publishing math papers is rather in journals than in conferences. So I think that's something which we should discuss further. But I also think that if possible, we should think about a way to have a stamp which is recognized by both communities. So not only journal papers for math, or not only conference papers for math. I don't know. I just want to comment on this because I've been aware of some unfortunate or not well understood decisions that were taken sometimes with CPP pieces for some formalization. And I'm not discussing if they were right or wrong or whatever. It's just that there is some glitches here that I think we should work on.
Yeah, thank you.
I mean, just to build on what Asia is saying a bit, there's a thread going on the CPP steering committee speaking about these issues, and maybe also elaborating on what Nicola was saying a little bit. One of the themes there is there's a new journal, Annals of Formalized Mathematics, and is there some way in which a paper published at CPP on math could also be published in Annals of Formalized Mathematics, or maybe, and there's some questions there about whether it should be only published in the Annals of Formalized Mathematics or published both here and there, and maybe from what you're saying, some way of having it being presented here as well as appearing in a journal might address some of your concerns.
The editorial board said journal has discussed that.
Right, I see.
Certainly open to the proposal.
Is that you?
I'm part of it, so is Asia for that matter. So
I see.
she's
And we have one of the editors.
Hi, so yes, I'm one of the two editors-in-chief of the Annals of Formalized Mathematics, and as Georges and Asia said, we have been discussing the opportunity of trying to set up collaboration with CPP during our last editorial meeting. So I think that what came up is that, as Asia said, the communities are somewhat different. So we would be so the journal first model is probably what would look like the most efficient for people publishing in the Annals of Formalized Mathematics. So if CPP agrees, the idea would be that papers that had been already been accepted in the Annals of Formalized Mathematics at a certain date, like for instance the submission date or whatever, they can be accepted as CPP papers. And then if so, they can receive a stamp as being, well, they had already been published in the AFM, and also be awarded like recognition from the CPP community, so that people a little bit in the border of the T communities, they can get recognition both from the mathematical and from the CS communities.
Yves?
I've seen many people.
Okay,
Yeah.
I don't think it works because accepting papers in a journal has its own numbers, and accepting papers in a conference has a problem of you have a limited number of slots for the conference. It's not the same model. But that was not the point I wanted to discuss. There's another thing you have to prepare for, is the advent of using artificial intelligence in combination with formal verification to produce mathematical results. And this will provoke, may provoke a sharp increase in submission of poor quality papers that are made by people who just think that running the computer is doing their job. And so maybe you will have something to prepare for there, and there are incentives. So there are incentives to make large libraries like MathLib to be developed, because that's going to serve as input to the AI movement. So there are incentives for that. These people who are doing this job need recognition. So we have a lot of pressure for a lot more publications, and maybe CPP is not going to be up to the, will just be crushed by the number of submissions it will appear. So maybe you will have to think about it. I don't have a solution, but I just wanted to.
But that's why the call for paper was also a way to make it clear and to avoid this kind of submission easily, because they don't just.
I didn't look at the call for paper. If I can go. Yeah, so maybe I should clarify a few things. The first is that the call for paper already includes some text explaining what the the standards we apply for formalization papers in general, but also for formalization of mathematics. And it's about, well, not explaining just the mathematics, but also why the formalization is interesting. So this should already, and this was what was done by Brigitte and previous chairs. Because not every formalized mathematics paper is necessarily an interesting CPP paper. Also, we want to have talks that are interesting, so I don't think we can open the floodgates to any formalized mathematics paper. I guess what might make sense, if we want to have this journal first, to offer this journal first option for formalized mathematics, is indeed to have some cutoff date when people are made aware of this option of presenting at CPP, not publishing at CPP, but presenting at CPP. For that they would have to apply with an extended abstract in addition to their paper that pretty much should explain what the talk would be like. And then based on that, the CPP program committee would decide whether that's an interesting talk for CPP or maybe not. Maybe that's really just mathematics, and it's fine if it just gets published in the journal. So this is the current working proposal we have at the steering committee level and the ongoing discussions, but of course we're welcome to more feedback.
I was wondering if you were thinking about doing different categories, as it was done in many conferences, to have pearls, which are system descriptions, which have a less stringent constraints on the number of pages, or a different set of rules for writing formalized math papers. Or would that satisfy both communities, actually?
Yeah, maybe just a brief response to that. I mean, the current call for papers, it has some phrasing that says if you have a formalized mathematics paper, or any paper for that matter, you need to demonstrate in your paper some, have some insights about how the proof assistant helped or hindered you, or some innovation that you had to make in the formalization style. And so this I think is where, I mean, if it was a paper that just was, I formalized theorem X into Y and that was it, this is usually not enough for acceptance. So that's the main guideline we offer now. Maybe
Sebastian's presentation and paper was very insightful in the way we kind of perceive this kind of math formalization paper. It was really about, not about I developed something for MATLib and that's it, but really about an insight on a specific point.
Yeah, but if there are other guidelines that we could use to, enrich this sort of prompt to an author and to the reviewers, that would be nice.
One word of clarification. First of all, this so what Mathieu raised is certainly something we also consider at the annals of formalized mathematics. So for papers to be accepted in our journal, the whole point is that mathematics must be interesting and the formalization must be interesting. So it's a journal of formalized mathematics. But just to clarify, we were not proposing anything automatic. Not that if a paper has appeared in the mathematics, then it should automatically be accepted as CPP. Nothing of the like. The only point was that we observed a certain discrepancy between ways papers are written for mathematicians and ways papers are written for NCS conferences. So the problem is that often colleagues have the conundrum of either publishing a paper in a math journal or trying to publish this in a CS style. And the idea is that if the content is interesting, even if it rather weighs the mathematical style, it might be a good fit for CPP. So this is provided, of course, the PC members considered it interesting and relevant for the conference and so on. It's more a matter of the style rather than the content. The content must be accepted by the board, of course. I mean, the CPP, it would not be a matter of discussing this.
Clément? Yeah.
So I wanted to ask how we feel about tool papers, because one thing that is happening this year is that CAV has changed the way they do tool papers pretty radically, from novel tools presented to the community to retrospectives on already popular tools. And I wonder whether we should make any changes in reaction to that.
Yeah, this sounds like it would be a good thing to have at CPP too. And I think my impression is that the current call for papers would not discourage you from submitting such a paper to CPP.
Yeah, I think there's explicitly a mention of tools as one of the categories,
right?
But it's as a full paper, and other conferences have like short papers for tool papers.
Mm. Yeah, in terms of categories, I mean, we also accepted this year a paper that whose title says Proof Pearl, although we don't have an explicit category for a Proof Pearl. So we judged this paper, the explicit instruction to the reviewers was disregard the fact that this is in the title and just evaluate it as a regular paper.
Guillaume, yeah?
Yeah, something I would like to suggest to consider too for the steering committee. There are several other conferences that are using a two-round process during the year, and one advantage of the system is that it allows for a reviewing process that is closer to journals, that is that it allows for major revision for papers that were submitted during the first round. In this case, the program committee can consider that the paper may be worth publishing, but is definitely not in a sufficiently good, and authors are encouraged to resubmit during the second round as a major revision. So that's something that may be considered.
Yeah, I mean, one challenge there is that we have a pretty tight timeline, especially to fit with co-location with POPL'. So having a second round there would, I mean, maybe we'd have to revise the timeline substantially to have an earlier submission in the spring or something.
Yeah, it will be ready 6 months before.
Yeah. 6 months before.
Sure.
Wait.
Maybe I can answer to this. I mean, it's not a crazy idea, but we should also consider that there is also ITP, and there is a chance that we would directly clash with ITP, and I don't think this is necessarily helpful for the community.
I will follow up on Kathleen. For ITP, the fact that there is ITP and CPP was already a choice to have 2 opportunities per year on similar topics. But what Guillaume is describing is a different need that is not catered neither by ITP nor by CPP. So maybe the 2 conferences could discuss about this possibility and have both have this approach, but it's also a change in the social fabric of the conference, because you ask people a different kind of work in the PC. So
Actually, I'm curious if ITP is also having a similar discussion with the Annals of Formalized Mathematics. No?
Not to my knowledge. I'm in the steering committee. I've not seen that.
Would it make sense?
I think so.
And do you think we should kind of try to co-discuss with ITP to?
It's difficult.
But I think anyway, it's. Thank you for the nice discussion. It's already 10:30ish, so that's time for the break. Go see Cyril. He will be the session chair of next session to try to set up your computer and everything during the break. And we'll see each other at 11.
Do you know where it will be next year?
Next
Okay. So welcome to the second session of this morning. And it's my pleasure to introduce the talk, Can we formalize type theory intrinsically without any compromise? A case study in cubical Agda by Frédéric.
Right, thank you. Just waiting for the slides to magically appear. There we go. Right, thank you for coming. So this is joint work with Liangting Chen and Jean Tsai from Academia Sinica. And we just learned in the business meeting that this is one of the very few Agda talks at CPP. But I hope there's not going to be too many Agda details, so that is understandable anyway. So what's the motivation? Well, if you want to do formalized meta theory or you want to do formalized meta programming in general, then you need to have some kind of internal representation of the syntax you're manipulating or proving things about, right? So we are trying to get a nice economic way to get this internal representation of the syntax of type theory. And besides, if you really think that type theory is an adequate foundation of mathematics, then it certainly should be the case that type theory should be able to reason about the syntax of type theory, because that's also part of mathematics, right? So concretely what we want is we want to have a type whose elements are terms which are well-typed in a certain context gamma of a certain type A. And it should only contain these well-typed terms rather than just having some extra junk that you don't want to reason about because it doesn't really make sense, right? So why is this hard? Well, if you just do this for simple types, then it's not. But if you do it for dependent types, then there are many complications. So for example, if you have dependent types, then they only really make sense in a context, right? So the type n of a finite type with n elements only really makes sense if you know that n is a natural number. If n is a Boolean, this makes no sense. And of course, terms depend on types. But if you have dependent types, then types also depends on terms. So you have this circular dependency between all the different sorts, where we have types depending on terms, depending on types, depending on substitutions, and all these kind of things. So you have to do everything at once. You can't stratify it in a nice way. And you also need to worry about definitional equality between types, because if you have a type such as fin1 plus 1, then you only really know what the terms of this are after you've computed what that 1 plus 1 is 2. So you know that you're talking about two-element types, right? So this also needs to be part of your syntax somehow. And similarly, if you have something like a substitution, an application, a dependent function applied to an argument, then you're going to end up with a substitution in your type of that thing. So you also need to have substitutions in your syntax. And this then leads to a non-trivial equational theory of these things, because you would expect that if you substitute by the identity substitution, that should really do nothing, right? So all of this needs to be part of the problems. So how have people done this before? Well, this is quite the selective history, I guess, but if you go back to last century, then there was an early formalization by James McKenna and Randy Pollack, where they represented pure type systems in an old system called Lego. And what they did was they basically took all the untyped terms, and then they had a predicate that said, these are the good ones, these are the well-typed ones, and you just form a sigma type to keep these. And then you have to prove a lot of lemmas where you say that, well, actually this case can never happen because it's well-typed by this separate thing, right? But it's also what they did in the SynFlean project that we heard about yesterday. And I think that that's probably a good way to do it in Lean. But if you're doing it in Agda where you have nice inductive families, then you can hope to do better, right? Nisse Danielsson did something like this in a precursor to Agda called Agda Lite, where it had an explicit equality relation, and then he proved that all of constructions you do actually respects this equality relation. So this is a classic instance of setoid hell, right? Where you have a setoid of terms, and then you explicitly have to prove that whatever you do actually respects this. And Chapman did basically the same thing, but he managed to simplify it a little bit and only use inductive definitions rather than inductive recursive, stuff like this. But he still had to do this manual proof effort, where he had to prove that everything he did actually respected the equalities, right? So I would say that the breakthrough happened in 2016 when Thorsten Altenkirch and Ambrish Kaposi realized that you can use quotient inductive types from Honda type theory to do a lot of these things for you instead, right? So the idea is that use the quotient feature of homotopy type theory to make the definitional equality of the object theory really be the real equality of the meta theory, right? Which then means that all constructions automatically respect this equality. And you don't have to prove separately that whatever you do respects it. Just because it's equality, everything respects equality, right? It also means that you can't do things differently for things that should be equal, which I would argue is a feature. If you're actually printing terms, you might not agree with me, but if you do meta theory of things, then I think it's definitely a feature, right? So how can we understand this? So it's a big definition, and one way to understand it is that you can make sense of it as saying that, well, what they did was they took the initial category with families, which is a certain model of type theory, and they encoded it as a quotient inductive type, right? Which gives some kind of guarantee that this is a sensible thing to do. And in particular, we know that categories with families, these kind of models, they are an instance of a generalized algebraic theory, and we know that every generalized algebraic theory has an initial model. So it makes sense that you could do something like this. And what they did this before cubic lambda was a thing, so they did it in kind of standard AGDA with postulates, where you very carefully postulate the equalities you want for your quotient constructors, and then you define an eliminator, and you hide this behind some abstract thing, and you promise to never look at the explicit representation. And this worked very well, but now we have cubic lambda, we have support for quotient inductive types, so we could hope that we could just do it without any tricks. So that's what we set out to do. But if you do this, you realize that in practice, this is not as straightforward as you might think, right? So here's just one example of what you have to worry about. So if you look at the equations for a category with families, then it's a category with families, and then you have an action of substitutions on your, so the category represents the substitutions, and then you have a family of types and terms. And you have equations like this, which says that, well, if you have a type A and you act on it with the identity substitution, then you should just get A back, right? And similarly, if you have a term T and you act on that with the identity substitution, then you should just get the same T back. But if you think about this equation here, then you realize that the left-hand side actually has this type. So it's a term in context gamma of type A where you act on it with the identity substitution. And the right-hand side has type just, it's a term of type in context gamma of type A. So they don't have the same type unless you apply this, you use this equality to make sure that they have the same type, right? Which is fine in extensional type theory, say, but if you just want to do this in cubic lambda, for example, then you need to have an explicit transport here where you use this equality proof to make sure that things line up and you're in the same type, right? But unfortunately, if you do this in cubic lambda, then cubic lambda will, for some reason, say that this is not a strictly positive definition, which of course is nonsense, because there's nothing non-strictly positive about this. But I mean, you can vent and scream at your screen, but in the end, you want it to work, so we need to do something about this, right? So in this particular case, we could use cubic lambda's built-in notion of a dependent path instead. But I think that then we're starting to stray from this idea of using the categories with families formulation, because that's a cubic lambda specific thing, right? So it would be nice if we could do this in a more principled way. Okay, so why do we need this transport? Well, it's because we're trying to be really precise about the types of our, the things we are manipulating. So for example, if we look at the constructor for taking a substitution from gamma to delta and extending it with one term to substitute for the top variable in order to get a substitution into an extended context, then we insist that this term we have here really is of a specific type, right? We're only happy to substitute from gamma to this extended context if we have a term which fits with this type that we are extending the context with, right? So that's where our problem's coming from, that we are really trying to be precise about these things. But of course, we could equivalently, we could say, well, you can give me any term you want, as long as you also give me a proof that it has the right type, right? So this is the Henry Ford principle. You can have any car you want as long as it's black, right? But the point is that if you do this, then we used to have a transport here. But if you do this, now we have this explicit equality proof, then the transport disappears, and we're just carrying around this equality proof instead, right? Which makes cubic lambda happen because there's nothing There's nothing weird going on anymore with a function in the middle of our definition, right? But if we now do this and everywhere, then really we don't need to keep this equality here around locally. We can just drop all of these things, which removes the problems, but then we reintroduce them by having a function type of, which says for every term what its type is, right? And then here we would change this to a constraint saying that, well, the type of t better be this thing, right? So this is what you end up with if you do this. So we have this simultaneous definition of context, substitutions, types, and terms. And compared to the previous definition, we are dropping the indexing of the terms of the types, but we're reintroducing it with this function here, right? And I've written set to mean set in the sense of homotopy type theory. So it doesn't have any higher above constructors, but the context can be any type. And if you do this, then you realize that you end up with something that looks quite a lot like another equivalent notion of a model of type theory, which is the so-called natural model, which we also briefly saw yesterday in the talk about Symfleen, right? Where we have a pre-sheaf, two pre-sheaves, and a natural transformation between them. So it's nice that this still has some kind of foundational grounding in the models. So this is what you end up with, and it's of course too much to take in at once. So I've highlighted the differences compared to the previous definition. There's not that many of them. Let me talk through them. So the first one is that we have this type constraint in our extension. We notice that there are no transports appearing anywhere on this screen, which is nice. And we also had to introduce some seemingly extra equations here in some of the constructors that are derivable from other equations, but if we put this derivation in, then we still get this strictly positivity error because we don't have a function in the middle of our definition. So we say, okay, give me any proof of this you want. And because we have explicitly asked for everything to be a set, there's at most one proof of any equation anyways. We know that it's equal to the canonical one, right? And we also had to interleave the definition of this tie-off function so that this definitional equality here is available when we define this eta law, for example, right? So we can write REFL here. Okay, so that's just for the basic type theory, just substitution calculus, more or less. But in the same way we can do it, we can add pi types, we can add inductive types as the Booleans, we can add a universe, and it all works quite well, right? One small thing that you have to do as well is that we found it useful to add in other kind of tie-off proofs that they should be derivable, but you can construct them from other pieces, like I said. So for example, if you have a context which has a Boolean as the top variable, and you ask for its type, then that should be the Booleans where you can put in any substitution you want, because you know that substituting the Booleans by anything is just going to be the Booleans, right? But sometimes you want it to be something that's not quite the Booleans, which you could fix up, but if you just put it in like this, then we know that it's going to be equal to the canonical proof for this fact anyway. So again, it's just about keeping the strict positivity checker happy, right? Okay, so we have a data type, but anyone can write a data type. So in order to see that this is the right data type, you would expect to at least be able to show that you have an initiality property, that you have some kind of morphism of models from this data type to any other model, right? And you can use the pattern matching or cubic lambda to define these things. So you get recursion principles, you get induction principles with witnesses that this is the initial model, right? Annoyingly, this is the one thing I'm not so happy about with this, is that we still have to mark these recursion principles as terminating when we did this, even though they are kind of obviously terminating. Because all the recursive calls are on smaller things, but I think the problem is that we also had to prove this kind of naturality property at the same time. It's just that it doesn't matter if you first translate the term and then you use the tie-off of the model, or if you first use the tie-off of the syntax and then translate the type, right? That should be the same thing, and you can prove this. But then here you have a rect tie of B, where B is something completely irrelevant to the thing you're currently using. So I think that's why it's not cubical lambda doesn't see this as obviously structurally smaller, annoyingly. But we mark it as terminating, and then we use this. And and it does terminate in practice. And we also thought that, okay, so we have these kind of hacks along the way, but when we present it as a recursion principle to the user, we can just define away these hacks, and it will be a nice interface. But actually, it turns out that it's not a good idea to do this. It's better to let the user also do their own hacks if they want, because sometimes you can then give a more direct definition that doesn't use this constructed proof if your situation is easier, which makes some other constructions easier. Right. So what can you do with this? So here's one example. You can construct the standard model where you interpret context as types and types in context gamma as functions from gamma into type and substitutions as functions. And then for terms, you can switch to the fibered perspective again. We say that, well, a term in context gamma, well, that's going to be an interpretation of a type. And then for every element in your context, you have to give an element of that type, right? And then the tire function is just the first projection that picks this out again. But we have to do this, we have to assume uniqueness of identity proofs, because otherwise we're not allowed to go into this non-set, right, from a set. Similarly, you can define the term model if you want, where just everything is interpreted as itself. Works quite well. Other things we tried was to actually do normalization by evaluation for this syntax, just for the substitution calculus, and that worked very well. Maybe in part because Gene did it. I don't know where he is. So it worked very well because there are no transports anywhere in these terms. So everything just computes. So transports are they're bad in many ways, but in particular they stop some computation in cubic lambda. But because we get rid of all the transports, this just computes. That's very nice. We also tried to do the logical predicates model, where the idea is that you start with a model, and you want another model which is displayed over this one, which means that for every element of the first model, you give an element of your new model. And then if you look in the literature, you see that, well, a logical predicate model, if you want the types over a type A from your original model, well, they should be types in an extended context where you now have access to a variable of this type as well, right? So this is like a predicate over A in the sense that it's a type with a free variable with an element from A, right? So you can try to define this. I've simplified it a little bit because you need to cryptify it to deal with the context. But the problem now is that we now have types, the type A appearing in our definition of the terms again, right? And now we have the transports coming back into our terms, and then we're back to basically the same kind of equations we had before. So this trick we used to get rid of the transport does not help for constructing this particular model construction, unfortunately. And you could try to use strictification to get rid of this. And all of the strictification machinery that Ambrus Capose and Pia developed, it's a very nice paper. All this also works in this setting if you kind of translate it across. So that's nice, but unfortunately it only deals with kind of the basic structure. It doesn't deal with pi types, for example, and it's with the other more involved type formers that you really start to get into problems here. So even though strictification works, it doesn't help with this thing. So unfortunately, I guess there's no silver bullet, right? So to summarize, some things work well, some things doesn't work so well, and some things kind of works, but it's not enough. Okay, so to summarize, we developed a representation of the syntax of type theory in type theory. I would say it's inspired by natural models rather than categories with families, just to give it a foundational grounding. But the main idea is that we have this tie-of function rather than indexing the terms over the types. And the good news is that it leads to fewer transports, which makes it easier to actually get cubic lambda to accept this. The bad news is that when you actually do things with this, then the same kind of transport seems to creep in again, and it doesn't solve all your problems, even though it at least lets you get there. So to answer the question in the title, can we formalize type theory intrinsically without any compromise? I would say not yet. Thank you.
Do you have questions?
You said that your contexts were in type, whereas everything else was in set, but they only contain types which are in set, right? In the syntax.
Yes.
So you could also lower the universe for context for the syntax.
So the contexts in general, I allow to be anywhere. They are unrestricted, right? Everything else I need to restrict to be a set.
But they could be restricted, and it would still type check, right?
Yes.
Yes.
It's more of a feature that you don't need to restrict it. I mean, it's the same way when you define the notion of a category. You typically want your hom sets to be sets, but you can allow your objects to be anything, right?
But it also means that there is no binding for a context in any of the constructors. It's a parameter.
Except parameter, yes, that's true. Yeah.
Okay.
Can the next speaker come to set up while we are still asking questions?
Thanks for the nice talk. For determining, like, do you have some intuition what would it take to get rid of it? Probably you need to modify cubical alpha, but is it realistic to prove these naturality properties on the fly during the definition of a type?
That's a good question. I'm not sure. I mean, I think the thing you would like to do is I'm not sure if you remember how we formulated. We said that if you had an equality, then you got another equality. And I think what you would really like to do is to just inline that equality in the second one. And then I think it would be possible to prove it or just get it intrinsically. But it doesn't play well with the rest of our formalization, unfortunately. So, but yes, I mean, it would be nice if we could do something.
One last question.
Yes. Thanks for the talk. So I was wondering, so we've been telling to mathematicians for a long time that presenting fibrations in a fibered way is kind of annoying, and it's much better to present it in an indexed way. And basically what you're saying is that actually maybe we were wrong all the time. Is this a more general lesson, or like is this a particular instance, or like what do you make of this question?
I think, unfortunately, the answer is that sometimes you do it one way and other times you do it the other way, right?
And do you have ideas of like when is one superior to the other, or like some sort of general lessons that would apply outside of QIITs?
No, I mean, yeah, that's a good question, of course. I mean, I guess you try it one way, and if it doesn't work, you try it the other way.
Fair enough, thank you.
Okay, one last question by me. So, okay, I'll ask it offline. Thank you very much again.
Thank you.
Okay, so the next speaker is Harun Khan on the formalization of a proof calculus for incremental linearization for satisfiability modulo nonlinear arithmetic and transcendental functions. If you're ready, you can start.
Yeah. Hi, everyone. Welcome to my talk. I'm Harun, and today I'm going to present a work formalizing proof calculus for... Sorry. Okay, sorry guys. Yeah, so we're presenting a formalization of proof calculus for incremental linearization for satisfiability modulo nonlinear real arithmetic and transcendental functions. And this is joint work with a bunch of my colleagues at Stanford University and UFMG and University of Iowa. So the motivation is SMT solvers are used in many safety critical applications. and many of them require the theory of nonlinear real arithmetic or transcendental arithmetic, like for example for dynamical systems or digital signal processing. And here by transcendental functions we mean trigonometric functions and the exponential function. So there are many use cases of those functions and reasoning thereof. And then typically reasoning in these theories, nonlinear real arithmetic, NRA, and nonlinear transcendental arithmetic, NTA, is done through this process called incremental linearization. And so we decided to formalize the CPC5 implementation of incremental linearization in Lean. And in the process, we identified errors and missing hypotheses in the documentation, as well as mismatches between the documentation and the CPC5 code base. And in addition, we also successfully reconstruct these proof rules using the Lean SMT tactic. So that's our contribution. So first, let me explain what incremental linearization is. So yeah, you have nonlinear and transcendental functions, as I mentioned before, such as like the exponential function or trigonometric functions. And so what we do is we abstract these away as uninterpreted functions, and then we incrementally approximate them using linear bounds. So this doesn't guarantee termination. It could, just run. But it's a scalable alternative if you don't need exact solutions. Like, for example, in the figure below, you have like this nonlinear objective circle, and the question is whether the intersection of the circle and the squares are non-empty. And instead of just looking at the circle, you can approximate it using four lines and conclude that those lines don't intersect the circle or the squares. Incremental refers to, in the process, we could get better linear bounds as necessary. So that's incremental linearization. Now, the background we use for our formalization relies heavily on MATLib, mainly for real numbers. We also use a decimal approximation of pi to 20 decimal places, and I'll speak more about that later. We use the properties of the exponential and sine functions. And earlier in the talk, I said trigonometric functions, but really the proof calculus only deals with the sine function because other trigonometric functions can be expressed in terms of sine. Like, for example, cosine is just a phase shift of the sine function, and then tangent is just sine divided by cosine. So we just focus on exp and sine. We also use derivative libraries, and we use Taylor polynomial theorems, and also theorems about convexity. So now let's talk about the proof rules. There are 21 of these rules, and we could put them into three broad categories: inequalities, and then properties of sine and exp, and bounding pi, so trigonometric, and then finally bounding transcendental functions using Taylor polynomials. And for most rules, we prove a Lean theorem that encapsulates the rule. But for some other rules, we write a tactic. Like, for example, there's a rule that bounds pi, and we have a Lean tactic that does this. So let's go over each of these categories one by one. So for inequalities, for example, one of these rules is, so you have the multiplication of two variables bounded above by a tangent plane, and this is just equivalent to the following like linear conditions. And then similarly, you have the other version of the rule where the product of two variables is bounded below by a tangent plane, and you can replace that by some linear inequalities. So to prove this rule is more or less straightforward. We encapsulate it, we formalize it in Lean just as is in the proof rule, and we prove it using like nlinearith or any tactic that deals with inequalities. so here's an example of another rule. This one, you consider monomials, and you have, you know whether these variables are positive or negative, and then the question is whether the product of the variables are positive or negative. So like, it's better to see an example. So like, for example, A is positive, B is negative, C is negative, and the question is whether A squared times B cubed times C cubed is negative. And so this can be done by this tactic we wrote called arithmetic sign, which basically applies these theorems iteratively to the monomial expression. And so these theorems are just all possible cases of raising a negative number to an odd power, a negative number to an even power, and so on and so forth. Yeah, this is an example of a rule where instead of like writing a theorem, we have a tactic that applies theorems iteratively. Cool. And now, so now the second set of rules, which is about the properties of sign and bounding pi. So one example is a sign shifting theorem, which basically, so we always, in the proof calculus, we always want to work in the interval negative pi to pi, because we're using an approximation of pi. And so if we're too far from the origin, the error compounds. And so it's best to just stick to the interval negative pi to pi, which works in the case of sine because it's a periodic function. So this interval is enough to express everything. So for example, the proof rule is, given any variable y, I can find like a principal value of x in the interval negative pi to pi such that sine of x is sine of y. And in lean, we express this just as it's stated in the proof rule. And then very quickly, I could just go over the proof of how this works. So in lean, if we're already in the desired interval, then there's nothing to do. Otherwise, you consider shifting your variable. If x is greater than pi, then you shift x down to the interval negative pi to pi using this expression, the ceiling of the quotient of x minus pi over 2 pi. And then we just use a MATLAB theorem that says, if you add an integer multiple of 2 pi, sign does not change. So that's the main crux of the proof. And if x is less than negative pi, we just do the same thing, a similar thing. And then the next rule we're talking about is bounding pi. So this is needed for again, for the convexity of sine, for example. And so the rule says, given bounds L and U, whether is pi between L and U. And to do this, we use norm num, and we use an approximation of pi in MATLAB that's approximated to 20 decimal places. So if your L and U are smaller than this interval, or inside this interval, which is within 10 to the negative 20 of pi, then the tactic will incorrectly fail. So one thing that we could do for future work is improve this approximation so that this interval size decreases. And finally, the third set of rules, which is bounding transcendental functions by Taylor polynomials. So the idea is to use Taylor approximations as linear approximations to this sine function and the exponential function. So the main theorem we use is the Lagrange form of the Taylor remainder theorem, which basically says if you have any function f whose it's differentiable and has its nth derivative is differentiable in this interval, then f minus the nth Taylor polynomial is this remainder expression. And so this is in mathlib, but there's a caveat, and that it has this extra assumption that x is greater than x0. And in half of our rules, we actually need x to be less than the starting point. In particular, for Maclaurin expansions, you need x to be less than 0. And so first we needed to extend this rule to to remove this assumption, basically for x being less than x0. And the way we did that was we took this theorem and we instead applied it to f of negative x. And then we have like a bunch of like rewrite theorems that basically push negation signs into and out of Taylor expansions and into and out of derivatives and nth derivatives and so on. So we first extended the Taylor mean remainder Lagrange theorem to remove that assumption. And then here's an example of one of the rules that use this theorem. So for example, if I have exponential x of t is bounded below by the Maclaurin of the exponential function. And so this is for both when x is positive and x is negative. And this is how we state it in lean. And so in the first case, if t is positive, then here p of t is is the Taylor polynomial. So we look at the difference and we apply the theorem in mathlib, Taylor mean remainder Lagrange, and we examine the expression we get at the end, and we just have to prove that that's positive. And then for negative t, now we need the other version of the theorem, and once we use that, we get a similar expression to study once you do the difference between the exponential function and the Taylor polynomial. And then finally, one last example would be bounding the sine function from below on the negative real numbers. This is one of the rules where the documentation was ambiguous, and so we had to propose a theorem. And so this is what we proposed, where d is the degree is 1 above a multiple of 4, and then you can bound sine from below by the Taylor polynomial, where d is 1 mod 4. So in the process of formalizing 21 rules, we found some errors and missing hypotheses. The first example is there are some missing side conditions. So for example, one of the rules had a missing condition that t is bounded above. And then some rules just had incorrect or some ambiguous assumptions on the degree, which we had to correct. So for example, the one I showed just on the previous slide, and a similar rule for approximating below on positive numbers. So to test our formalization, we do proof reconstruction, which, so lean SMT is a tactic that from lean you can call CVC5 to generate a proof, and then you replay that proof step by step using a process called proof replay. So CVC5 proofs are replayed in lean in the form of lean theorems and tactics. And so in order for this process to work correctly, we need to ensure that the proof rules in CVC5, there is a corresponding proof rule in lean, and these are all saying the same thing. So the formalization was mainly to extend lean SMT for NTA and NRA reasoning. but there were some challenges encountered. The first being mismatch of proved rules and CBC5 output. So partially because the documentation in some cases was ambiguous, but also we had to refine our theorems to actually match the CBC5 code base. And then another issue that we ran into was computing a polynomial at a specific value is not possible. So we had to, in Lean, so we had to define computable versions of polynomials. Like for example, this is how we define the exponential Taylor function, and then prove equivalence to the Taylor polynomial of the exponential function as already defined in MATLAB. And then finally, if L and R are real numbers, it's impossible to decide whether L is less than R because real numbers are not computable in Lean in the general case. But in most of our cases, L and R are rational numbers, so we're okay. And then in the one case where L or R is pi, we use a 20-point decimal approximation, which can be improved upon as future work. Okay. So finally, here are some future directions. CBC5 sometimes fails to add casting steps, so there's a challenge when mixing integer and real values in mixed integer real valued proofs, and this leads to holes in the proof. And so this would require work at the solver level to ensure the casting steps are added for these like mixed integer real valued proofs. And then the second would be sometimes there are unjustified reasoning steps performed by the solver that creates holes in Leans, and then again this would require working at the solver level with the CBC5 team to ensure these holes are patched up. And that's all for my talk, and I'd like to take questions.
Could you say a bit about what proportion of proofs produced by CBC5 you're able to actually reconstruct? Or did you say that and I missed it?
Right, so we're able to reconstruct each and every one of the proof rules we formalized as part of this proof calculus. But we, like on like other benchmarks, so we have like our own benchmark, and we construct everything on it. Some like standard benchmarks, they don't use these rules, so yeah, we didn't use it. We didn't, yeah.
Am I correct that in CBC5 all numbers are in the same type? In CBC5, is there a difference between real numbers and other numbers? Are pi and 5 in the same type?
So, I mean, you could declare them as real numbers, yeah.
So that makes that all your formulas are mostly manipulating real numbers.
So, I mean, I guess you could also declare 5 as an integer, yeah, yeah.
But your problem of missing castings is because of this difference.
Yeah, because there are like some integer steps and there are real number steps too, and so like in Lean, I guess we need like casts between these types, yeah. But in CBC5, it just reasons like fluidly through all of these.
They're all numbers.
Yeah.
Yeah. Well, I think you can also try to work in the proof system in such a way that you use mostly real numbers and you mark the ones that happen to be integers or rational numbers as a subsets instead of being in a different type. So that would make it possible to remove the need for casts.
Yeah, that's an interesting suggestion. I think, yeah, I think like just manipulating real numbers is in Lean, that's challenging because they're not computable. But yeah, that's something we could certainly think about. Yep. Okay.
Thank you for So the next talk is about mechanizing synthetic Tate computability in history by Ruming.
Okay, hello. So today I'm going to talk about mechanizing synthetic Tate computability in history. So let me break down this title a little bit. So synthetic Tate computability is this abstract categorical gluing approach to meta theory of type theory. So if you want to prove things like normalizations or canonicity, sometimes you use this kind of a logical relation proof. And history is the main focus of this the main tool of this work, which is a Neupro-style proof of system based on extensional dependent type theory. I'll say more about this later. So as a motivating example, if I want to prove something like the canonicity theorem, which is to say that every closed term of type Boole is either true or false. The way I can prove this is via this Tate method. So the proof idea is you can equip every type A with a computability structure, and then you equip every element of type A with a corresponding evidence to the computability structure. And here's an example. So syntactically, you have that true is an element of type Boole. And you can equip Boole with this predicate to say that every Boole is either true or false. So think of this as a sort of a sigma type where the first component is the syntax in red and the second component is the semantics. And on the term side, you need to equip the evidence for this predicate, which in the case of true would be a left injection. All right, and let me group this piece of data together a little bit. So let me group the term part, let me call it the blue capital true, and the predicate part to be the blue capital Boole. So if you think of this as a sigma type, indeed, the blue true has type the blue Boole. And you could do this for other constructs in your language, like the elimination, for example, the case analysis. The syntactically on the top will be the syntactic if, and the semantic will be a case analysis on the Boolean. Remember, the semantic of a Boolean is an injection either to the left or to the right. So you can case analysis on this. If it's a left injection, then you return a true branch. If it's a right injection, you return the false branch. And more importantly, you can check that all those blue terms behave exactly like the red terms, meaning that they satisfy the same equations. Like, for example, on the screen, that's the beta law for the if. And the way you verify it is you plug in all those definitions for the blue if and the blue true. And indeed, syntactically, that would be syntactic if true, which is going to the true branch. And semantically, it's a case analysis on the left injection, which will give you the true branch as well. So therefore, if you have an element, arbitrary element of type Boole, you can take this process, which I call bluify, the actions of turning red thing into a blue thing. Then you can obtain a proof that the term that you have is either true or false. And more importantly, after this, you need to verify that when you take the top part of the result of bluify, you get back exactly where you started with. And the reason for this is you want this E to be the E that you care about, the U you started with, not some arbitrary Boolean to have the proof with. And categorically, the story is like this. You start with a syntactic category T, and you define this functor bluify to some sort of a gluing category where the gluing category has object where it's two parts. The first part is the syntax, the second part is the semantics. And the gluing category has some sort of a projection functor pi back to the syntactic category, which is to just isolate the syntactic part. And then you verify the bluify functor is indeed a section of the projection functor, meaning that if you take the round trip, you get back exactly where you started with. And this is an analogous thing of the fundamental theorem of logical relation if you are coming from a logical relation background. So this approach is sometimes also called Artin gluing or proof-relevant logical relations. And it's sort of a large proof because you sort of need to go through every single thing in your syntactic category, which is inductively defined. And some of the proof obligation, because you're specifying a functor, is kind of tedious. Right? For example, the naturality condition, which is to say that all the operation preserve substitutions. So this is the analytical story of Tate's computability, or as French call it, the reducibility candidate. And the synthetic story of the same thing is you can describe this functor, the Bluify functor, in a type theory. And the type theory admits a model in the category, and therefore it gives you back the logical relation as you want. So here's the idea of synthetic Tate computability, which is introduced by John Sterling in his thesis. So you build a type theory starting with one axiom, which is you have an intuitionistic proposition seen, which represents the syntax that can control whether you are talking about the syntax or are you talking about the semantics. And it induced a pair of modalities. This is the idea from homotopy type theory, the open modality and the closed modality. Let me not tell you how they are defined, but they satisfy one property, which is open of closed A is isomorphic to unit. What that means is if you mark things to be semantic under the closed modality, you have a way to completely erase them, namely to use the open modality to completely erase anything that is semantic. And therefore, this open modality is sort of the synthetic projection functor pi we saw earlier. So a bit of a history of synthetic Tate computability. It has been used to prove a lot of meta theory for a dependent type theory. Maybe the most famous one is the normalization results for Cartesian cubical type theory by Starling and Anjuli. And most recently, I myself proved the canonicity for cost-aware logical framework using the same proof technique. So cost-aware logical framework is this dependent type theory, dependent call-by-push value language, which my group has been working on for the past couple of years. So it's a type theory that is specialized for cost verification of algorithms and data structures. So here's the technical detail for synthetic Tate computability. Remember, I say we need to put the semantic information under the closed modality, and here's exactly the same thing as before, except for the predicate that the syntactic Boolean B is either true or false is under the closed modality, which is marking it to be the semantics. And on the evidence side, we still have the left injection, but it's guarded under the monadic return for the closed modality. And why is this useful? Maybe it's not obvious immediately, but we can show that under the open modality, the blue true, which is this part, is equal to the red true. And the reason for this is this part is of type closed something, and open of closed something is isomorphic to unit, which goes away, so leaving only this part, and therefore we can prove this equation. So the proof goal of synthetic Tate computability is to construct all those blue terms, like blue true, which is a term of type bool, such that under the syntactic, under the open modality, which represents the syntax, they give you back exactly what the syntax you started with. So as a piece of notational device, I would write sort of this subset type notation or extension type notation where true is an element of type bool such that syntactically it's equal to true. It's just a piece of notation. So to prove the fundamental theorem of logical relation, it suffices to construct all those blue terms, all those blue counterparts to the syntax that you have, for example, the Booleans, the true and false, and if each of their corresponding type that you would expect, such that syntactically they are equal to the syntax they started with. So let's do that. So I just write on those types, and I want to give terms of those things. And the technical detail of how exactly we write down those terms are sort of irrelevant. But in almost all cases, there's only one way to make everything type check, reducing the complex logical relation arguments into some sort of programming puzzle in a dependent type theory. And here's the complete program. And we can do the same thing for like more complicated structures like pi types and lambdas and applications. And then you verify that indeed the blue terms satisfy the equation, for example, the beta laws. And just give the term. It's exactly as shown on the screen. Again, technical details doesn't really matter. So the proof is quite short. In fact, it's too short that it fits in 2 of my slides. But this can be kind of deceiving because there are a lot of details that are behind the scene. And the first kind of detail is the hidden transport reasoning and equality reasoning. If we look at, for example, the semantics of lambda, the computability structure for lambda, in order for this thing to type check, it actually needs to transport along a bunch of equations. In fact, this is the first equation you need to transport along. And then in fact, in order for this equation to make sense, it needs to transport along another equation, and a bunch of other equality reasoning. So in many proof of systems, like ACDAs or ROC, this will lead to transport hell, the similar kinds of thing that we heard about in the first talk in this session. Except for in their work, the transport hell arise from the substitution calculus. Here, the transport hell arise from the modality framework that we work with. So there are other reasons why this proof is kind of short. Maybe the most notable one is function extensionality, which notably is not provable in ACDA or ROC, those intentional proof of systems. So my point is none of your favorite proof of systems support all those features I need in order to make my synthetic Tate computability nice and beautiful, except for one, or at least I only know one, which is Astari. It's this new proof of system that is being developed at CMU, which is a NuPro-style extensional proof of system based on computational semantics. So I'll remark a little bit more about NuPro and computational semantics. So the idea is you start with raw syntax, and you build operational semantics around those raw syntax. Building on those operational semantics, you can build per model, which is the logical relations. And because the logical relations are sort of extensional at functions or equalities, you get those extensionality principles for free. And that's why it's an extensional proof of system. So here's a little bit of more features about Istari. The first thing is the typing judgment is internal to the language. For what that means is this thing M:(A), M of type A, is a proposition to be proved by the users. Right? This is not like in ACDA or ROC where you write down the term and you write down the type and you click a button, the type checker automatically type check everything for you. And the second thing is this sort of a substitution principle. If I have n equals n prime, which is a propositional equality, Istari validates the equality reflection, which is to say that the judgmental equality coincides with the propositional equality. So if I have n equals n prime propositionally, I could also have m of type an and at the same time m of type an prime. And last but not least, most famously, this kind of thing is undecidable. The type checking process in extensional type theory is undecidable. But really, this is a feature, not a bug. Because if the type checker is stuck, the user can manually take over. And typically, when that happens, the user have more domain knowledge about how this thing should be type checked, and therefore they can do things better than the type checker. So here's a bit of an example, a very small one. If I want to write a function, vec m plus n to vec n plus m, just swapping the order of the arguments to the addition, I can write down this type, and I can write down the term, which is the literal honest identity function, lambda v dot v. And then my goal is to prove that the identity function, the term that I write down, indeed has the type that I specified, which I then need to use a series of tactics, which is like this. And you notice that I call the type checker will run everything, and it will get stuck. Because at some point, it would need to prove that m plus n is equal to m plus m. And that's when the user can take over to apply whatever lemma that you can prove by induction. And notably, in ACDA, you would say, you can't write something like this. You would have to say lambda v transport of this equality of v. And that complicates the reasoning about anything that involves this function. So building on this, equality reflection and all those other features in Istari, we built a library for this synthetic phase distinction that is necessary to do synthetic Tate computability. For example, the modalities that I showed you earlier, as well as a bunch of other things. So here's another example to show our mechanization. So this is the lambda, the semantics of a lambda, and this is quite literally what you would write on paper, for example, from Sterling's thesis. And in our mechanization, it's quite literally word-to-word transcription of what the on-paper term look like. I would just highlight, so we specify the type, we specify the extension part, the syntactic part of lambda, and for the term, it's the syntactic lambda as well as the semantic. And you'll notice that there, in the term itself, there's no transport, there's no equality reasoning, even though they sort of have to exist somewhere. And the place where they exist is sort of in this ... where it's establishing that indeed this term has this type through a series of tactics. So maybe the main takeaway is our mechanized proof is almost a verbatim from the on-paper proof. Well, except for Istari doesn't support Unicode, which I guess in the proof assistant community is sort of a deal breaker. But anyway, so we mechanize in this work, we mechanize the canonicity model for dependent type theory, which has the pi type and Boolean with a large elimination, as well as the causal logical framework that I told you about earlier, which featured this free forgettable junctions, F and U, as well as the computational effect for cost. So let me do a little bit of a comparison. So the intentional proof assistance versus the extensional proof assistant. So maybe the main thing to say here is where exactly is the proof, right? So in intentional proof assistant, all the proofs are in the term, right? All the equality reasoning, you have to put transport maybe here and there. And once you have those terms, once you massage all those equalities into the term, the type checking process becomes automatic. Whereas in the extensional world, all the proof, all the main proof happen in the typing derivation. And therefore, if you write on a term and you write on a type, you need to manually establish that the term indeed has the correct type. And this process, this type checking process, is mostly automatic because there's the default type checker. But because the undecidability problem, the default type checker sometimes gets stuck, and the user can manually take over. And both can do this kind of a mechanized Goulian arguments, the logical relation, the categorical logical relation for meta theory, and most notably on the intentional side, Kapasi and Puget in a very recent ICFP paper showed how to mechanize this Goulian argument in ACTA with a observational type theory layer built on top of it. And this work is about mechanizing synthetic Goulian argument in an actual extensional dependent type theory. So when I put the paper online, the immediate reaction I got was, at what cost are you giving up the decidability of type checking? And here's the cost. So we need to write those lines of tactics in order to establish the well typeness of those derivations. But it's really not too bad. It's quite manageable. Like for the Booleans, the terms related, the semantics related to Booleans, it's like 100 lines. And for pi's, it's like 200 lines, 300 lines, something like that. The only thing that is quite bad is the large elimination, which in this case takes about 1,000 lines of tactics. But this whole process is sort of mechanical, and it's quite manageable. And I want to conclude my talk by quoting a CPP paper from a couple years back, which says that accordingly, those Goulian proof have some sort of extensional flavor, and as such, are less amenable to implementation in a proof system based on intentional type theory. Moreover, the more sophisticated iteration, which they're talking about synthetic data computability, rely on multimodal type theory as internal language for future reach category for which the mechanization is still in its infancy. So hopefully, my work convinced you that it's indeed possible to mechanize the complicated synthetic data computability argument in a modal dependent type theory that is actual extensional. And that's the end of my talk. Thank you.
Thanks for the talk. It's very nice work. I was wondering, so how much of this could be reproduced? So we had the talk yesterday about this kind of embedded proof assistant in a proof assistant. How much of this could be reproduced inside a proof assistant rather than like through an external proof assistant, and then all of these things would at the end of the day elaborate to intentional type theory, and then the type checker would be trying to derive equality proofs, and when it fails, it gives you manual obligations to prove these things yourself. And like, I feel that in a sense, this should be possible, and maybe allow you to kind of go back and forth between the external point of view and the gluing category and the internal view? Like, what do you think of this?
Yeah, I think it's certainly possible. What you're asking basically is how can we use the technique from Vortex talk yesterday,
Exactly.
that's from the synthetic lean to our approach. I think it's totally possible, maybe not immediate, but it's totally possible, because here in my work I only focus on the synthetic side because I have a synthetic language I want to program inside it, whereas in their work they are trying to develop for an arbitrary synthetic theory they can encode into some sort of a semantic model. So I think there's completely connection there that we can explore, but again, my work is completely on the synthetic side.
Thanks.
I have a small question about history.
Okay.
Back in the day, one of the main concerns about New Perl was the large amount of rules. At the end, it was something like 300 reasoning rules. Is it something that also happened in history, or is it more principled? I mean, smaller reasoning-wise?
I personally have not experience with NuPro, so I don't know how to compare. But my user experience in Istari is quite pleasant. In fact, it's probably more pleasant than my experience in Agda. So I don't know how to compare. I mean, I heard that NuPro is hosted on some sort of a server, which I don't have access to. So I mean, Istari is sort of a modernized NuPro, which you can install on the laptop and use it. I have to say that the experience has been quite pleasant.
Okay, thank you again.
Thank you. Thanks.
So the next talk is about building blocks for stepped index program logics, and is Thomas Sommers presenting.
Okay, thank you very much for the introduction. So I'll be talking about building block for step index program logics, which is work I co-authored with Jonas, Leonard, and my supervisor, Robert, who is sitting somewhere over here. So before we start, the main things we need, of course, are program logics and step indexing. So let's briefly start from the program logic side. So on the program logic side, generally what you do with a program logic is you take a program and you prove some property about the program. But you can also do more general things, say prove something about entire programming languages, such as type safety, using the same program logic approaches. So for instance, you do this for type safety, you do this by giving a semantic model of your types and then using your program logic rules to apply. But of course, program logics are complicated, so we also run into these issues where we say have types with cyclic features, and then we have to handle these as well. For instance, in Haskell, you have these recursive types, such as infinite lists. You can have things such as session types, which can give you recursive and repeating protocols, and also some form of, say, indirection via the heap, which allows you to create these cyclic structures, such as the box type invest. So in this case, we need to make sure the semantic model itself is also well-founded. And one well-used approach for this is to use step indexing. And then with step indexing, what we do is the semantic model, we index it by the step index. And then if we have, say, some value in the semantic model, we say that it behaves like it for a specific amount of steps, which is the step index. So the main issue with doing this directly, as was done initially by Appel and McAllister in 2001, is, well, now if we have the step index everywhere, so in all our proofs we also have to do this explicit reasoning about the step indexing, as you see in the bottom there. So a better solution is to instead extend your logic with some internal notion of step indexing, which you can do using this later modality, which is the arrow there. And then that says that, well, if we have later p, then p only holds after we take the next step. So this corresponds to changing the step index. And now nicely, if you want to give both the model or do any proofs, you only have to reason about the later itself rather than all of the, well, numbers, which are the step indices. So for instance, if we want to define an infinite list or a stream, you can say that a value is in the stream if the first part of the value has the correct type And then after some step, we only check. Only after some step, we force the second value and check that it's also a stream. And this allows us to create these cyclic features. But well, this is nice from the modeling side, but of course, on the user side, we have to work with this later. And it's it's trivial to introduce this later, because if we know something now, it'll remain true in the future. But then we get to the later elimination problem, which is where we actually want to get rid of this. And there's a few different approaches that we can do to get rid of one of these laters. So the first one is if our proposition doesn't depend on time at all, so it just remains the same, well, we can get rid of the later. Another one is that the later nicely commutes with other operations such as conjunction, separating conjunction, existential, and universal quantification. But the main one that we will be focusing on is if you take a program, in our program logic, we tightly couple the step indexing with our program steps, such that when we take a step from E to E prime, we can actually get rid of one of these laters. And then there's also a newer one from 2022 by Spicer al., which is later credits, where we instead of removing the later directly during a step, we get the permission to do it as a token, and then we can use it at some other point. But it is relatively orthogonal to our work, so I won't go into details. So this is all nice. We now know how to eliminate one later. But that leaves a problem, because sometimes one later is just not enough. So for instance, if we model session types where we can send without waiting for the other side to receive, we run into where we have a number of laters corresponding to how many messages are in the buffer. You also have, if you model something like Rust's mutable boroughs, those can be nested and also induce multiple laters. Or something such as in Perennial, where we're talking about what happens to resources when the system crashes and recovers, and you also get multiple laters there. So now we don't just have the later elimination problem, but the multiple later elimination problem, where we have to eliminate a number of laters, and moreover, sometimes that number of laters may depend on the number of program steps that have already been taken. And the thing we encounter in the ecosystem so far is that different program logics for different applications use different approaches for these multiple later elimination. So that's what we're going to tackle in this work, is, well, we have these different approaches for doing this, but we want to unify this because, well, if you want to, as a user, you just want to use one of these program logics and you want to say, hey, this approach looks nice and I want to use that one. But, well, at the moment, you're stuck with the approaches that are implemented by the program logic. And we're specifically focusing on those program logics, so the domain-specific program logics that are built in the Iris separation logic framework in Rock. So there's a few sub-goals as well. So the main goal is to unify the approaches, which consists of making sure we have consistent proof rules. So for multiple later elimination, you have consistent regardless of which program logic you're in. The other one is, well, if someone creates their own program logic and they want to do multiple later elimination, we want to make it easy for them to also get these rules rather than doing everything from scratch. And the last one is, well, I already talked about how users should be able to pick which approach they want to use, but moreover, if the number of laters you need depends on your approach, we want the user to be able to choose that rather than having it fixed by the program logic, which is currently done. So before we get into that, this is a very, very minimal overview of Iris. It basically consists of 3 layers. The bottom layer is our separation logic. So that defines the separating conjunction, how to work with resources, updates, and that sort of thing. And then on top of that, we have the standard Iris program logic, which is one of several possible ones, which defines the weakest precondition, and then the proof rules, which is modeled in terms of the base logic. And then on top of that, you can instantiate it with a language of your choosing. So that's generally in operational semantics and, well, the syntax and values of the language, of course. So the standard language is heaplang, which is an OCaml-like language with heaps. But the Iris program logic is not the only program logic that we're talking about. There are multiple. So we have many specific, domain-specific program logics, which are all built out of the components in the Iris base logic that reuse the separation logic. Two notable ones which do multiple later elimination are Twillium, which does trace refinement, so also allows you to reason about things such as fairness, and Perennial, which talks about recovery in the case of crashes. So if your system crashes, can the recovery get back to a state that you want to be in? So those are the program logics. They define the weakest preconditions. But of course, on top of those, you also have other things, such as different languages. So refined Rust is a model of Rust and semantic typing in Rust. Golang is, well, a Go semantics, and then you can also stack on top of, say, other languages. For instance, Actress adds session types and session type channels to heaplang, and Aneris adds session types to Twillium. So we have this nice landscape, but, well, which approaches do these actually use? Without going into detail of how the approaches specifically work, going through them, these ones use later credits, which was the fourth method I was talking about. These ones use something called persistent time receipts. These ones use additive time receipts. And these ones use something called a step update modality. But sadly, none of them actually use all of the methods. So if a user doesn't know which one they want to use yet, well, there's no good place from which they can use all of these. And what we want to get to is make sure that all of these are all colored so they can use everything. Quickly, before we get there, let's briefly talk about what we actually need to know about, say, one of these program logics. So focusing on the Iris program logic in the middle, well, there are two parts that we mainly care about. The first part is that you can actually use it as a program logic. So for that, we need to define the weakest precondition in terms of the lower layer, so the base logic, separation logic. And then from this, we derive our Hort triples. And, well, the proof rules are just statements, so the lemmas about the weakest precondition, which you can prove in ROC. And then that is the program logic you use. But also on the other side, we want to know that our program logic actually means something. So the second part that we mainly care about is a theorem called adequacy, which extracts the properties from the weakest precondition. So for instance, for the Iris program logic, this is safety in that your operational semantics does not get stuck. Zooming in on the first of these, let's briefly look into how the Iris program logic is defined. So without going into too much detail, we'll just focus on the later elimination part. So the weakest precondition either is already a value, in which case the post condition holds, or, well, it's in the current state, it's reducible, which is red, and then after any step we can take from that point, we still have the weakest precondition. But it's guarded by that one later. And that allows you to remove the later for each program step, as we did on one of the earlier slides. But sadly, when we move to multiple later elimination, that single later is replaced by this mess. So what do we do now? Well, we need to keep track of how many steps we've already taken, which is the n. We have to match it to some sort of resources, which are the time receipts in S. We get the later credits, and, well, you have to iterate the number of laters again. So what does this mean? Well, if you want to make your own program logic, are you going to want to do this all again? Probably not, so you'll opt out, or if you encounter a problem where you specifically need it, you'll add it at that point. But that means if someone else wants to work on your program logic, they have to implement all of these as well before they can start doing their thing. So what does this mean? Well, we have multiple later elimination. Great. But, of course, we have a few things. So first, we're kind of adding back in this step index that we wanted to get rid of by using the later modality, since we now have to keep track of the n again. And the other thing is, of course, various approaches have hard-coded various versions of these for their specific domain. So if you want to use one of them, you're stuck with their approach. And if you want to do this for your own program logic, you have to basically start from scratch. So what we instead do is we create an extra building block on top of the Iris base logic, which basically says we have P after doing all the multiple later elimination for that program step. And this way we again get the tight coupling between program steps and using this modality. So it looks like this in the diagram. Very simple. You add an extra brick, and then we now have a single building block. So if you want to do multiple later elimination, you don't have to do from scratch. You instead just replace the later by this thing, and it pretty much works. So let's see, that says, oh yeah, we have all the approaches that all these projects used to have already. So now if anyone uses that in their program logic, they can relatively easy migrate all the proofs that require multiple later elimination to their own program logic. And that one I talked about. And well, the other thing that is not specifically visible here is that we shifted the perspective from the program logic choosing how many laters you need per step to the users can independently choose how many they need, and then we have a way of combining them such that you always have enough. So I already showed this one. So now if we actually use our building block, it looks basically like the first one. You just replace the later by a physical update modality, and you're there. And similarly, if we want to derive some form of rule, if you do it without our building block, well, it depends on specifically how you hard-coded multiple later elimination. So for, say, standard iris that is using that definition. For perennial, there's an even more complex one to support more features. So if you wanted to add that to some other program logic, you would have to do this all over again. And well, as I mentioned, if you want to reuse it, you can't. You have to do it from scratch. So of course, with our building block, this gets quite a lot easier since we just replaced the later by our modality. What we did the hard proof, which requires modeling all of these multiple later elimination approaches. And then what you do for each proof rule that you want for your program logic, you go through the definition, you unfold it until you get to this modality, you apply the corresponding rule, and then you fold everything back up. And that's all you have to do. So it's really straightforward to derive all of the multiple later elimination methods. So for instance, very briefly, if you want this program logic rule, which is, for instance, in heap lang, well, all you do is you unfold the definition of WP, you simplify a bit, and eventually you get to the shape on the right, you apply it, and then you fold everything back up. And you can do this for all of the methods, and that makes it a lot easier to be consistent across both program logics and make sure that you have all the approaches. So what we actually did with this is to verify it works. We looked at all the projects at Iris that use multiple later elimination. So those are the ones on the board here. And then we converted or migrated them to use our physical step modality in their program logic and ensured that all of the user-facing proof rules just remain the same. So with our modality, we can not only do all the same things, but we can also model all of the proof rules, so the multiple later elimination proof rules that were previously hard-coded in terms of the basics in our modality. So that is the main part here, and I wanted to briefly mention two small conclusions from this. The first one is that because we provide all of these methods, you give the user the choice what they need rather than having to use the one in the program logic. A good example of this is linking actress. So linking actress is an extension of actress where you can merge two channels, which forwards all the messages between them. The issue was it's based on Iris's heap lang, which only had persistent time receipts, but the most suited approach was another one, which was the additive time receipts. And previously, this had to be hacked by using an invariant and the other method. But now, after migrating to our physical step modality, you just use the additive time receipts that you always wanted. And the other nice thing, the other nice thing is that we changed the number of laters to be chosen by the user. So a lot of our rules are parameterized by this function f. So if you somehow encounter that you need more laters than are provided, well, you increase f, and at that point you should be able to get there again. So if you want it linear, exponential, whatever you need. The nice thing is that all the rules can be weakened, so you can always derive a smaller one from the larger one. And this allows us to use Cox's type class mechanism to define a type class that allows you to if you're a user, you can choose a function f that you need for your approach, create this type class, and then in scope of that type class, all of the lemmas will use that f. And then if someone else needs, say, twice or 10 times as large a function, they define that one. And then only at the end, when you're constructing the final adequacy proof, we extend the framework that Iris already uses for working with ghost resources, for also creating the function that you need here. So you always know that you have a large enough one. And you don't have to care about, say, someone else's need for a larger or smaller function. So this was mostly a high-level overview since I didn't have a lot of time. So we have more details in the paper. We have quite a bit of work in the paper about which details how these multiple later elimination approaches actually work, and how to combine them, because some of these seem disjoint at the start when you initially look at them, but they do all work together if you have the correct model of our modality. So by using a building block, all of these projects can use the same approaches. And also, for the program logic side, I only talked about how to derive the rules for now. On the other side, we of course have the adequacy statements, and the paper also talks about how we simplify proving this adequacy statement by doing all of the bookkeeping of laters. And then, well, to conclude, the paper talks about some details related to migrating each of the projects. So that is the conclusion. Thank you.
Is there a question?
Thanks for the talk. You said that the user can specify like this f function. Are there any restrictions on that? Like it has to be monotone and n or anything? Or the user's totally free to?
The only restriction is that it has to be 0 at 0.
Say I'm doing something with, I don't know, additive time receipts. What would I have to do to integrate this with my project?
The main question is, are you using iris separation logic?
I am using iris, but I'm not using the iris WP.
So that is exactly what we're working on. So if you have a WP and you had, say, later, well, the main thing you do is, let's see quickly, if you replace the later with a modality, you can then quite easily from the structure of your proof rules derive these multiple later elimination rules, and then you get these additive and persistent time receipts. So, but if you already had some, you might have to redefine your version of additive time receipts in terms of ours, and that should be about it.
Okay, thank you.
Another question?
So very nice talk, thank you. So these existing approaches, could they be simplified using your version? Do they sort of need to keep track of the manual step indexes like they did, or have you sort of figured out a way to sort of get away from it so that they can be made simpler as well?
The approaches themselves don't particularly get simpler. It was, so the main thing here was to make sure we consolidated all of these approaches such that they, one, work nicely together, and two, if you have a program logic, you can add all of them. So if, say, you want to move something like session types from actors to Go, you can now do that by reusing this modality instead of having to convert everything. On the actual simplification side, we haven't done too much on that.
Okay, thank you.
Thank you.
The next talk is online.
Pour l'instant, il y a un souci technique avec le talk online. On est en train de voir comment le résoudre.
Okay, so there might be a little bit of delay. There's a technical issue.
The next speaker is remote.
Yes.
He was supposed to be on Discord, but he had some problem on Discord, so we want to try to do on Zoom. If some of you has a laptop that you can use.
With Zoom?
Zoom, yeah. You should have sent a link to the workshop organizer. Or I don't know if you can make it. Yeah, no,
You have a workshop organizer.
Yeah, you should make the people should have sent to you a link. Yeah, he was not able to share stuff. Yes, yesterday was working. Now it changed on computer. I don't know. Hi, Jimmy. Okay, you are, huh? Okay.
Turn up volume, maybe.
Yeah, try to speak. Sorry? No, I think you need to, choose the right output.
What's going on?
Okay, you just pick the right speaker, right?
Yeah, I hit it down.
Okay, try to speak, please.
Can you hear me? Wait. Can you guys hear me?
Yeah. I'm not sure if Larry
Is he not out? Should we here if we are we on the Zoom call?
Maybe
Yes.
collective share.
We want to do.
Yeah, okay. Try to speak, please.
Are we getting volume from him over here? Don't think so. No.
Là, tu es en train de partager ta présentation du business meeting.
Ouais.
Je pense que tu es en full screen et que du coup ça prend le dessus. T'enlèves full screen de...
Is he speaking right now?
Can you ask to the presenter to speak, please?
Can you speak, Jimmy, please? Speak.
I'm not sure if they
Boy.
We can put a mic on the computer.
I can't hear the cursor. There's the cursor.
Yeah.
Select speaker, HDMI to USB. Microphone. Can you
Maybe
hear? You can hear us because that's going through there. If we go.
Can you do same as system and back, maybe?
Yeah, we can try same system. Can you speak? Okay, no, you cannot speak. Cool. why is this why is Discord cursed right now?
I was not able to open the camera and show the screen. Okay. We can try to figure out like if we use this.
Hopefully there is only one remote presentation at CPP this year.
Move this talk in the afternoon so we can figure out to like fix this current issue.
Yeah. I mean, we can go. It's lunchtime anyway, so.
So when do you want to move it?
What we can do is that we.
If you can decide what time I'm.
I think it's up to the organizer.
Yeah.
So we can figure out your Discord problem. How would you move it?
Donc j'annonce que I'm announcing that we are moving the talk to the afternoon.
We can nice talks if we can do the very last talk.
CPP talks.
want after that, so we can.
So let's do that.
Is it okay for Jumi? Jumi, is it okay at 5:30 local time? That's about 4 hours, 5 hours from now.
Okay, so 5:30.
We will think
Okay, so the afternoon, this talk will be moved to the afternoon session at 5:30.
I will send you an email to make sure. Sorry for that. And we use this one? We will use this for now. I can.
joined work with my previous supervisor, Anthony Lin. Yeah, I'm in Buckenhausen, but he's in University of Kaiserslautern. Yeah, so let's get started. First, I want to give a motivation example because, like, we want to. Now we use internet a lot. We have a lot of web pages. We interact with them every day. For example, here we have a small, like, the text input window. You can, like in Google, like in YouTube, you can write some comments there. So here you can write some text there. But there is some JavaScript code behind it. Its first one is the cat is a variable of the text you just input. And then for X, it just calls the function of HTML escape. It's a sanitizer. It will convert some characters to its HTML entity encode. After that, it just for security reason, we don't put what the users input into to transfer it to the server. And the second one is escape some strings. We also want to make some string not unsecure for the browser or for the server. So finally, it will generate in the HTML. It will create a cat list. So like if you just input some like a cat 1, cat like Tom, something like this, it will create a cat list. This is the intention of this code. But the thing is like this code may have some bugs because we don't know whether HTML escape and escape string do their work correctly. So if we just input the flora and fauna, okay, that's okay, because of step 1, the HTML escape, we will just escape the characters of the end symbol. It's the HTML entity. And second, escape string will do nothing because no character to escape, so it keep it unchanged. Third one, just create a catalyst. It works, everything works fine, no problem, no exceptions. But the thing is, some users may input others, like this one. It will input alert with some prefix and suffix. Finally, after the HTML escape and escape string, it will generate JavaScript functions. So when you click the button, it will jump out, something like this. This is obviously not what we want. And also for all the web developers, they don't want something like this. This means their code have something, bug. And here we just put alert there. Probably we could put other more, dangerous, risky functions here to steal some data from the users. So this means that filter the user input is very important for the security of web applications. But whether can we to verify that the programs the users just wrote to make sure that we guarantee that the user input will finally be transferred to something, to transform to something legal and won't hurt others, won't hurt our systems. So like we can use SMT servers like here. We have 5 constraints. First one is like we could encode the HTML escape as a function, right? And then put the result of the HTML escape to escape string function. After that, we use the concatenation. Here the plus is the string concatenation. We concatenate them together, we get the Z, and then we use the in the HTML function encoder to further transform it to the inner cat element in the ML. So this means we finally get the final string to be showed on the browser on your web page. But we need to check. The last line is say that whether it matches some unsafe strings. Like we can use regular expressions to express this string is unsafe. So when we put it there, we can check like whether it matches or not. If it matches, that means our code have some bugs. This is what we want. But the thing is here, how can we model the semantics of these functions, HTML escape, like escape string or like in HTML, these things, stuffs. We must have mathematical models to model it and then verify it. So the solution is, our solution is the symbolic finite transducers. So it's, this slide I give some like very boring but text definition of it. It's It's the transition label classic is just the transition label just characters from the alphabet. But in symbolic transducers, it uses like the predicates of a Boolean algebra. So it means the symbolic one. We always know that symbolic stuff more concise, succinct than other explicit one. And it also can support infinite alphabets, provide more efficient execution of the label transition operations. And the key advantage is to avoid the big alphabets, because for web applications, we may have like the Unicode. Unicode have like more than 1 million characters. When we try to handle them, we must be very efficient. Otherwise, it's useless for the web response. Yeah, but after this, we can think about like two simple example to show like the power of the symbolic finite transducers. Like the left one is the classic one. We want to express that the transducer has some input. We want to accept input with only even numbers. The f is some output function. It means that we get the input 0, we will compute an output character based on 0. The thing is, this transducer want to accept all like even number of sequences, like 0, like 2, like 4, 6. The classic one, the thing is, the even number is infinite, so yeah, we can't use it to impossible to represent. But with symbolic one, we could just with only one transitions like here, x mod 2 equals 0. Then we can say that all the x satisfies this predicate, then we just accept it and compute the output function using f. So you can see that it's just one transitions. It can express infinite alphabet. So this is advantages for us, also for us to use to represent the application functions. I give another example, probably more easy to understand for the web applications. We have we want to match the pattern. The first is a sequence of lowercase alphabet A to Z, and another sequence of alphabet characters and big uppercase A to Z. But we want to use the transducer to transform all uppercase to lowercase, but lowercase to uppercase. So this transducer will do this work. So you can see that from Q0 to Q1, it just try to accept all the lowercase characters, and when it get it, it will output to upper function, change to its uppercase. Similar for the uppercase matching one. So like the example input is like when we input the big small, the output is not big small, but it changes the lower and upper cases. So this is another case or example of the transducers. Okay, now we give the formal definition of the transducer. It's for the status, it's quite classic, like NFA, DFA, something like that. It's like Q is the set of status, and I is the initial status, and F is the acceptance status. The only difference is about the transition relations. In symbolic setting, the transition is about two parts. First is predicates. We try to match a character uses predicates. And the second one is the function f, the output function. And in Isabelle, we try to model it using some Isabelle symbols, like here. We have Q and Q prime are two status for the transitions from Q to Q prime. And we also have the transition labels and two parts. First one is a set option, and another one is prime f is the function. Okay, so here we don't use any concepts from the Boolean algebra. We just use it's a set. We just said, okay, this label is a set, because all Boolean algebra predicate can be represented as finally it just denote a set. So we use this abstract definition to make it easier to prove and understand. The output function is just we give characters. We use option time because we want to support epsilon transitions, not only the the characters in the alphabet. So it means that this opt function could when the input is an epsilon transition empty string, it will also generate something. So this is the basic Isabelle definition. With the definition of the transducer, we define a key operation because I say we need to model the the web applications, HTML escape, all these are similar like a function or something. So, but how we do the computation is use the product operation. So it's the here we use the T to denote the symbolic finite transducer, and A is a symbolic finite automaton. It's like the user input. The user input after the processing of the transducer is the result of the product. Some formalization details like the result may contain epsilon transition because our transducer contain epsilon transitions. And also we need to formalize the epsilon finite automata as well, not only the transducers. So I give two examples, like if the A is some strings or the Unicode, because the user can input all the Unicode string in the input window in your web pages, right? And the encoder, we have T is a transducer to encode the HTML sanitizer, and then the result is all the possible strings after the sanitizer, after sanitizing the input strings. Another example is like, okay, so the input is just a sequence of digits, and the T is just, we replace this sequence of digits to a constant string number. Then the result of the product is number. So this is the intuition behind the product operation we formalized. The thing is, we want to use it to efficiently to do some verification for the HTML or web application sanitizing. The thing is, we need to have a good way to formalize it. And also we have, because Boolean algebra have a lot of different forms. Like we have used intervals, we can use some arithmetics like x mod 2. All the different formalizations, we can't just, firstly we can't do them all of them at once. So we need a way to make it easy to extend to support different forms of the labels. So our way is to use the refinement proof based on the work library of Isabelle. So in the most abstract level, we just model everything with the mathematical concepts like sets, like maps, or something like that. But in the implementation layer, we use another data structure to store the status. Here we use red blank trees or hash maps. We can do this automatically, almost free, because I think in Isabelle there's a very brilliant library. It's called the Refinement for Monadic Program. This is a very brilliant library. Then you can write logarithm in abstract level, but refine to efficient data structures like red blank trees and hash maps. So yeah, and finally the second layer. After second layer, we still keep the transition labels as a Boolean algebra L locale in Isabelle. No concrete execution implementation, but in the last layer we will refinement to some, like in this paper we only refine it to intervals. So this is the basic idea of formalization. So to step by step, whether you want to add a new Boolean algebra representation, you just need to update the last layer. The first layer is fixed, don't need to touch them at all. So it makes us easy to extend. And also with the hash map and red blank trees, it will be very efficient to execute. This is the Boolean algebra locale we define. It's in abstract level, we define the semantics of your Boolean algebra, what set it represent. And also a lot of operations like empty, intersection, difference, membership element, and together with a bunch of assumptions to define what is the correctness of your operation implementation. So our interval Boolean algebra implements this locale and then automatically integrate into the formalization of transducers. So finally, we talk about the application and evaluation. The first one is, I say at the beginning of the motivation example, we want to do the sanitizer checking. We want to check like after the sanitizing, the output string won't hurt our systems, won't have some unsafe strings. So like for the single one, like the I is like assume it's an input, and T is a sanitizer we model as transducers. So their product, the result is another language for the output strings. Then with the intersection of the A is some tanks, like unsafe strings sets. So if their intersection is empty, means then okay, so our transducer functionality is correct. It's satisfied what we want. And the second one is like in reality, not all the sanitizer is not a single one. Usually a program will use a bunch of sanitizer to step by step. So we need like a composition of them. So like the second one, we first use trim sanitizer and then use the HTML escape sanitizer. After this two steps, we get the result. We check with the tank strings. If they are empty, means then okay. So the composition of our sanitizer is also correct. Also work perfect. So this is a sanitizer checking. We give another example like to show how to use transducer to model one of the sanitizer. This is one from the anti-access tank encode HTML in C#. The input is a string T, like user input string T. So after like the first one is like if it's null, then it's written null. If it's empty, then it's written empty. But the third one is if it is in the if branch means that it is safe. So we just pan it. We don't need to change the character. But for the other characters, we need to encode them into some code into the final strings. So this is the sanitizer from the internet we pick, but this one is very easy to be represented, to denoted as a transducer like this. Just one status, two transitions. Like when it is safe chars, means safe characters, we just keep unchanged lambda identity function. But every unsafe chars, we call encode function to make transform to others. Yeah. And we also to pick a bunch of sanitizers from the internet to evaluate the effectiveness and efficiency of our approach. For HTML, for JavaScript, for JSON, XML, CSS. So you can see that. So for the unsafe part, we deliberately to remove some of them. We find that when we remove them, they are unsafe. So this means that when we write or use the sanitizer, we must be careful to not miss some sanitizer, to not reorder some of the sanitizer to make it safe. But the verification itself is very efficient. All the verification is below the 0.02 second. So it's very efficient verification. Another application is about string solvers, because in a few years ago we developed a string solver. String solver is a branch of SMPT solver only for string series. So that one was also in Isabelle, but it only supports very, very basic operations like equality, like concatenation, like regular constraints. The thing is they're not quite useful for the real world applications, security analysis, because as I said, it needs string transformations, like from one string to another string. So because our transducer now, we have transducer now, so it could be used to model the event. So we use it to model the SMT-lib supported operations for replacement. I just show an example. This is the example to replace the digits with the constant string number. So from the state Q0 prime to Q0 prime 1 prime is just to accept, okay, say all the digitals. And after that, it will replace it with number. So this is a basic idea. For the replace all, we model the replace all operations. So replace all has two parts: pattern. First one to match the something don't match the pattern, and now they match the pattern. Then we use it with the replacement. Yeah, this is replace all idea. We also compare with some state-of-art assembly solver like Ostrich and CVC5. To our big surprise, actually, our solvers could beat the other two in most of the benchmark. Is expect the second line, the replace string CVC4-5 after performs Earth and perform better than Earth. But it also shows that our service string solver could be used to really nullify some of the real world applications. So finally, I just want to express the expressiveness comparison with transducer. This is something talked about in SMT-lib community, is that whether SMT-lib should support transducer directly instead of use replacement. I give an example is replace each character in A to Z with its corresponding ASCII code. In transducer, it's just very simple, one state, two transitions. But if you use replacement, it will need 26 constraints. It's very long and ugly and give a lot of burden to the string solvers. It's not good. But in transducer, it will be very easy to solve. So, but now I haven't yet support. But if it support the solver could easily to support the transducer as well. So finally, is some side dishes. Not only the transducer, we have now have a complete, pretty big library for the FA and the NFA and the transducers in symbolic setting. If you are interested, you can try some of them. And finally, the contribution is we formalize first SFT, and we use the refinement approach to improve its efficiency, flexibility, and tension. And yeah, we also applied to two applications. Yeah. Yeah, that's it. Thank you.
We can take a quick question, but if the next speaker can also set up the...
Thanks for that talk.
Thank you.
Do you have any intuition what the other SMT solvers are doing wrong and what you are doing right? Is it just the fact that you're using the transducer representation? And
yeah. I mean, that's a good question. Because when I got the experimental result, I was surprised, very surprising to me. Because a deep comparison with them is hard to say, but I can just say some potential reasons. Firstly, the other two solvers, they try to cover all the features of the strings and try to cover the complete set. But ours, when we encounter something, we find that we can't solve it, we will just give it up. Another reason is like for Ostrich developed in Java, Scala or Java, it was JVM, so mostly they will run slower than other languages. For CVC5, you know, it was a different way, not different logarithm. They use word equation theory to do the solving. I'm not quite sure because I didn't find some benchmarks uploaded by the CVC5 in SMT-lib. So if they have, probably we can compare them. But now we can only find these benchmarks they can't solve. But probably the word equation theory problem, yeah, that could be. Mm-hmm.
All right, let's thank the speaker again. Our next speaker is David, telling us about enhancing symbolic execution with machine-checked safety proofs. David, the floor is yours.
Hi, so this talk will be about generating safety proofs, and this is a joint work with Shahar Itzhaki. So I'll start with some background about symbolic execution. So this is a program analysis technique where we explore the paths of the program. And it has many applications, for example, test generation, bug finding, and verification. At the high level, it works as follows. We run the program with a symbolic input instead of a concrete input. And when we have a branch that depends on a symbolic value, and both sides of the branch are feasible, then we fork the current state. And then we continue to explore each of the new states. So let's see how it works with this example. We start with the initial state. Then we have this branch. So at this point, we don't have any constraints for x, which is assumed to be symbolic. So we fork the current state. Then when we follow the L side of the branch, we finish to run the program. And on the other side, we enter the block and execute this update of y. And then we reach the second branch condition. And this time, we do have some constraints over x. And so in this case, only one of the branch sides is feasible. And when we follow the L side, we also finish to export the program. So in this case, we explore two paths, and you can see that in each so in each path you have some you accumulate some path constraints, which will be used later. So in general, when we analyze a program with symbolic execution and we examine the results of the analysis, then we have several cases. So if the analysis found some bugs, then we can take the relevant the path constraints of the relevant buggy paths, use the SMT solver to obtain a concrete input, and then we can run natively the program to see and we can see if there is a crash or not. Otherwise, if the analysis didn't find any bugs, then we have basically two cases. In the first case, we have a timeout, which means that the analysis tool didn't finish to explore all the path, and then we don't know if the program is safe or not. And in the other case, we have an exhaustive analysis, which means that the tool did finish to expose the path. But can we really claim in this case that the program is safe? So in general, the answer is no, due to several reasons. So first, the analysis tool can perform different forms of under-approximation, for example, state pruning and concretization. And of course, the implementation of the tool itself may contain bugs. So to convince you that this last concern is actually real, so let's have a look at this example. So we have two symbolic points, and then we compute the gradient between these 2 points. And now let's see what happens when we analyze it with the CLI, which is a state-of-the-art symbolic execution tool. So again, we start from the initial state, then we fork. And when we execute this division instruction, CLI checks for a potential fork because it checks if the divisor may be equal to 0 or not. And after this, the analysis is done. So what you can see is that we explored two paths and we didn't find any bugs. But is this program actually safe? So of course the answer is no, because sign division can fail in two cases. So the first one is when you divide by 0, and there is another case of overflow where you take the minimum sign value divided by -1. And this results in a number which is outside the range of signed int, and it actually results in a crash similarly to the first case. But it turned out that in CLI, the handling of sign division was incorrect, and the result it missed this path. So the bottom line is that if you want to have formal safety guarantees, you can't really rely on an unverified analysis tool. So what can we still do? So one way is to try to verify the implementation of the analysis tool. But this is hard. For example, CLI is written in C++. It has complex dependencies such as the standard library, LLVM, and so on. So our solution is based on the idea of translation validation. So when we analyze a program, we additionally produce a safety proof, And this proof is specific to the programs that we analyze. So now the scheme looks like this. When we have an exhaustive analysis, which means that we finish to explore the path and there are no bugs, then we additionally produce a safety proof. In this work, the proof is written in ROC. And then we can take the proof and validate it using the type checker of ROC. So in this case, the TCB will contain, of course, it will contain ROC and also the SMT solver. So now let's see what is the structure of the proof. So at the high level, we have two main sections. So we have the predefined section, which contains the semantics and the theory that will help us to prove safety. And the second section is auto-generated by the analysis tool, and it contains definitions and lemmas which are specific to the programs that we analyze. So let's start with the first one. So we want to define concrete and symbolic semantics. In this work, we deal with LLVM. So in the concrete domain, we have a concrete state, have a program location, have a store which maps variables to LLVM values, which can be integers or the special values undef and poison. And then we have a stack. In the symbolic domain, we define a state in a similar way, but instead of LLVM values, we have SMT expressions, and we also have a phi, which is the path constraints of the symbolic state. Here you can see several examples for rules for the semantics in both domains. So above you can see the rule for the sign instruction, which is quite similar in both cases. In the branch rule, so when we deal with concrete semantics, we can derive only one state depending on the evaluation of the branch condition E. And in the symbolic semantics, we always derive two states, and in each state we update the path constraints with the appropriate condition. And now we would like to relate somehow the concrete and symbolic semantics. So first we want to relate the states. So we say that a symbolic state over-approximates a concrete state if the concrete state can be obtained by evaluating an SMT model on the components of the symbolic state, while this model has to satisfy the path constraints. And then we have this theorem which connects between the semantics. So if we can reach a concrete state C from the initial state of the program, and in this sequence of steps we don't have any states that contain a Poisson value, then there must exist a symbolic state S, which is reachable from the initial symbolic state of the program, and S over-approximates C. So this theorem will help us later in another theorem which talks about program safety. And going back to our example, so we saw that we explored these two paths. So this structure is called the execution tree of the program, and basically it depicts the paths that we explored during the analysis. And now we want to define the notion of safety for trees. So we're in the context where we have a subtree where the root is S, and we say that this subtree is safe if these two conditions hold. The first, S must not be an error state. And then if we can derive S prime from S based on the symbolic semantics, then either S prime is infeasible, which means that the path constraints of S prime are unsat, or there is a child S prime prime of S in the tree, which is equivalent to S prime, and the subtree of this S prime prime should be also a safe. And based on this definition, we have this theorem, which is basically if the execution tree of the initial state of the program is safe, then the program is safe with respect to the concrete semantics. So this helps us to make a step toward showing program safety, but we still need somehow to compute this tree and to prove that it is safe. So this leads to the second section in the proof, which is done by the analysis tool. So let's see what we have here. So we have the definition of the program, the symbolic states that we explored. Then we define the nodes of the execution tree, and here we have here we prove that this tree is safe, and we do it in a bottom-up manner, which means that we first show that the leaves are safe, then we show that their ancestors are safe, and so on until we get to the root of the tree. Once we prove that the whole tree is safe, we can apply the previous theorem and conclude that the program is safe, again with respect to the concrete semantics. So the most challenging part here is showing that these subtrees are safe. So I will show you several examples to explain how it works. So suppose that we now execute this instruction. So we are in state S4 given here. And we want to show that the subtree of S4 is safe. So we look at the derived state, and now we have either to show that this state is infeasible or find the matching state in the tree. So in this case, we go for the second option, and so we simply take the successor of S4 in the tree, which is given here below, and now we need to show that these two states are equivalent. So they are slightly different because of these expressions. So the analysis tools uses various SMT optimizations. So this expression is more optimized than the one given by the formal symbolic semantics. But we still see that they're equivalent. And in general, what we do to discharge these kind of goals is we formalize in ROC the SMT optimizations that are used in the tool. And we prove a lemma that shows that these optimizations preserve equivalence for SMT expressions, and then we just apply this lemma to handle these kind of goals. Another example, so let's see what happens when we execute this branch instruction. So we are in state S5, and it has two derived symbolic states. So let's start with the first one. So here you can see that the path constraints are unsat, so this state is infeasible. And for the second state, so we want to find the matching state in the tree, which will be S7, given here. And now we need to show equivalence between these two states. This time we have a difference in the path constraints. So to handle this, again, in an automatic way, you have this lemma, which basically says that if the conjunction of PC and the negation of E is unsat, then we can remove E from the path constraint. So this helps us to discharge this goal. Let's talk a bit about proof compilation optimization. So as we know, RAW can be very slow when the proof is large. So to handle this, we use several optimizations. First, we try to reuse terms. For example, if there is an SMT expression that is used in multiple symbolic states, and we define this ROC term only once, and then only use the variable in different locations. And another optimization aims to minimize proof objects. And I will spend a few slides about this one. So let's go back to the example where we have, so this was state S4, and we wanted to show that the subtree of S4 is safe. So what we did, we looked at the derived symbolic state, we looked at the state from the tree, the one that is computed by the symbolic analysis tool, and we had to show that they are equivalent. So let's try to see roughly how it looks in ROC. So we have this lemma. The goal of the lemma is to show that the subtree of S4 is safe. So this is just a reminder for what safe means for in the context of trees. So safe is a relation, we apply its constructor, and then we need to show that each of these 2 points hold. So this block in the proof corresponds to this part in the definition. We want to show that this is not an error state, and then this block tries to prove this one, and we want to show this option, which means that we need to provide this child S prime prime. So the bottom line here is that the resulting proof is very long, and it uses expensive tactics like inversion and subs and so on. So if we do it for every subtree, this is going to be very expensive, so we want something better. So, so this proof that we showed before for this specific proof for the subtree of S4, we can actually generalize it to this lemma. And this lemma is going to handle any subtree where we have an assign instruction. So it can guarantee safety of the corresponding subtree. And once you fulfill these conditions, and the main thing here is that you need to show that the symbolic store, which is derived by the symbolic semantics, is equivalent to this sigma opt, which is the symbolic store which comes from the analysis tool. So this is the main part here. And once we have this lemma, we can make the previous proof much shorter. And so the proof is smaller, and we use simple tactics like apply and reflexivity. And the expensive tactics remain now in the proof of the generic lemma, but of course we prove it only once, and we reuse it for every subtree where we have an assign instruction. And the same thing we do for other types of instructions like branch, call, ret, and so on. So a bit about the implementation. So we developed a formattation in ROC, roughly 20k lines. And in this work, we model a subset of LLVM with integers. So what it contains, so we have the semantics, concrete and symbolic semantics, and have also some theory, some of which we mentioned before. And then we extended CLI to generate proofs based on this formalization. So in the evaluation, we used several benchmarks with integers, so some examples for SVComp and some other examples. And we focus on these metrics, so we want to see the overhead of proof generation, the proof time, and the proof size. So here you can see the results. So these two columns shows analysis time with baseline CLI and with our approach. And then you can see the proof time, which is basically the compilation time with the ROC, and the proof size. And so we have different modes. This column is the most optimized mode, and this one uses none of the optimizations. So you can see that there is a big difference in both proof size and proof time. And actually, in some of the cases, we even ran out of memory when we try to compile the proof. So these optimizations are essential to make things work. So to summarize, we proposed an approach for generating safety proof using symbolic execution, and we applied it for LLVM and the CLI. For future work, we plan to support more advanced features of LLVM like memory, etc. And also believe that this approach can be applied to other symbolic execution tools and to other types of program analysis. So that's it. Thank you.
Let's take a few questions while the next speaker sets up.
Thank you for the talk. So I was just wondering about trusted base for this. So what do I have to trust when the V file gets verified, right?
Yeah.
I probably have to trust that my C program was translated to LLVM, but then I have to trust your LLVM semantics. Maybe you want something else.
Yeah, so we need to trust. So we have ROC, have our specification of the concrete semantics. You don't really care about symbolic semantics, only about the concrete. And we also need to rely on the SMT solver. This can be addressed by tools like CockSMT probably, but we didn't handle it in this work. And also, yeah, you're right about the translation from like the LLVM model to the embedding in ROC as well. Yeah. Yes.
You mentioned this bug in CLI,
yes.
I think, that had to do with division.
Yes.
Did you find other bugs or some, yeah? symbolic
For this
executor?
work, no, but we found some bugs related to memory. Yeah.
I think we should stop questions here and move on to the next talk. Maybe we can take other questions offline. All right. And so the next talk is going to be the one by Ludovic on layers of confluence for actors.
Thank you. Seems good. Yeah, so I'm Osman, and I'm... yes, this is true. I'm the one that's underlined. And this is joint work with Ludovic, my supervisor Einar, Violet in the Western Norwegian University of Applied Sciences, and Yannick from India, who's somewhere around. Yeah, so I'm going to start with a sort of motivating example that's, at least on the surface, very simple. So we are going to be interested in parallel or concurrent systems in which there is some sort of non-trivial non-determinism. And as our simplest example, we'll consider this sort of system. And here we have three sort of client nodes that delegate some work to some workers, and then those workers further delegate to some compute nodes that do the actual work. And so far, there are very few details. We're imagining this in a sort of actor-like setting. But what I want you to notice immediately is that there's sort of two layers here of race conditions, where in principle, the result could depend on like which order the clients delegate their work, and furthermore, which order those workers delegate compute work to these other nodes. And so in general, even for simple cases like this, properties of systems like these are quite difficult to prove. There are very many possible interleavings, and we want to prove something for all possible execution paths. And especially here, we have this sort of layered race conditions where the possible execution paths of compute F and compute G might depend on the order at which work arrives to worker 1, for example. And yeah, it could be much more complicated than this as well. And so, having done that motivating example, we're now going to take us a step back and look a bit at how we're going to treat this sort of problem, and then I'll present a solution that we have formalized in Rock before we get back to the motivating example. So for our purposes, we're interested in showing that such a system is deterministic, in the sense that no matter the interleaving of all of these calls, the result you get at the end will be the same. And we're going to say that that is equivalent to saying that the induced transition system here is confluent. And then, I mean, the literature has tons of different sort of confluence properties that are all applicable in different scenarios. But in particular, we want to look at strong confluence, which is this case where when the system diverges, you can take one step on one side of the relation and an arbitrary number of steps on the other. And this is sufficient to prove confluence. But that's not enough in our case. It's too weak because we want to be able to take steps on both sides, but that's not allowed. And on the other hand, if you take arbitrary number of steps on both sides, this is too strong. And it doesn't actually imply the confluence that we want. So we want to find something magical here in the middle, these question marks. And what we found is actually not our invention. It's due to De Bruyne in an unpublished old note that was then sort of rediscovered and modernized by Andreas and Klopp in 2013. And it's their words, they call it a truly amazing proof. So let's look at that one. Here comes De Bruyne to rescue us from our race conditions. And first, we need some additional structure. So we're going to introduce a notion of indexed transition systems. And here in our example, as was maybe evident by the way I laid it out in the first place, we're going to index it by these layers with the compute nodes at the bottom, the workers in the middle, and the clients at the top. But in general, an indexed transition system needs some totally ordered indexing set. And then we have a family of transition relations indexed by that set. And so not necessarily for each, but each transition relation sort of lives at one level of this indexing set, and some are above others, or greater than others. And in particular, we care often about the union of all of these to recover our original transition relation. And we're just going to denote that by a simple arrow, and these arrows with the subscript of the level will be the indexed versions. And in our example, that means the calls coming from the client will be at the top level, and the returns coming back to the client, or the returns will be at the worker level, and so on. We'll get to the details later. But the thing that this allows us to do is to do induction on these levels, because now we have some structure, we can exploit that structure, and we can say, well, maybe it's strongly confluent at the bottom, but as we move up, we can have slightly weaker assumptions because we can use the confluence of the layers below. And this leads De Bruijn to what he calls the weak diamond property, where it turns out that actually it suffices to have these two shapes. And so this one here on the right, this D1, or my right, your left, says that if you have two diverging transitions on the same level, then you can close one end of it by taking any number of steps on this level and levels below. And along the bottom, you take only steps at the lower level, and then at most one step at this level, so this alpha, and then any number of steps at strictly lower levels again. And note that in the 0th case, so at the bottom level, this is the strong confluence that we said was too strong, or sorry, too weak. But when alpha increases, we get higher up in our hierarchy, this weakens, and we have a slightly weaker condition. Note also that this D2 requires that beta is strictly smaller than alpha, and so has no instances on the 0th layer. But otherwise is quite similar, except now this one on the right has to be strictly below alpha. Yeah, and then De Bruijn's amazing proof shows that if this is the case, that for all such diverging peaks, we can close them with one of these two, then the union, the entire system, is confluent. Huzzah. And his truly amazing proof looks like this in the paper, which is perhaps why it's unpublished. But it works by this sort of diagram pasting, where you use these properties to construct diagrams and glue them together along all of the correct edges, and magically at the end you have the exact diagram you wanted. In Andreas and Klopp's modern account, which we mostly work based on, it looks more like this. But even here you can tell, here we're making one large rectangle here. But it requires all of these smaller ones, and an induction hypothesis, and this Church-Wasser property, and it's still quite an intricate construction. So I will not go into too many details of the proof itself. It is available through our paper and on, I believe, a GitLab. But the general idea looks something like this. We assume these two, D1 and D2, and then we use them to construct several other shapes that at the very end we put together to create this CR, which is like a Church-Wasser or an equivalent to confluence at all levels below the one we're currently, or yes, at all levels strictly below the one we're currently at. And so by induction, when we build this all the way up, we have confluence. But instead of all the details, I'll just discuss some differences in the rock versus the paper proof. You may have noticed the red pieces in the previous slide, these opts. So we found it useful to introduce an optional step where the original proof says you always take a step at this level. We say you take at most one. And this is mostly because it's convenient and it allows us to do some things where it's like, well, these corners are actually the same. We don't need to take any steps. We just close it immediately. And now we don't have to take a step. And this implies the original theorem, which we also show, but it does lead to some complications in the proof. For example, this lemma from Andreas and Klopp in there, and De Bruijn's work, you only need this 5th diamond, and it directly implies the 6th one at the same level, whereas we actually also need this confluence assumption. But this turns out to be fine, because when you're doing the induction, that confluence assumption is exactly the induction hypothesis that we have, and so we're still able to use it, and the proof still goes through. It also helped us find some minor bugs and clarify some case distinctions. The clearest example is this one here, which the right-hand side, or your left-hand side of this inequality is not equal to the your right-hand side. In particular, when this middle step doesn't happen. And so there were some sort of like minor bugs like this that had to be ironed out, but it still goes through. Also, the original uses some just proof by contradiction at the lowest levels, where we instead build the induction directly. And this ends up being about 1,500 lines of slightly tedious rock proofs, where you're taking all these rectangles, you're decomposing them into their parts, you're making some small changes, and you're putting them back together in just the right way. Okay, so now that we have that, let's get back to our motivating example. So I'll go over this in sort of a high level, but when we have a program that induces a transition system over our configuration of nodes and their work. And so, for example, in this one, you can see our original setup, but restricted to only 2 clients. They take a call step, and we label this step, which will be useful later. And this call step puts client 1 into a waiting state, and then puts a method in the worker's queue. And then the worker can pop that, and it can start working on things and so on. Then we add this indexing. We can say, okay, well, these compute nodes are at layer 0. These workers are at layer 1, and the clients are at layer 2. And in particular, also this call step is at level 2. And this sort of the worker just doing its thing is at level 1, and so on. And this is where we like to have the labels on the steps, because then we can look at the step directly and say, this is a step. This is a call step performed by client 1, which is at layer 2. So this is a step at layer 2. And this is very nice. It reduces our confluence question to just constructing these D1 and D2 shapes for all the critical pairs. And there turns out to be one case of this that is the difficult one. Somewhat unsurprisingly, it's the call case, where the divergence is that a call was made by 2 different clients, or indeed 2 different workers, but 2 different nodes, and they reach their destination in the opposite order. And so we need to close this one. This is D1 at level 2, and so it needs to be closed by some steps that are strictly below 2, at most 1 step at this level, so more steps that are strictly below 2. So let's do that. And the first thing we're going to do is simply to ignore that first any number of steps and take the 1 extra, the maximum 1 step at level 2. It's the other call. And now we're in the state where we have our both of our methods in the queue, but they're in the opposite order in these 2 corners. Then we're going to compute those, both of them. And in this case, we can say the queue looks empty, so this is fine. But in general, we might have an arbitrary amount of work already in the queue. And so we first need to do all of the work that we already have in the queue, which might use even lower layers in the system. And so this is also a bit of work. But once we've flushed the queue, we can now compute first one method and then the other. And along this edge, we will do the same, but in the opposite order. And so now, once we've returned the results, we have these 2 states where in one case, the workers computed M1 and then M2. And in the other one, they computed, well, in this case, work 1 and work 2. Work 2 and work 1, so in the opposite order. And we need to show that actually the result that they receive is the same. And so here, we need some assumptions about the purity of methods. And what we use is a sort of not quite purity, but the nodes have their own their own local state, and your method has to terminate, and it is not allowed to mess with that local state. Or rather, it can mess with it while it's running, but then it has to restore it at the end. So we have to make some purity assumptions on all of the methods in the system for this to hold. All right. And so now, hooray, we wanted to prove confluence of a system. We reduced that by the Browns proof to this nice, or slightly nicer, weak diamond property. And then we reduced the weak diamond property to some purity assumptions of the methods and the fact that the call graph has this structure that we can exploit. But in practice, I mean, we have our actual program here, and we say, okay, well, this doesn't have a call graph. So we need to do a little bit of static analysis to estimate or to approximate that call graph. We also do this directly in Rock by for each node, we overestimate sort of the number of possible, or the set of possible nodes it can make a call to based on its available methods. And we say, okay, well, if that fits our layering, then we're good. And in this very simple case, it does. So we can also get this one to fully go through. And there we have it, right? Our little example is confluent. But this one in itself is not that interesting. We want to generalize a little bit. And in practice, what we do is the general case, and this is a special case. But in general, we define this for a sort of toy actor language that we call lambda act, that has sort of calls and returns, and the usual sort of imperative local language. And we identify two classes of systems based on their call graphs. The simplest one is this here on top, where we say, okay, there's just a single server and one layer of clients that are all making calls to the server. And the other is this sort of this layered case where we say there's a bottom level and there's a distinguished top level and then an arbitrary but fixed number between there. And each node is only allowed to call nodes that are below it in this structure. And this is, I mean, this is similar to what we've seen in the motivating example, which might tip some people off. So the motivating example is indeed a special case of this one with n equals 3, n equals 2, we're zero indexing, which is what we actually show in practice. We use the static analysis to show that it holds, it fits into this pattern, and then we can apply our general theorem. And this, it's actually quite a bit of work. This simpler case is about 1,000 lines of code. This one is almost 4,000. And again, it's this sort of taking apart transition relations and putting them back together in the right way that turns out to be quite tricky. And as an overview, the general case of the closing of the pair we saw earlier looks like this. We make the two calls. We make the other call so that we now have the methods in the queue, but in the opposite order. Then we flush, so we empty our queue and also everyone below us in the system, which we can do by an induction. And then we compute the two methods. And here we have to do some work in this lemma called commute requests to show that the result at the end will be the same. And all of these dotted lines here, these are the sort of correspondence lemmas that we have to prove that turn out to be most of the work. All right, so the conclusion here is that even in the obvious cases, we look at that and we say, oh, well, that's confluent. Confluence can be really tricky to prove in general. So we propose this weak diamond property as a possible solution. And to show that, we use it in these two classes of call graphs. And all of this is fully mechanized in Rock. And the formalization reveals some subtle details of the original proof, where there were small mistakes or omissions, as usual, but they turn out to work. In the future, So our language is currently very, very simple. There are some obvious directions to go. The first is futures, which most of these actor systems have. This turns out to not be a big problem. The other is dynamic objects, so you can create and destroy these nodes as you go along. This, as far as we can tell, is a much bigger problem. It would also be interesting to use this sort of proof setup in different applications. Maybe they aren't necessarily these actor systems. And finally, as I said, some of these proofs are quite difficult and tedious, and it would be interesting to look at some better tooling for this sort of diagram pasting and proofs that sort of are visually very nice on paper, but turn out to be quite a nightmare in the proof assistant. And then finally, Andreas and Klopp generalized their proof to partial orders instead of total orders. We did not do this because we don't really see a use case, but if anyone has like a obvious great use case for partial orders on the rewriting systems, that would be great. And thank you.
As before, let's have the next speaker set up while we take a few questions.
Thanks for the talk. What if my graph does not fit the two structures that you identified, in particular for graphs with cycles, full graphs with cycles? There's probably no hope for using this technique, right?
No, then you would have to, I mean, I can't guarantee you that it won't work. You might be able to find some very clever encoding that will still allow you to use De Bruyn's proof if you can close all of these rectangles. But that is sort of a missing step. Or rather, there's two steps. There is applying the proof, and then there is some setup to make sure that the proof can be applied in a nice way. And that part will require some ingenuity, I'm afraid.
Great. If you don't have other questions, then we'll move to the next talk. Thank you very much.
Thank you.
And the last talk of this session is by Martina on towards composable proofs of cache coherence protocols.
So good afternoon, everyone. I'm Martina Camaioni, and this is a joint work with Jan, Chin, and Thomas, and we are part of the same laboratory at EPFL. So the main research question behind this work was the following. Can we find a simple and more trackable way to prove correctness of complex protocols using interactive theorem provers? As probably some of you know, when we use interactive theorem provers as Leancock or others, these are really useful tools to prove complex protocols. Why? Because they allowed us, for example, to reason with parametric setting on the abundant state. However, they usually required a lot of human interaction, and this leads to proofs that are really long, takes a lot of time to be complete, and not so much reusable. So for the subject of this project, we decided to focus on a complex hardware problems, cache coherence protocols. Cache coherence protocols are already proved in literature using interactive theorem provers. However, these proofs leads to really long proofs that can take 2 years to be complete. Why? One of the main challenges behind this is the invariant discovery. So usually the user have to come up with hundreds of properties to describe cache coherence protocols. So in this talk, we propose our solution that is like, we discovered that leveraging the invert structure of cache coherence protocols, in particular the local structure, we are able to discover an invariant with much less properties, so it's much more easy to discover. And moreover, we also discovered that cache coherence protocol have like, we can decompose it, and this leads to proofs that are much more reusable. So first of all, why we need cache coherence protocols? So in general, like we know that access the main memory is an expensive operation, so we would like that our CPU perform the load store operation not directly to the main memory, but to a local memory that we call cache. However, like we need some coordination between different cache, and this is usually done by the parents, because we want to ensure that the memory is coherent. What it means, like intuitively, this means that we want that these local caches and the memory like behave like as central memories. So How the cache look like? The cache is usually composed of different cache lines. Each cache line have an address, a value, and a state. For the cache coherence protocols that I will present you today, this is MSI because the state can be M, it's a modified state. So in this case, we can perform read and write operation directly on the cache. Then we have the shared state. In this case, we can just perform read operation on the cache, but for the write operation, we have to go back to the main memory. And then we have the invalid state. In this case, we have to go to the main memory to do any read and store operation. So let's analyze, for example, an example to just give you an intuition of how this works. In this case, we have just one cache line, so we don't care about the address, and we have the green cache that is in a modified state with the value 2, and the blue cache that is in an invalid state, and we don't care about the value in this case. So the blue cache wants to perform a load operation. We cannot do it straight away, so the cache have to request the permission to upgrade to the S state to the parents. The parents cannot respond immediately to the blue cache because it doesn't know what is the last value written, because the green cache, you have the modified state, so it can update its value. So what it does, it asks to the green cache to invalidate itself. So the green cache does this and say, okay, the last value that I written in this case was the value 2. The parents can finally now update the memory with the last value written and responds to the blue cache and say, okay, now you have the permission to go to the S state with the value 2. And finally, we are able to respond to our load request. So the question now is how do we define the correctness properties of a cache coherence protocols? As a bit anticipated you before, we wanted the protocols to behave like a centralized memory. So in a centralized memory, we don't have caches, and the load and store operation are performed directly to the main memory. So one key property of a centralized memory is that it ensures coherence. What does it mean? It means that the load operation returns always the last value written. So we would like that also our cache coherence protocols, and this is why it's called coherence, ensure coherence properties. So in order to do that, some configuration must be unreachable in a cache coherence protocols. Why? Because for example, let's analyze this configuration in which we have the green cache in M in a modified state and the blue cache in a shared state. Now the green cache wants to perform a store operation. It can because it's in a modified state. So we have that the green cache store, for example, the value 3. Now the blue cache, you want to perform a load operation, and it can because it's in a shared state, but he's able to read just the value 2, that is not the last value written in this case. So we want that he's be able to read the value 3. So how do we prove that SM are unreachable configurations? In order to prove this, usually you need a long and difficult invariant. Why? For two main reasons. So first of all, because cache coherence protocols are complex protocols. What I didn't tell you before is that the parents is not just a coordination between different caches, but he also have its own state. And it keeps track on what is the beliefs that you have for the state of the other cache. And this is difficult because the cache coherence protocol have a distributed nature, right? So it doesn't know with the certainty which state the cache are. It just have to guess. For example, in this case, if we have the green cache that the parent think that is in M, but this green cache wants to invalidate itself and you go to I, the parents not yet, doesn't yet analyze the signal, is not update, it cannot update its beliefs. Another problem is that when we want to usually define global invariants, like the one that we care about, that means that two caches cannot be in MS simultaneously, usually we need to state global properties. So for example, we can say, okay, if we don't want that two caches are in MS simultaneously, we don't want that the parents send an OK to go to M and an OK to go to S simultaneously to two different caches, right? And this is a global properties because it requires to see the system in its globality. So actually, these properties cannot prove in isolation, and usually required a loop, and this is like the user work, to like say, okay, to prove these properties that we care about, we need to add new properties, and so on and so forth, until our invariant become an inductive invariance. So global invariance consists of many unstructured properties that must be manually identified by the user. The key contribution of this project is realize that actually we don't need any global invariance. So in order to prove the correctness of cache coherence protocols, we just like need to focus our attention on the subunit cache parents. Intuitively, why this is the case? Because even if the parents believe that it's not update all the time, this is enough to characterize our system. So only focus on the parents' beliefs, a single cache state, and signal between a parents and a single cache. This is enough to prove correctness. And this is particularly interesting if you think about that in general we have a parametric setting. So I present you a system with only 2 caches, but we can have like n number of caches, right? So instead of like write global invariance that they talk about all the different channels from different caches, it's just sufficient to like focus our attention on this like subunit cache parents. Okay, so now the question is how do we write the correct local invariance? And we actually discovered that this local invariance is much more structured than what we think, because we discovered that to write it, the local invariance is sufficient to ensure 5 different classes of properties. So the first one is what we call relation between signal, that state that some signal cannot simultaneously exist in the cache parents and in the parents cache channel. So in the case, in this example, for example, we cannot have a response M from the parents to the cache and simultaneously a response I in the other channel from the cache to the parents. Then we have what we call signal uniqueness, that say all the response signals should be unique. So we cannot have, for example, 2 response M. Then we have another, the third class that is over-approximation. So I anticipate you a bit before, and I told you that the parents can, is not only update the beliefs that they have on the cache, but we always have to ensure that the parents' belief over-approximate the real cache state. So in this case, if the cache is in M, the parents should think that the cache is in M. You cannot think that the cache is in an invalid state, for example, or in a shared state. So then we have the fourth classes, that is conflict configuration, that say that the parents believe that at most 1 cache can be in M. And finally, we have like the last one, the signal to state, that relates like response signal, solely response signal, to the cache state and to the parent's case state. In this case, like we have that if we have a response M from the parents to the cache should be in I, and the parents should think that the cache is in M. Okay, so cool. So if we apply these 5 different classes to our MSI, we realize that we just need 2 properties of the type relation between signal, 4 of the signal uniqueness, 3 over approximation, 2 conflict configuration, and 4 signal to state. So with a total of only 15 properties, we are able to prove the correctness of our MSI protocols, compared to like 100 of properties of the state of the art. What is significantly cool is that a local invariance of only 15 properties, we are able to prove global correctness property as the one that like we care about, that like 2 cache cannot be in MS simultaneously. So ultimately, with a local invariance, we prove it in Lean for MSI that is coherence, that is like ensure the correctness. Okay, so we discovered that locality significantly reduced the size of invariance necessary to prove correctness. Moreover, we discovered that we can apply this taxonomy not only for MSI protocol, but also for SI and MI subprotocol. So like in SI protocol, the state can be only S and I, and we can perform only load operation. In the MI subprotocol, instead, the state, we can perform both load and store, but the state can be only M or I. We don't have a shared state. So why do we care to prove also the correctness of these other subprotocols? Because like this is interesting if we want to prove a slightly different version of MSI protocols. So actually what we did is not prove like straightforward that our MSI protocols refine a central memory, as is usually done. But we first discovered that we can done this proof. So we can prove that MSI is just a refinement of a combination of two small subprotocols that are SI and MI. And then we prove that SI plus MI refine a central memory. So, so we discovered that actually MSI at each point in time can be described as either MI or SI system, in which if you think about the MI and the SI system, they have in common the high state, right? When all the caches are in I. And in this case, we can switch from like one word, one protocols to the others. So why is this interesting? Because modularity helps in building reusable proofs. Let's suppose that now we want to prove a slightly different version of MSI that we call MSI prime. Instead of proving that MSI refine a central memory, as usually is done, we have to prove that MSI refine SI plus MI system, and then that MSI plus MI system refine a central memory is already proved, so we don't have to change. And like do these changes much more easier because we go to an intermediate system instead of doing the whole proofs. So our MSI prime, usually it's a realistic implementation. Instead, we design our combination of SI plus MI protocols allows much more of non-determinism behavior. So for example, in SI plus MI protocols, we can request M and request M even without any preconditions, so without any store or load request. So why we do this? Because in this way, then it's trivial, like proof that, for example, our MSI protocol in which we say, okay, we request S if we have a load operation, refine SI plus MI, in which we are able to request S even without any load operation. And the cool thing is that then if we change MSI and we say, okay, let's assume that we want to prove MSI prime, in which for a load we request M instead of S, is still refined to the same SI plus MI system, because in SI plus MI we can still like request M without any preconditions. So we can reusable proof without changing our composition of SI plus MI system because we are allowed much more non-determinism there. So to summarize, during this project, we discovered that locality leads to smaller invariants, that we also able to classify this smaller invariant using the taxonomy that provides structure to locality. We also see how modularity enables more trackable proofs and non-determinism allows building reusable proofs. In the paper, we also extend like this to multi-address MSI protocols. The question now, a cool research question can be, can we apply this concept of locality and modularity also to other protocols, for example? So I'm done. Thank you for your attention.
Thank you very much, and we have time for a few questions.
Thank you. So I'm not as familiar with the verification of protocols, but it seems to me that the thing that you exploit is this notion that the parent really has an accurate over-approximate view of what its children are doing in order to be able to get from the local property to the global property.
Yeah, so they don't have exactly the perfect view, but they have an over-approximation on that, and this is enough to leverage the correctness, exactly.
So was this like a known technique that you're exploiting? Do you think this generalizes nicely to any other kind of graph protocol where some node has some sort of over-approximate view of all the other nodes are doing?
Yeah, like this was not done before, so like we kind of capture like an inherent property of cache coherence protocols. And like, I don't know if can be generalized, but I'm thinking that, for example, for distributed protocols in which maybe sometimes we have a leader that have more information, maybe we can apply something similar. And because having this local invariant is much more an advantage because they are much smaller, because the system is much more smaller, right? So it's easy come up with like 10 properties that describe a smaller system instead of 100 for a full system. So this is an interesting research direction.
So cache protocols are a really nice target because they're tricky and important, but also a super annoying target because the real high-performance cache protocols tend to be much more complicated and also confidential. So talking to people in IBM about what they do, some of the details of that are public, and they have all kinds of states and all kinds of different messages between states, which are tricky to imagine dealing with. So I wonder what, I've not been paying attention to that recently, I don't know what is known and what you can feasibly aim to do sort of in the public literature beyond things like MSI and MESI and whatnot.
So you mean for protocol that like you don't know the implementation, or like you know?
Well, there are a bunch of fancier implementation techniques which are somewhat known, and some of them are described in patents, but you can't find a description of the IBM Power 9 protocol in detail. But it might be that that you can see the ideas in the design of them and know whether this kind of thing would be applicable.
Yeah, maybe if I can have abstract at least like implementation of that, I can try to apply the same ideas. Like,
and I suppose my point is really there is a whole world of much more complicated cache protocols that is annoying to look at, but which one can look at some aspects of.
Now maybe they also have some inherent structure that we can take advantage. So like the most takeaway of this work is that like sometimes instead of go straight forward to the problems and try to come up with invariants, like looking on like what is the inherent structure of the problem, the protocols that we can take advantage in this case was, for example, these locality properties, simplify a lot like the proofs. So maybe there will be like slightly different concept that can still simplify the proofs.
And that would be a happy world.
Yeah.
Do we have other questions? So I have a question. In your refinement, you were refining between MSI and MI plus SI. Do you have an intuition if you added more states to this, right? So MESI or MOE SI or so on. Do you expect that you would have similarly an OI and EI, and then the refinement will work?
Yeah, I didn't prove it, but I expect that if you add a new state, and like you can still come up with this diagram, let's say, so in which you can still say, maybe now you have a new state, O state, and whatever, but it should be still like go to I, so you can come with these sub-protocols. This part of the proofs like are reusable, right? You don't have to prove it again, and you just have to add that like part. So this is also a cool thing of like why decomposition can like lead to reusable proofs.
We have time for one more question. Well, I have one more question. So you are modeling the behavior of these cache coherence protocols, but there's also a lot of work on verified implementation of processors and cache hierarchies now. Can you imagine connecting these? Would there be difficulties in connecting this with actual hardware implementations, assuming you have the right models for the hardware itself?
For a cache coherence protocols?
Yeah, could you verify like an actual circuit that implements this rather than just a model of how this works?
I mean, we can extract like some code that runs and then like, but yeah, like, I don't know, I did only on like abstract implementation, so.
Cool, so it sounds like there's good follow-up work there. All right, well, let's thank the speaker again and every speaker in the session.
Welcome everybody to this session, last session of CPP on separation logic. So in this session we'll have 5 talks, 5 exciting talks, and the first one will be given by Leila El-Beheri from MPI, so please take it up.
Thanks for the introduction. So, hi everyone. In this talk, I'll talk about a recipe for modularly verifying generic tree traversals. So, tree data structures can be found everywhere in computer systems. In compilers, they can be found as abstract syntax trees, in web browser engines as document object models, and in hypervisors as page tables, just to name a few applications. And in these applications, tree traversals are the predominant means for accessing and manipulating data. So the correctness of the system crucially relies on the correctness of the traversal implementation. So our goal is to apply program verification techniques to verify the correctness of those traversals. And in system applications, tree traversals usually have 2 features. They are higher order, and I'll explain what this means in a moment, and they allow for effectful operations. And this effect can take shape in one of 2 forms, either by modifying the content of a node or by changing the structure of entire subtrees. So let me illustrate these 2 aspects through an example. I have in this slide an implementation of a pre-ordered traversal over pointer-based binary trees in C. The traversal checks whether the tree is a leaf or not, and if it's not a leaf, it applies an operation on the root of the tree, and then it recursively traverses the left and then the right subtree. And this operation that the traversal applies on the tree nodes, which I call F here, is given to the traversal as input. And this is what I mean by higher order. And let's look at the client of this traversal. So here I have a client which instantiates the traversal with the tree incur F operation, which just increments the values stored in the nodes of the tree. Clearly, this operation is effectful because it mutates the program state. And this is what I mean by traversals accepting operations that are effectful. In this example, the effect is more localized, where a single node content is mutated, but especially in computer systems, the effect can be more global in the shape of mutating the structure of entire subtrees and not just changing the value inside a single node. So currently, the canonical way for specifying traversals that are higher order and effectful is by viewing them as iterators, where basically the specification abstracts the tree into a sequence, and then it describes that an operation has been applied to elements in this sequence. And because this operation itself is generic, the specification can be parameterized over a predicate that acts as an invariant over the sequence of elements that have been enumerated so far. And lastly, because this operation can also be effectful, like I've just shown, we can express this specification in separation logic to simplify reasoning about state. Now, the problem with this iterator view is that it doesn't work well for traversals where the per node operation depends on or modifies the structure of entire subtrees and not just a single node. So instead, we've come up with a new recipe for specifying and verifying such traversals that mitigates this limitation. This recipe is general, so it can be applied to a number of different implementations. It's modular, so it allows reusing parts of the verification effort when verifying traversals that share common components. And it's automatable, because the point is to apply this recipe inside an automated program verifier. And these tools are known to be widely incomplete. So we try to address this incompleteness by identifying strategies or heuristics that improve automation. So I'm not going to focus on automation in this talk. There's more details about these heuristics in the paper. But I'd like to talk about why it's important that the recipe is general and modular. So in principle, tree traversals in computer systems are actually quite straightforward. They traverse the tree in a depth-first order, applying an operation on a subset of nodes along the traversal. But in practice, there's tons of different ways in which the traversal can be implemented. The order of the traversal can be a pre-order, a post-order, an in-order traversal, or even it could be specified by the client of the traversal. The tree itself can be implemented using arrays or using recursive data structures and pointers. And then in some system applications, like hypervisors for example, the tree can have a fixed arity, but in other applications, it could also have a variadic arity. And then there could be also additional features in the traversal implementation. So the point is we don't want to special case any of those implementations, and instead we want our recipe to apply to all these implementations. And additionally, if we use the recipe to verify, for example, a pre-order implementation, we don't want to redo all the steps in the recipe to verify a slightly different implementation. So ideally, there should be some reuse across the recipe steps. So now I'll explain how the recipe works. And to do that, I'll show you how to apply the recipe step by step on the example that I've shown earlier of a pre-order traversal. So the first step is actually quite standard when we're verifying programs that are written in low-level languages like C, where we usually have a data structure with a complex layout and physical memory, which would be difficult to reason about. So instead, we define a nice mathematical abstraction of this data structure and establish a relation between the actual implementation of the data structure and the mathematical model. And then we can use this nicer mathematical model to specify and prove our specification. So in the case of this example, we can use a standard ADT definition of binary trees, like the one I show on this slide. And we can define a representation predicate that basically says that a null pointer is related to a leaf, and a pointer P is related to this mathematical tree on the right if P points in memory to a structure, PL, APR, and the pointer PL is related to TL and PR to TR. So this is pretty standard in separation logic. And now we can use this nicer mathematical models of binary trees to write our specification. What we want to do is we want to write an invariant-based specification, which goes something along these lines. We want to say that we want to parameterize our specification over some predicate R. And if R holds on the initial traversal state and R is preserved along the traversal, then we can guarantee that R will hold on the final state after the traversal. And recall that the problem with previous work was that they represent this traversal state using sequences, and this was limiting. So the question is how to define this traversal state to avoid this limitation. And to answer this question, let's revisit the client that I've shown earlier. So recall this client instantiates the traversal with an increment operation. So a reasonable postcondition that we might want to give to this client is that all the nodes in the tree have been incremented. And to prove this postcondition, we will need to instantiate the traversal invariant with an assertion that says that the nodes that have been traversed in the current traversal state have been incremented, and the nodes that remain to be traversed are unchanged. And from this invariant, we identify at least 3 aspects that the traversal state needs to capture. First, we need to be able to tell what are the old values of the 3 nodes, and we need to be able to tell which nodes have been traversed and which nodes remain to be traversed. And a 4th aspect that's not obvious in this example is the tree structure. Because like I said, in computer systems, many traversals allow the operation to depend on the tree structure or even change the tree structure. And so the client might want to instantiate the invariant with a predicate that reasons about how this tree structure changes along the traversal. So to meet the above requirements, we define the traversal state in terms of the zipper data structure. A zipper is composed of a tree, which in our case represents the tree that is currently under focus in the traversal, and a path to represent everything else. So recall that the invariant that I've just shown needs to talk about the nodes that have been traversed and the nodes that remain to be traversed. And from this zipper-based representation, we know, for example, that A prime has been traversed because the focus is currently on TL, and this is a pre-order traversal. We also know that TR has not been traversed because this is a pre-order traversal. However, there is no way to tell whether TL itself, which is under focus, has been traversed or not. So we annotate our traversal state with a flag to distinguish between the states where the focus subtree has been traversed from the states where it hasn't been traversed. And from now on, whenever I have a traversal state on my slides, the nodes and subtrees that are shaded in green are the ones that have been traversed in the current state. And lastly, we wanted to be able to talk about the old values of the tree nodes. So we need the traversal state to somehow have the old tree. But since we choose to represent the current tree using zippers, we also choose to represent the old tree using a zipper to avoid having to zoom out from this zipper focus when comparing the old values with the current values. So the traversal state has an additional shadow zipper to represent the original tree. So if we put everything together, we have a specification that says that if the input tree pointer P is related to some mathematical tree, and the invariant R holds on the initial state where nothing in the tree has been traversed, and R is preserved along that traversal, then the traversal guarantees that in the end the pointer P is related to some mathematical tree where the invariant holds on the state where everything in the tree has been traversed. So the question that remains to be answered is how to specify that the invariant R is preserved along that traversal. Okay, so to understand how to formalize this idea of traversal progression, let's first see how the traversal state evolves in our running example. So in the non-leaf case, we start with this traversal state. And before I show how the traversal state evolves, I'd like to notice that these are all ghost steps. So there is nothing happening in the actual program that is running that's related to traversal states. These are all just happening in the ghost state. So once we apply the operation f to the root of the tree, the traversal state should move the focus to the left subtree to reflect that the root has been traversed. And then after the recursive call on TL, the flag in the traversal state should change to reflect that TL has been traversed. And then the focus moves to the right subtree, and after the recursive call, the state evolves to reflect that TR has been traversed. And in the end, the focus moves to the root of the tree again to reflect that everything in the entire tree has been traversed. So these are all the steps that the traversal state makes along that traversal. And for steps 2 and 4, which are the recursive calls, we actually get for free that the invariant is preserved across these steps, because for recursive calls, we get to assume that the specification holds. And the postcondition in the specification already gives us that the invariant hold on the state where the subtree has been traversed. So we don't need to add anything in our specification to guarantee that the invariant is preserved across these steps. But for steps 1, 3, and 5, we need to somehow specify that the invariant is preserved across these steps. And the key insight here is that the traversal state progresses in one of two ways. Either it's at a point where the function f is about to be applied to a node, and this is what we call action points, and these kinds of steps we call action steps, or it's just moving the focus in the traversal state to some other subtree. So without getting into too much details, we define these three primitives: action points, action steps, and silent steps. And we specify that the invariant is preserved across the traversal by saying that R is preserved by silent steps, which boils down to specifying that if the invariant holds on some state S, and S is not a state where the action F or the closure F is about to be applied, then R should hold on the state after making a single silent step on the traversal state S. And we specify that R is preserved by action steps by requiring that the action or the closure F satisfies the following specification. If R holds on some traversal state S, and this traversal state is a state where the operation is about to be applied on node V, then after applying F on the node V, we get that the invariant holds on the state where we take a single action step, replacing the old value V with the new value that F computes, V prime. And now we can put everything together to get a specification for our tree traversal. So the specification says that if the input tree P is related to some mathematical tree T, and if the invariant R holds on the initial state where nothing in T has been traversed, and R is preserved by both silent steps and action steps, then the traversal guarantees that at the end, P will be related to some new tree T prime where the invariant holds on the state where everything in T prime has been traversed. Now the steps that remains to be done is to pass everything into our favorite program verifier to get a proof that the implementation satisfies the specification. And like I said, the automation might get stuck, and in the paper we identify some heuristics for how to write hints that will help the automation go through. Now, if we have a client that we want to verify against this traversal, we'll need to instantiate the invariant, the traversal invariant, with a predicate, and then show that this invariant implies the postcondition of the client. To evaluate this recipe, we've applied the recipe inside the Refine C program verifier. And we've managed to verify a number of different traversal implementations. So we've tried verifying different orders of traversals. We've tried verifying a traversal over array-based binary trees. We've also verified a traversal over variadic array trees. And we had a traversal with an early termination. And most importantly, we managed to verify a traversal which accepts operation that take an entire subtree as input and potentially change the structure of the input subtree. And we've also verified clients for all of these different traversal implementations. The nice thing about the recipe is that it also allows reusing its steps. So once we've used the recipe to verify a traversal over a pointer-based implementation of binary trees, we tried using the recipe to verify an array-based binary tree representation, and we only needed to redo step 1 because the actual data structure implementation changed, so we needed to change the representation predicate, but all of the other steps we were able to reuse from our pointer-based implementation. In fact, we divide our recipe steps into steps that are dependent on the logical model of the tree, steps that are dependent on the concrete implementation of the tree, and steps that are dependent on the traversal implementation, and then there is client steps. And if we make a change to that traversal implementation, for example, going from a pre-order to a post-order implementation, we only need to redo the steps that depend on the traversal implementation, but we don't need to touch the steps that depend on the logical model of the tree or the tree implementation. So to recap, I've presented a new recipe for specifying and verifying stateful higher order tree traversals. It's based on the zipper data structure. The recipe is general, modular, and automatable. And I have here a link to our GitLab repository where we have the recipe integrated in the Refine C verifier, and we have verified a number of different case studies. Thanks for listening.
So we have a few minutes for questions.
So one question I was wondering since the start of your talk is, what's happening if the tree is actually just a list? Do you recover the usual reasoning principles you have in iterators, or?
If the tree is just a list?
Yes, yes. I mean, a list is just a tree with RT1.
Then it will, the specification will boil down to the sequence-based specification that has been done in prior work, because the zipper over a list is just two lists.
Thanks for the talk. If I want to traverse two trees at the same time, say for comparing them, for example, can I apply the same recipe? Have you tried? Does it work?
I haven't tried two trees at the same time. If you want your invariant to relate both trees, then I don't see why it wouldn't work. You'll just need to know how to progress both traversal states at the same time, but it should work for like relational traversals or things like that.
Thanks for the talk. I have a question regarding the using tree traversals in other contexts. So most of the time you want to use tree traversal as part of another algorithm. How easy is it to use your specifications to actually verify a full algorithm that depends on a tree traversal?
I mean, there is, so a lot of the work that focuses on tree traversals focuses on first order traversals that for example, would rebalance the tree or has like a complicated algorithm implemented inside the traversal. In this case, if it's not a higher order depth first traversal, then the recipe is not very applicable. But if it's still higher order and depth first, then yes, the recipe can help specifying the traversal.
Can we get the next speaker ready while we take a last question?
Okay, thanks for great talk. So, do you think you can verify trees which have a pointer to the parent? So this is often the case when we want to do iteration of a tree, like iterate like last iterator for trees. When a next step can traverse to the parent, and I guess the zipper representation is great and can be applied to this situation. How do you think?
I mean, if the child has a pointer to the parent, then I think the first challenge will be in defining a representation predicate. If there is pointer aliasing, then I'm not sure we'll have to, like, the representation predicate will be more tricky to define. But if there is a representation predicate that abstracts the implementation into a tree model and we can derive a zipper-based representation from that model, then yes, that would work. Thank you.
All right, thank the speaker again. So the next talk is a distinguished paper and will be given by Yawen Guan from EPFL, also about trees, among others. So please stop.
Yeah. So hi everyone, my name is Yawen, and I'm going to talk about the work with Clement on precise reasoning about containing internal pointers with logical pinning. So time for a puzzle. How to verify this program? But no worry, I'm going to walk you through. So the first, let's assume there is a linked list storing the lowercase character ABC at pointer P, at the location P. And then we call the M function with index 1, which is going to expose the internal pointer pointing to the first element B. And then the to operator is essentially a map operation that is going to update the lowercase character into the uppercase ABC. This operation preserves the internal pointers so that R remain valid to be used to update the element B to X. This simply is very simple 3-line example. It's actually surprisingly difficult to verify. If you write in a language like Rust, the borrow checker will reject it. If we do interactive theorem proving, most of the state-of-the-art separation logic approaches will find very complicated or even impossible to verify. These include the match 1 operator, of course, and many more others. So in this talk, I'm going to tell you, I'm going to first briefly introduce separation logic in one slide. And then I'm going to tell you why containing internal pointers are difficult to reason about. And then I will give you the key idea, the key insight, which is also the takeaway of our talk. And then I'm going to give you a step-by-step explanation of our proposed solution called logical pinning. Our target is the sequential programs that is written in the pointer manipulating language like in C. So, separation logic. The core idea of the separation logic is separation. Separation is to divide resource into disjoint part. The basic construct is called a separating conjunction. For example, P points to V, star Q points to U. The left-hand side talks about a cell at location P storing value V, and the right-hand side talks about a cell at location Q storing value U. And the star ensures that these two cells are disjoint, so P and Q cannot be alias. A container, like a linked list, is represented as by the representation predicate in separation logic. The typical representation predicate of a list says that if the list is empty, then P is the non-pointer. Otherwise, P points to the head element of the list. And then at P+1, at location P+1, we find the intermediate pointer Q, which recursively point to the tail of the list. We can notice that this intermediate pointer, these internal pointers, they are hidden in the representation predicate behind the essential quantifier here. and then therefore it's not showing up in the top level logical model. This is good for modularity, but it made this internal pointer difficult to reason about. The first observation we have is that exposing the address of a subplot is usually over-approximated as borrowing. So look at our concrete example. Now we can replace the diagram with the representation predicate, and the state after the nth is usually modeled as R points to B, saying that R borrowed the element B from the list to become its exclusive owner, and then leaving the rest of the list that is stored at location P. And then notice that 2-upper actually wants it's bad the full list ABC. To get that, we have to revert the borrow to return the element B back to the list. And this process, we lose information. We forget about R, which we need to use later. The second observation is that traditional sophistication are imprecise. They do not capture pointer stability. Pointer stability is a property of container operation that talk about that the operation preserved all the possible internal pointer of the container. It's widely used in low-level programming like C and C++. And in our example, we know that 2-upper actually preserved the internal pointers. And we also know that 2-upper is essentially a map operation. Well, easily we know how to specify a map, right? The typical sophistication says that if you give me a list, that I'm going to update every element of the list to the uppercase. However, this sophistication actually allows implementation that move the element around, so that R may end up pointing to some invalid memory. This is actually pretty surprising to me personally to see that this beautiful, elegant, simple map sophistication that we have been using for years is actually imprecise. So, based on these two observations, we propose logical pinning, which is the lightweight borrowing model and proof discipline for precise reasoning about containing internal pointers. We have two key ideas, and I'm going to talk about them one by one. The first key idea is that in the container's logical model, we are going to annotate each borrowable subpart with its fine-grained borrowing state. So previously, we have this list ABC at location P, and then we are going to refine the predicate list to list prime to allow us to annotate the element with this borrow state owned. Everything is owned at the beginning. And for the borrow state, now we can say that the first element is borrowed at location R. We have this bracket because we actually check a list of exposed internal pointer to that specific element, so it's a singleton list. We can see that in this kind of borrowing, in this kind of modeling, we go directly from the own state to the borrow state, which does two things at the same time. It not only expose the address R, but also do the ownership transfer. However, the ownership transfer is not needed. It's an over-approximation here because we actually don't really need the ownership transfer here as we have already seen before. So instead, we have the fine-grained borrowing states. So we introduce the intermediate state called offered, saying that B is offered at location R. So we still have the ownership of B, but we offer it at location R for other people to borrow in the future. So we decouple the address exposure and the ownership transfer. And it allows us to actually go back and forth purely logically between the offer state and the borrow state. And then if we don't want the exposed location R anymore, we can forget about it by going back to the own state. So now instead of like borrowed, we use offered here to just expose the address R. And then we can do the ownership transfer later when we actually need it. So the second key idea is that we can capture pointer stability with a precise classification of writes. So we have already seen two different kinds of writes here. The first kind, we call them in-place writes that update the content exactly at their original location. The second kind, we call them full writes, which may relocate or deallocate elements. The first kind, they don't invalidate existing pointers, so they preserve pointer stability, while the second kind does not have this guarantee. So we know that 2-upper is one example of the in-place write. So we can capture the pointer stability by saying that it's going to preserve all the borrowing state and all the exposed internal pointers of this input state. So we have this offer state at the end here. And then we do the ownership transfer later when we need it. So to combine these two key ideas together, now we can see the full proof coming out. So at the beginning, everything is owned. And then after nth, we expose B is offered at location R. 2-upper is going to preserve all these borrowing states. So it becomes capital B offered at location R. And then we do the ownership transfer here. We call it a logical borrow to detach the ownership of the element B out of the list. And then after the local reasoning, and then we can do the revert of logical borrow. We call it a logical return to put the element back. And then after all of this, if we don't need R anymore, we can do a logical forget to forget about the exposed location R. So logical pinning. In this work, we show that logical pinning allows precise sophistication of realistic APIs for leaves, for trees. And then we show that it's practical by showing that it assumes some well-known proof patterns. It simplifies some complex proofs, and it also enables reasoning about program pattern that is not allowed, not supported by the traditional sophistication. And we show logical pinning is compatible with most separation logic variant. You only need to change the way to write sophistication and representation predicate. And we formalize it. We formalize the borrowing model and all of our result in one of the separation logic framework called CFML in ROC. So next, I'm going to give you a step-by-step explanation of logical pinning. And I'm going to show you how to use it as a proof discipline in 4 steps. And I'm also going to tell you about the state of the borrowing models. So the first step is the preparation step to prepare ourselves. So start from the typical sophistication of a linked list. We notice that we have this indirection introduced by the intermediate pointer. We are going to abstract it away by denoting it as the little star applied to the list predicate. We call it indirect predicate transformer. And then so that this predicate says that at location P+1, we find the list L indirectly stored. So it's just syntactic sugar. You can understand as notation. So then we rewrite it. And then we find, and then we notice the pointer arithmetic P and P+1. We can also do abstract it away by introducing a record, which has 2 fields, element and X. And the first field store X, and X is described by the predicate cell, which essentially points to predicate, but simply says that X is going to be stored in a cell. And then the next field L, the next field next, it's described by this indirectly stored list. So we write it again. OK, so now we finish our preparation. Time to do the rework. So first, we need to identify what exactly is the borrowable subpart. In our example, it's this list element, the characters. And their logical model is this little chart, the character here. And their representation predicate is this cell, the points to predicate. So now we are going to refine our representation predicate from list to list prime to check the borrowing states. So for the logical model, we convert it to, we change it to borrowable characters, where the borrowable type is going to encode all of these borrowing state. We have 4 states in total. And then the others are the same, except for the representation predicate, we have the little b. It's like the little star. It's also a predicate transformer. So B cell is going to describe a borrowable cell instead of just a normal cell. We actually use the same notation for the logical model and the representation predicate. So we only need to write the little b char and little b cell. So you can see the only difference between list and list prime is just we apply the little b on both the logical model and the representation predicate of the borrowable subpart. And we say that we have 4 different borrowing states. They are owned, offered, borrowed, and missing. They are actually modeled by a pair a pair of option of value and a list of alias, a list of exposed pointers to that specific object. When the option is sum, we say that when the value is available, we have an aggregated state called available. On the other hand, if the option is none, we say that the value is unavailable. If we know that the list, the exposed internal pointer list, has at least one exposed address, we say that this object is got pinned to that specific address, so you cannot move it in the memory without changing its borrowing state. Otherwise, we say that it's logically floating in the memory. You can freely move it, and then logically it's okay. There are a lot of transactions among this borrowing state, and we already know some of them. For example, from own to borrow, we know it's pointer exposure. And then between offered and borrow, we know that it's ownership transfer, that you can go down, you can go to borrow state by a logical borrow, and you can go back by a logical return, and you can both back and forth. And then we know that from offered to owned, we are going to forget about the exposed pointer. We do the logical forget here. And the second step, now we know how to refine the containers like representation predicate to capture these borrowing states. Now we are going to enrich the API sophistication to reflect the validity of these exposed internal pointers. So the first is the AMP function. We know that in our example, it converts the owned B to the offered B. So what does this sophistication look like? Well, we need to say that if n is valid, it's less than the length of the list. And then if we have a list L described by list prime, and you can notice here, list prime actually allow all kinds of borrowing state. So this element, the interested element, can be owned, can be offered, can even be borrowed. We don't care, because env is actually a function that only cares about the underlying shape, the underlying structure. It doesn't care where the element is here or not. And then in the post condition, we are going to update the env element depending on the original state of the env element. If it's originally pinned, if it's originally floating, then we are going to pin it down to the location R. So own will become offered and missing will become borrowed. And otherwise, if it's already pinned, then we are just going to remember one more alias. So in the entire pattern matching, we can encapsulate it in the function called pin ln at location R. The second function is the tool-up function, the map operation. So let's start from the typical map sophistication that we have already seen before. So we need to add a precondition saying that for every character in the list, it has to be either in the own state or the offer state, because we now need the ownership of the element. And then in the post condition, we are going to update the character. Depending on its state, if it's own, then you stay as own, we just update the content. The same for offer, we are just going to update the content. And that's all the possible state in this case. And we can write it as a map into the borrowed state. We don't need to write the pattern matching all the time, of course. So now with the refined logical model, with the refined representation predicate, with the enriched API sophistication, we can just need to prove the correctness of this program, which we have already seen before. So I just presented logical pinning, which is a borrowing model and proof discipline for precise reasoning about container internal pointers. The key idea is that we have this fine-grained borrowing state that decouple pointer address exposure and ownership transfer. And we enable precise API sophistication. In the API, we can check the validity of these exposed internal pointers. And in the paper, we have much more. For example, if you're curious, can we borrow recursive substructures? Yes, we can. We can borrow the tail of the list. We can borrow subtrees. And then we also show maximally precise sophistication of a realistic API, list API. By maximally precise, I mean that the API, they account for all the possible internal pointers. And they also require minimal ownership in the precondition. And then we also show the comparison to match one to Ross borrows. And then we also show how logical opinions assume well-known proof patterns. And also we show you how to do systematic transformation from a normal container to a container with borrowable substructure. And finally, there's some nice composition between the predicate transformer, the little b and little star here, to allow you to express some subtle case like, I want to borrow the intermediate pointer and transitively borrow the tail, or I want to just borrow the tail itself, or I want to be able to borrow both, but separately. Like you can express those subtle cases. And you can scan this QR code here to see our repo, to see our formalism. And thanks. I'm looking forward to your question.
I wanted to ask, why do you have a list after offered and borrowed? What's the reason for having multiple aliases if presumably they're all pointing to the same location?
Yeah, I actually have a backup slide for this. Sorry, too far. Sorry. Here. Wait. Okay. The problem is, so we check a list of aliases because like the list actually encapsulate all the equality, so that we don't need to check them separately. So for example, if it's already offered, of course, we can say that just return the pointer that we already know. So we can check that separately as another pure condition by the side. Or we can just say that it got added into the alias list. So that our specification is actually very simple. We just say that we pin it down, again, on a new location. It doesn't matter if it's already got pinned down in one location or not.
Yes, but when you move from offered to borrowed, don't you have the constraint that you can be borrowed by only one pointer?
When I move from borrow to offer to borrow, yeah, I will need to from offer to borrow. I will need to forget about all the exposed internal pointer, but it doesn't matter like how many of them because they are all equal to each other.
Okay, so in a language like C++, you have iterators, so they can be invalidated, which is kind of similar to what you have shown, but more importantly, they can be moved around along a list, next and previous cell, and it is not clear if this is a use case you can support with your model.
So if I understand correctly, you are saying that you have a value that you can move in the memory? Or I didn't quite get the question, sorry.
Yes, say if you have a pointer to a cell of a list, of the pre-linked list, you can move the pointer to the next element or the previous element.
Mm-hmm.
And is it something that you support with your model?
Yes, you can. In the API, we support like the API support that go to the next element, previous, or even the next tail, the nth element, something like that.
Thank you for the talk. It was very nice. My question would be, if you have like borrowed the pinned down and borrowed a pointer, can you insert it into another logical list as well, and then pin two elements of the two lists together, or is that not yet possible?
So currently, if two lists want to share a common element, is that what you mean, right?
Yes, but if you have it pinned down, you kind of know that you can keep it and you can like switch borrow it around.
Yeah, exactly. That's one of the use case here. If we have multiple containers that share one element, usually temporarily, we will view it as one view it as offered at that location, or the other view it as borrowed at that location.
All right, so you can actually have
yes,
two logical.
and that's yes, exactly, and that's one of the. For example, when we do tree rotation, that's what happened because in the middle of tree rotation, you have two nodes sharing in the same subtree. Yeah.
So let's thank the speaker again. And so our next talk will be given by a local, Virgile Mariano from INS Rennes, about probabilistic programs.
I have a problem. I've just implemented skip lists as part of some big project I'm working on, but I'm not too confident that I did it just right. So I want some way to be sure. Thus, I go to my good friend Felix, and I ask him if he has some way to verify that my program does what it is supposed to do. He tells me then that I should probably look into the iris separation logic, because it's nice, it's high order, it's highly modular, and I should be able to tailor it exactly to my needs. But I chose to go the random way with my implementation, as it's quicker to write. And I have no idea how to make iris comply with randomness. But he does. He tells me I should look into error credits and the logic that implements them. So let's take a step back and generalize the problem. A lot of algorithms make use of randomness as a way to gain speed at the cost of having correct result up to some probability. And to reason about those algorithms, you need to have specialized logics, such as errors. But such logics only provide one primitive kind of distribution, usually. And different algorithms can sample from different distributions, sometimes multiple at the same time. And thus, you have to implement them before being able to reason about them. And this is a problem because you still want to be able to use them as modularly as the primitive your logic provides can be used. So let's start. Our choice will be errors. So let's start with a primer with what errors is. It is a higher order separation logic that allows you to prove properties about sequential probabilistic programs. The way errors achieve this is by introducing a new resource called error credits, where it will be written using this little lightning bolt, and where owning epsilon error credits is akin to having an allowance to fail to prove the specification under scrutiny with probability epsilon. Errors also comes with two kinds of Hoare triples, total and partial ones, depending on whether you consider a diverging program to satisfy no specifications at all or to satisfy all of them. And the key thing that makes Eric tick is the fact that whenever your program is sampling from a random distribution, you can choose how you distribute credits depending on the outcome, and you can scale them up or down under some conditions. Let's have a deeper look at how this works. Here are some rules of errors. The first one simply states that you can combine and split credits however you see fit. The second is the one that allows you to make real use of credits. That is, if you have one full credit, then you have the authorization to fail to prove your spec with probability 1. So you can prove bottom and you can stop reasoning at this point. And the last rule is the one that lets you distribute credits. This states that if you start with some amount epsilon of credits and you're sampling from the uniform distribution on the integers from 0 to big N, then you can choose how many credits you want in the end, as long as the expected value of the credits after sampling is at most what you already had. Intuitively, this boils down to saying that if you know that you will fail to prove your spec with probability epsilon, then you can explain why and where this failure can come from. Eris also has two nice adequacy theorems that ensure that what you prove with it has some meaning. The first is for partial triples, stating that if you start with some credits, some epsilon error credits, and prove that your program should terminate to a value v respecting some spec phi, then the probability of the program terminating to a value that does not respect phi is at most epsilon. And for total triples, in the same situation, then the probability of the program terminating to a value that does satisfy the spec is at least 1 minus epsilon. Let's look at a small example to be more familiar with how this works. Here I have a simple program that samples 2 random bits and then checks whether the sum is 2, that is, that both are 1. And if you look at it hard enough, you can convince yourself that with probability 1/4, it should return true. In Eris, then, you could state the following spec. That is, if I allow myself to fail to show my spec with probability 3/4, I can then guarantee that the program will return true. We can prove it in the following way. We start with 3/4 credits. Then we sample a random value into x. So 2 possible cases, x is 0 or x is 1. In the first case, I will choose to now have 1 full credit and stop reasoning on this branch. In the case x is equal to 1, I will have 1/2 credit remaining. And if you look at the expected value of the credits after sampling, it's indeed 3/4 the amount we had before. On the second branch, we haven't finished reasoning. So we need to sample the second bit into y. Once again, if y is 0, I want 1 full credit and
to fail to prove my spec. And if y is 1, I have no credit remaining, but that's not a problem because indeed, in this case, x plus y will be 2, and I will return true, allowing me to prove the spec at the bottom. But now, if you were to take this example and sample from another distribution, first you would have to implement it, and you wouldn't have such nice rule to reason about it. And this is exactly what we set out to do. We set out to define exactly the kind of rules we want for a sampler to be able to use it in exactly the same way and for them to be as nice. And after defining an interface, we have also implemented it using the same methodology over and over again for a variety of distributions and proved some nice abstract results that allow you to get stronger reasoning principles on samplers that implement this interface. So let's get back to what I was saying. I want to replace my sampling by another distribution. Let's say a Bernoulli distribution. So I have to implement it. This would implement the Bernoulli distribution with parameter p over q plus 1. To implement it, what you do is you sample a value from the interval from 0 to q, and you look whether or not you landed before p or after p. And then you return 1 or 0, depending on this. And now that I have this implementation, I can plug it in. And I would be able to prove, probably able to prove with some probability that this returned true. But first, I want some rules to reason about my implementation. Can we maybe find rules similar to the one we had before? The answer is yes. We can prove this rule for credit distribution, which in a sense is the same thing. We're stating that we start with some amount epsilon of credits, we sample, and then there are only two possible outcomes. Either it is 0 and then I have some amount epsilon 1 of my choice of credit, or it is 1 and I have some other amount epsilon 2. And they are constrained by the fact that the expected value of those is epsilon, according to the expected value for a Bernoulli distribution of parameter p over q plus 1. And this is nice. Then probably this rule can be proven in most of the cases and you want it. But do we really want it, and is it enough? The answer to this is yes. There is this nice theorem you managed to prove called distribution adequacy that states that whenever you have some expression E and some distribution mu, and that you can prove a rule of the shape we've seen before, that is, starting with some credits epsilon and reducing E, we land on a value V and some new amount of credits, such that the expected value of the new amount under mu is exactly what we had before, then the expression has probability mu of V to reduce to every specific value V. So this, in a way, this rule perfectly internalizes the output distribution of an expression. And so we want it in our interface. So we can start building it. We will want some sampler, we will call it sample, and we want it to follow this exact rule. But now that we have managed to generalize one of the reasoning principles Eris gives us, we might want to look at the others that I have skipped for now, that allow for even nicer proofs. We will be looking at pre-sampling tapes. These are a device that allow you to completely decouple reasoning about credits and sampling from the actual flow of the program. The way you achieve this is by extending your operational semantics with a new kind of state we call a tape. A tape will have a label, which is a kind of abstract location, and it will represent some source of randomness for which we have already received some values. So if I have some tape at a location iota, but it is empty, and I am sampling from that exact tape, then as I have no bits already sampled, I will simply reduce, as before, randomly. But if in my state I already have some values on iota, then I will reduce deterministically with regards to the value on the tape. And I will remove this value b from it, as we want to note the next samples to be sampled if we call again. The reason this doesn't affect the adequacy theorems for Eris is that there is no way for the language or the program to add stuff onto the tape. We can only do it at the logical level. And so, if I have, in my logical context, the fact that some tape at the location iota has values on it, I can go from this to having two new possibilities for the uniform distribution on 0, 1, whether I have the same tape with the value 0 appended at the end or the value 1. And I can resume reasoning from there. Let's go through another example to understand how this can be useful. Let's see the rules first, sorry. So you have the first rule that simply states that you have a language construct that lets you, at the logical level, allocate an empty tape. Here the hooked arrow is basically a points-to predicate, but for tapes. The second rule states that, as we've seen before, if the tape has already some information on it and we are sampling, we have to return the value that the tape holds and remove it afterwards. And finally, the last rule states that we can do reasoning with credits whenever we presample values onto the tape, as we've done before when sampling from the program, but now purely logically. Now let's get to an example. I've taken here the example from before, but I've made the bit sampled into X lazy. It will only be sampled when we really need it. And so at this point, I can't really do the same reasoning I've done before, because when I reach X, I have no way to split credits by sampling, because the program is not actually sampling. But luckily, I've labeled the sampling operation with a tape that I allocated before, and I can still prove the same spec as before for my example. The way this would be done, again, is you start with 3/4 credits. Then you go through the tape allocation and you get an empty tape at some location iota. Then you make the conscious choice of sampling onto the tape, whether you append 0 or you append 1. And you can do exactly the same reasoning for credits as we've done before in this situation. So the leftmost branch can be eliminated right away. But on the rightmost branch, we still have to work again. So we can go through the regular sampling and scale credits as before, eliminate the new leftmost branch, and now remains the branch where X and Y, where Y is 1. But now we have some value on the tape. So when I will reduce X, the tape makes it so that it reduces it to 1 necessarily, and I can still conclude. And I can keep the nice flow of credit reasoning I had in my previous proof. So can we maybe generalize this idea to the Bernoulli example we had before? So the first thing we want is some way to label tapes for this example. So we will modify the implementation slightly to take a tape location as input and label the sampling operation with it. Then allocating a tape for this sampler will boil down to allocating a tape for the innermost sampling operation for the uniform distribution. So the implementation is simple and as follows. The interesting part is defining what it means to own a tape for the Bernoulli sampler. It will be done as follows. Owning a tape for my sampler at location iota with the bits from B onto it will amount to owning a tape for the uniform operation I'm doing inside of it, such that when I translate what it means to run the sampler with those values from the innermost tape, I get the values I want to hold outside of this existential. And if you work through those rules a bit, you will be able to prove reasoning principles similar to the ones from before. I will not show them for this example, and instead show directly what they are in the general case. And here is an example of a tape and what it translates to. So in our interface, what we want now is some way to allocate a tape. We want some notion of owning such a tape at the logical level. We want indeed that when we run through the allocation, we do get an empty tape at some location. And we want that if we are sampling from some location and at this location a tape holds some value, we reduce according to it. And finally, we want to be able to pre-sample onto the tape. As before, again, we want to be able to start with some credits and go to a situation where we have one more value onto the tape and credits according to what this value is, as long as its expected value is the one of the credits we had before. But now that we have this nice little interface, we might want to put it to the test. So let's go through a case study of the geometric distribution. It's interesting because for now the example I've used had a finite support and was always terminating. But here, the geometric distribution has infinite support. And as you can see from this implementation, it can have arbitrarily long runs. So it's not terminating anymore, but only almost surely terminating. But Eris has some tooling that lets us still prove some things about this kind of implementation. The main technique we will be using is called error induction. As it is a bit complicated, let's take a small aside to understand it better. The rule for error induction on error amplification or error induction is as follows. It's not the most understandable, but let's try to understand it intuitively for maybe the example of recursive function. This here states that if you want to prove something about a recursive function, and before reaching any of the recursive call, you can strictly increase your credit by a constant amount, greater than 1, then two things can happen. Either you do finitely many recursive calls, and so you terminate and you just have to prove the spec, or you do infinitely many. But as you keep increasing the amount of credits, you have to reach 1. And when you reach 1, the proof can still terminate, and you can again prove your spec. And once we know that we have this technique available, we can use it to prove the following spec for sampler. This is the same as before, an instance of our interface, where here you can see the textbook definition for the expected value of F2, and here you can see the same triples as we've seen before. In conclusion, and again, we now have to populate the remaining part of the interface, that is the tapes. So as we are sampling from a single Bernoulli distribution inside of our implementation, we only have to allocate a tape for this sampler. Then the notion of ownership of a tape, we have the same shape as before. We want to own a tape for the underlying sampling of the Bernoulli distribution in a way that it's related correctly to the sequence of values we want to own at the abstract level. This ownership, this translation predicate follows the following rules, where basically it states that for each value on your abstract notion of tape for the geometric distribution, you have a sequence of 0 of exactly this size ended by 1 on the underlying Bernoulli tape. An example would be as follows. For the Bernoulli tape, I would have 0, 0, 0, 1, so I have a 3. Then a single 0, so a single 1. Then no 0 before the 1, so it's 0. And now this shows that we can implement some harder distributions with our interface. And if you want harder distributions, we have a more complicated example inside of the paper. In conclusions, we managed to specify an interface for implementing distributions and samplers for those distributions, so we can decouple reasoning about the implementation from the clients of those implementations. We have also shown a general method for populating this interface, and we have proven abstract results on samplers implementing it. Finally, we have a variety of implementations of samplers and their corresponding instances for this interface. Remaining questions are whether or not we can scale this to continuous distributions, and if it is possible in some way to facilitate reasoning about the tape predicates by maybe having a way to derive them automatically. And another remaining question is if we could get some sort of completeness result about whether or not this is always implementable, and if any sampler that does behave operationally as the distribution describes would have to obey those rules. Thank you.
So we have time for a few questions. So I'll start with one. So at the start you said you have this distribution adequacy that says if your program follows this rule, then it implements this distribution.
Yes.
Is there a reciprocal? If I have a program that satisfies this,
so that's exactly the last question I was trying to convey. We do not know if we can always hope to have such a rule if a program does implement a distribution.
Okay, I thought it was about the pre-sampling tapes, whether it's always possible.
My bad.
How does the pre-sampling of tapes actually work? Like, I mean, here you're presenting them as sort of rules, but I guess you need some kind of behind-the-scenes infrastructure in order to enable this sort of pre-selecting from a random source.
So for the primitive uniform distribution in arrays, this is done through some erasure lemmas that tell you that if you have some behavior starting with a state with populated tapes, then starting from a state that has no tapes or only empty tapes, the program behaves the same. At least the final distribution is the same. And for every implementation, what you have to do is every time find a way to translate to a more primitive tape predicate and show that the presampling is still possible.
Can we get the next speaker ready?
So I'm a bit worried about your error induction rule, because it seems like you can only use it to prove terminating a program that uses exponential decay for termination. That is, essentially the sequence of error credits is a power of k, essentially.
Yes.
And the reason why it terminates is that the series of powers of key of 1 over the power of key is 0, right? Question is do you think it can be generalized to series which are converging but less rapidly?
So I'm not exactly sure if you could do it because this rule was already presented in the Eris paper and I didn't really work on it, only used it. I suppose that as long as you can show that you can eventually reach one full error credit, then you could show a similar rule, but I wouldn't give you a guarantee here.
Is it a question or do you want? I can answer. Okay.
So there's like different criteria for proving almost sure termination of probabilistic programs. This is kind of basic one because it's just, as you say, powers. But there are some kind of techniques based on martingales. We've also implemented some of those, but they are not part of this work.
So let's thank the speaker again. So the next talk will be about Rust and given by Arnaud Golfus from INRIA.
Okay, so I'm a PhD student working with Jacques-Henri Jourdain and Armel Guénaud, and I'm here to talk to you about how we verified undefined and persistent arrays in Rust. So in Rust, you have this interesting principle that's called the shared XOR mutable a lot of the time, and that brings us some very strong guarantees about aliasing of pointers. So here's an example of a program that has pointers. It has mutable borrowers, which are checked by the compiler. And so we are assured that these two pointers do not alias, this x and y. So if you write to x and then y, you know that the write to y did not influence the value of x. And so this assertion will always pass. In fact, if you try to make those two pointers alias by passing the same pointer twice, the compiler will complain, and it will produce a compile error. If you do want to alias, you can use row pointers and some unsafe code. And so you code basically the same function, but you replace ampersands with stars. And you add some unsafe, and then it works, except of course it will crash at runtime because the assertion no longer passes. As much as possible for our purposes, we'll try to keep doing stuff in this world because it's much easier for verification. So our verification tool is Crusoe, and it actually uses these guarantees that the shared XOR principle gives us. So, for example, here's a specification for this function f. It doesn't have a precondition because the pointers are already separated and there's nothing to assert. But it does give us a very simple postcondition for the writes we did. So, like it says here that the x pointers receive the value 1 and the y pointer receive the value 2, and that's it. with this caret operator that says this is the value we've written into the pointer. But sometimes we do want to verify structures that are more complicated than that and do use shared mutation with, for example, row pointers. An example of such a structure would be union find. In union find, you categorize elements into sets. So for example, here we have A, B, C, and D that are originally in 2 sets. And you can do some union operation on elements to merge their set together. So here we could union B and D to get this full set of the 4 elements. And you could implement that with pointers by saying that B points to A, D points to C, and the union just change the pointer, and so the sets are represented by a single element by following the pointers. So when you follow the pointer, you get the sets that they belong to. And here we can see that it explains why it's a bit hard to reason about that, because if you try to do this find call, so you find the element, the set that A and C represent, before the union, those two are different. After the union, they are in the same set, so the call will be equal. Except, of course, the union operation does not talk about A or C at all. So you have a very non-local behavior here, and it's quite difficult to reason about. So that's mainly why we want to stay in the easy world of burrows. So if you want to specify this program with pointers, you can take inspiration from the implementation without pointers, and we try to inspire ourselves with that. So without pointers, you usually use an array. You have this big array, which is a vec in Rust. And the elements are no longer pointers, but they would be indices in this array. And this is easier to reason about because you pass the whole state of the union find to each function. So each find, each union call will get this whole array, and so reasoning about it becomes much easier. To do that with pointers, instead of this array, we'll use a piece of ghost state, big ghost states that talks about all the pointers that our union find is currently managing. And we'll have some relation between the pointers in the program world and the ghost states in the ghost world to make this all work. And in order to get back our guarantees about aliasing, we need to find a way to borrow check this, to have the compiler borrow check this ghost code, this ghost object. So that's what we did. In this talk, I will present how we adapted this notion of ghost state with ownership, which was first implemented in Varus, and we implemented it in Crusoe with our specific way of doing things. In particular, we can support all the pointers, usual pointers operation. And so usually when you verify a program with pointers with Crusoe, the ideal, and in this case what we'll do, is only add ghost code. You keep all the other operation, and you add ghost code in the middle, and it should work. And in this case, we will verify how to do, we will see how to do union find with that. So, so pointers. So to get our guarantees, we cannot use pointers as is, because we just said that they introduce a lot of aliasing and mutation at the same time, so that's not possible. So you cannot dereference pointers. If you do that, the tool will just yell at you. Instead, you use this this compose type, which is composed of a ghost and then the Python. And the first part will be about erasing this object from the normal code so that it does not incur overhead. So yeah, so when you have a ghost object, you can manipulate it. From the point of view of the verification tool Crusoe, it logically contains the value that it envelops. So you can talk about it in the specification. Here in this requires, you can say that its value is a certain number, for example. And in order to get our rules of ownership back, this does have the same ownership as the type it contains. So here it's a box are non-duplicable, so this ghost object is also non-duplicable. If you try to, the compiler will raise an error. On the other hand, in the normal code, in the code compiled by the compiler, this type is compiled down to unit, and units are completely erased in Rust. so it does not incur any overhead. Then inside this ghost, I said we will put a ptr_own. So this ptr_own object should be conceptualized as a points-to of separation logic. So there's on the left there's a pointer, and on the right there's the value you want to store in there, because it will track the value in the ghost code. So you can access those two parts in any specification you want. And in order to use that in the code, in order to use pointers, you will need to combine the two. So you will need 3 operations. You will need to create pointers, to read from them, and write from them. So these are these 3 operations. Each time you allocate a pointer with this API, you get also an additional object, which we call the permission, which is a ghost of ptr_own. Each time you want to read, you need to use this asref, and each time you want to write, you need to use this asmet. And I'll focus a bit on the specification of this asmet function. So it looks like this. This is straight from the standard library of Crusoe with the same specifications. And I also wrote an example in order to see what this specification mean a bit more. It makes them a bit more easier. So at the start, when you want to get, so this function takes a pointer and it will translate it into a mutable reference by using the permission. So the first thing, the only thing it requires is that the pointer you're using is actually the right one for the permission. So this is this first equality this requires, and it corresponds to this equality in the code. And then it gives you 3 post conditions. The first one being that the pointers did not change. The pointer associated with the permission did not change. And then we can talk about the value that you get into the burrow when the value that is originally inside the burrow is indeed the one that was in the points-to. And then we can use a bit of Crusoe specifics about these caret operators to say that the last value that you write into the burrow will become the new value of the permission. And so in this example, we can get the specification that we want, which is that the value was incremented by 1. And so, okay, so now we have all these pointers. We can start to talk about union find. So these are the types and the type invariant that union find will use. So the first type is the data type, the type that will actually get compiled into the program. It's sometimes either you're at a root or you are linked to another element that you need to follow to find the root. And then you have this UF type, which will always be wrapped in Ghost. And that contains all the permissions that we defined so far. It maps them, so it contains this map. If you need to use a permission for a pointer, if you want to read a pointer, you need to index into this map, find the right permission, and then use it. To ensure that it's the right permission, you have this type invariant on this UF type. So it's defined as this logic here says that the function is usable only in specifications, and so you can use all sorts of logical operators like for all. And so it says if you contain if the pointer is contained in this permission map, then indexing it will get you a permission that has the right pointer. And then you can say some additional stuff about the value if you need to. If you would verify the actual program, you need to talk about the value as well. Now we talk about find, the find function. So the find function in program code starts like this. It's you take a pointer, you return another element as a pointer, and you of course start by reading it and trying to find if it's a root or linked to another element. The rest of the code will not talk about it, but the first is already interesting because we need to read this pointer. To do so, I said that we only will add Ghost code. So here's the proof. We just add a bunch of stuff around those pointers. We have the specification that says that the pointer is indeed managed by this big Ghost UF structure, and that the return value is correct in the sense that it's a root. But mainly I'm interested in how we get this permission, because we need to use as ref in order to read the pointer. And so we need a permission to do so. To get this permission, this asks for a ghost of permission. We only have a ghost of UF. And recall that it's a map, so we need to do some additional operation in order to get this. So one thing I did not talk about up until now is that we also need to execute some ghost code in order to retrieve this permission and use it to read the pointer. So in this case, it would simply index into the map, and the rest will follow. And these ghost blocks, do have some restriction on them in order to not influence the normal run of the program. And here's a summary of all these restrictions, basically. So what it says is, each time you enter, each time you exit, the second line says each time you exit the ghost block, you wrap the result into this ghost object. And conversely, each time we want to use a ghost object, we will have to enter a ghost block. So you can't use this object outside of the ghost block. You can, although you can do whatever you want with it inside of it. As for normal programmable value, you can read them, but you can't write or move them into the block. And of course, you can't escape. You can't have control flow escape the block to the outside, as it would change the control flow of the program. So that's all the mechanisms we need to complete the proof. So I presented to you how we implemented ghost code with ownership in Crusoe with this ghost type and the ghost macro, and how we handle pointer with this PTR own object, and we showed how to do the proof of union-find. In the paper, we also added more mechanisms, in fact, in Crusoe, which are lifted from Iris, which are a resource algebra, a combination of resource algebra and local invariant that allowed us to do a proof of persistence arrays as well. Those two proofs are in Crusoe's repository right here. Thanks.
We have time for a few questions. So I'll start. So you said that you took inspiration from Verus, right?
Yeah. By
adding ghost code like this in this way that is borrow check to Crusoe, do you have new capabilities that Verus doesn't have?
We do because Verus in the start does not exactly have the same feature set. In particular, this function is not implementable in Verus, so it takes a pointer and translates it to a mutable borrow, and it does not exist in Verus because you cannot return mutable borrows. And so, yeah, basically around mutable borrows, we have a bunch more functions that allows us just to do a bit more things. Yeah.
Thanks for the talk. Maybe this is just in my head, but I think the average Rust user is maybe a little more into the language and the PL of the language itself than for some other languages, although maybe not at the level of a full theorist. How would you explain the significance of your results to someone who uses Rust in industry or casually?
If I were to sell it in some way to a Lambda Rust user, I would say that this is the thing that brought unsafe code to Crusoe, basically. You could do some really small unsafe stuff, but the manipulation of, say, row pointers and also interior mutability is really is unlocked by this ghost code.
Maybe following up on this, so you said this brings unsafe Rust to Crusoe, right? Last year, I think at PLDI, there was a talk by Sasha. I think that was about combining Crusoe for safe Rust and Jillian for unsafe Rust, and Jillian is based on separation logic and Rust belt. So do you have a way to compare, let's say, this hybrid approach and your here this new version of Creusot?
Well, I would say the thing here is that we avoid separation logic per se. We only use the type system to encode some principles, but we do not explicitly reason with separation logic and iris and that kind of stuff. So it's more integrated, but maybe also the reasoning principles are a bit weaker. They have to be encoded into Creusot. Like this function is axiomatized in Creusot. It's not proven.
I'm not a Rust user, but I've tried to study Rust. I'm more of a C++ programmer, but I'm trying to take advantage of some aspects. I want to understand, this is my ignorance. Did you say that this ghost notation has no runtime overhead in production?
Yes.
Okay. And the second question is, does it in effect then give you another notation for doing essentially the same thing but without passing the entire aggregate and using indices?
Yeah, kind of, yes. That's the idea, is that you get a similar reasoning principle, not exactly the same because it's not an array here, it's like a map, but you get similar principles.
Then the benefit that I would see from this, if it exists, is that you could have two accesses to the same array as long as they don't overlap or the pointers are not. The point being, if that's not the case, what have you bought yourself other than another way to say the same thing? And if the answer is you've now taken something that was a big aggregate and you've turned it into a smaller piece, and now maybe in parallel, you can do another smaller piece. I would think that would be a strong advantage to what you're suggesting, if it exists, but I don't know.
I'm not sure I understand the specifics, but
the question again is, what is the semantic advantage, the actual benefit other than syntax that you're causing instead of passing the whole array and using indices?
I mean,
are you passing a subset somehow?
I mean, so in the end, in the implementation we've proven there is no array. It's only pointers in memory. It's really the pointer-based implementation. It's not array-based. So it's not the same implementation.
Which allows you to do more things.
Which could only, it does only.
That's the selling point. It allows you to do more things, not just another way.
I mean, that's the selling point for this specific implementation, if you want to have that. Yeah, yes.
Okay, again, somebody asked, well, how would you sell it?
That's in this case, well, you have to understand first that it's mainly a case study for Creusot, right? But also, there is one operation that you could do with this that you can't do with the array, is that you can merge two unified structures together. With the array, it's not really possible because once you've given away indices, you can't readjust them into the array,
if
right?
You lock an entire array, you can't share it.
Yeah,
if you lock a piece
kinda,
of it,
yeah.
Then you can, and I think I was hoping that's what you were saying.
I'm not sure it's exactly the same thing, but yeah.
In the interest of time, and because we have one last talk, let's thank the speaker again.
Thank you.
You will not be able to hear you through
Hi,
the
can you hear me?
microphone. So when there is question, someone has to like the question must be near
the mic is going to be here.
Yeah, the mic up. So or you are going to repeat the question, or just people come here
okay,
to make the question.
Yeah, okay, so I'll try to. Okay. So our next talk is online, is a proof pearl by Jumi Corcutt from Bloomberg. So let's. Jumi, can you hear us?
Yes, can you hear me?
Perfect. Maybe more volume.
Sure, I'm gonna keep speaking while you guys try. Can you hear me? Is this better?
This is.
Is it
Yeah,
better?
yeah, I think that sounds good.
Okay.
So, so Jumi, the stage is yours. I think.
Okay, thank you. Hi, everyone. I'm Jumi. I'm a researcher at Bloomberg's CTO Infrastructure and Security Research Team in New York City. Today, I'm going to present to you a proof pearl about game trees, implementing game trees as rows trees in functional languages, particularly Rock, the proof assistant, and more importantly, recursively building game trees correctly. So let's start with the very basics. What are game trees? What are they good for? Game trees are mathematical abstraction in game theory. They're used to reason about games and searching for the best move in a game. Famously, Deep Blue, a program that did game tree search for chess, won against Kasparov in the 90s. Game trees can also be used for pathfinding and constraint satisfaction. Game trees concretely depict the state space of a game. A game tree consists of states of a game organized as a tree, where each branch leads to a state after one move. So let's see an example. Consider tic-tac-toe. You want to explore the state space of tic-tac-toe. The tree has the empty board at the root, as you see. And now player one has to mark X in one of the 9 empty cells. That means there are 9 possible moves they can make, and that there should be 9 branches of this root. So after the first move, this is what the game tree looks like. Now, at each of these new boards, we know it's the second player's turn. And in their turn, player 2 will have to mark O in one of the empty cells. And given that player 2 has 8 empty moves at each of these new boards, these new boards must each have 8 branches. I don't have enough room here to show the entire tree, so here's only the leftmost branch expanded. At each of these new boards, it's player 1's turn again, and the game keeps going. So I think you get the idea. The entire tree, assuming that we stop expanding a branch after a game is won, is around 550,000 nodes. So that probably wouldn't be the basis of our time here. So I'm going to get back to programming. There are various data structures we can use to represent game trees, but the most idiomatic and common one from functional programming languages is rows trees. So for those unfamiliar, a rows tree is a tree data structure in which a node contains a list of subtrees, as opposed to only 2 subtrees like in a binary tree. So here in the slide, we see definition of rows trees in Rock. First, we have definition of lists, linked lists. We can either be nil, empty list, or cons, something that contains one element and another sublist. And after that, we have a type of trees. So in our definition, a rows tree can only be a node that has a root element and a list of subtrees. So this is the game tree for tic-tac-toe that we saw before, but now written as a rows tree. And obviously, we can write it out by hand like this, but can we write a function that builds this tree for us? So let's try. We want to make our function parametric over different types of game states. That is a type A here. Then we have the next parameter, a function that takes a state and gives us the list of states that are one move away from that. And then we have the init parameter, the initial state of the game. So I should be able to compute the entire state space from this, right? Well, let's attempt writing this function. The first solution here is to put the initial state in the nodes and then get the states after one move from the initial node by calling next, and then mapping over those next states with recursive calls. So great, we must be done. Just to make sure, let's check what Rock says. Oh no, Rock is not okay with this function definition. It says it cannot guess the decreasing argument of fix. Well, what does that mean? It means Rock is not convinced that this function terminates. Rock's termination checker often stops you when a recursive function is not obviously terminating. So what do we have to do to convince Rock? Well, I do have to interrupt this line of thinking and ask, does this even necessarily terminate? For tic-tac-toe, sure, it will. But what about other games? Not all games are finite like tic-tac-toe. So if we're trying to explore the state space of an infinite game, then the game tree will not be finite. And that's a bit of a problem for us, because we define rows trees in Rock with inductive data types. Inductive values are finite, and recursive functions in Rock must terminate. Where does that leave us? Now we have 2 problems that we need to deal with. 1, how do we write the recursive function that we wanted to write? And 2, how do we represent and compute infinite trees, especially if we want to deal with infinite games? And there's a way we can answer both of these questions, and that is co-inductive types. With inductive types and recursive functions, we could only have finite values and terminating functions. With co-inductive types and co-recursive functions, we have possibly infinite values and possibly non-terminating functions. So let's look at our failed attempts of writing unfold for inductive trees. and make it work on co-inductive trees. And yeah, if you just add code to a lot of stuff, that works just fine. And those of you who have dealt with co-inductive values and tried to reason about them before might say, but Julie, we could have had a finite tree and it would be a lot easier to write proofs about them. Do not worry. Even if we have a possibly infinite code tree, we can still convert that to a finite tree by taking a finite number of elements from the code tree. This is what the proof assistant folks call the fuel pattern. We have a program that may or may not terminate, so we add a fuel parameter and let the program run as long as there is some fuel. And now using the function to convert a code tree to a tree, we can say a tree is finite if at some point adding more fuel doesn't change the tree that you get. And using that definition, we can even say a game, as defined by its initial states and next states function, is finite if the unfolded game tree is finite. And using that, we can prove that tic-tac-toe is a finite game. We need to unroll the tree, game tree 10 times, hence they exist 10. And 10 because 1 for the empty board, and 9 because the longest game of tic-tac-toe takes 9 moves, so that's 10 times. So what are the lessons to learn from here? The first one is co-inductive types can be infinite, so they don't require termination checking. They require productivity, but that's a different story. And with no termination checker, writing unfold gets a lot easier. Lessons that we don't really have the time for today, but are in the paper, is reasoning about co-inductive values is much harder and more verbose. Our proofs about co-inductives take about twice as long as our proofs for inductives. And reuse of co-inductive proofs in Rock is annoying, but one can get around it. There are a bunch of methods that we mention in the paper, but we don't actually use them. But for some kinds of reasoning, you also need techniques like biosimulation, which we also explain in the paper. So let's get back to inductive game trees. I believe we can still rescue this function that we had before. So we had a function that we, 1, could not convince Rock that it's terminating, and 2, actually does not terminate for infinite games. So let's write a version that works for finite games. Here's an attempt. This is very similar to the version that we had before, except now we have a relation R, and our next function returns new game states that are less than the previous states according to that relation. Except that's not enough to convince Rock. We need to prove that this relation is well-founded, and then use the well-foundedness of this relation to convince Rock that this function terminates. What I mean by well-foundedness, I mean that things should not be able to keep getting smaller forever. In other words, it's impossible to have an infinite decreasing chain. So take the less than relation on natural numbers. You cannot build an infinite decreasing chain because you cannot get smaller than 0. So less than on natural numbers is well-founded. Or take the strict subset relation on sets. There is no strict subset of an empty set, so no infinite chain. And now we have a game state type A and possible game states of that type, A1, A2, and such. We don't know yet that the relation R in game states is well-founded, so we need to prove that. I won't show you how to write that spec or how to prove that. The constructor formulation is a bit different than the one that I present here. So, but I will show you how to use that proof to do general recursion. We will use it by breaking our unfold function in half into an entry point function and an auxiliary function. So here we have the entry point function that requires the relation R to be well-founded, and then uses that well-foundedness to generate an accessibility proof. We also have an auxiliary function that takes that accessibility proof and uses it to perform recursion. I'm not going to show the definition of accessibility here today, but you can think of it this way. As long as we have a value that is less than what we started with, we can use that value in a recursive call. And since there can be no infinite descending chain in this relation, then the function has to terminate. This idea is the essence of all methods to perform general recursion like this in Rock. Methods like program fixed point, equations, they all use accessibility under the hood. And thanks to this, we now have an unfold function for inductive game trees as well. But whenever we want to use them for a game, we have to define a relation on game states for that game and prove that the relation that describes the moves of this game is well-founded. So what are lessons to learn from this? General recursion on inductive types is well understood, but it can be a bit labor intensive because you have to prove the well-foundedness. Lessons that we don't really have time for today, but are in the paper, is that getting around the termination checker can require carrying around extra bits of proof, which forces us to make our verification more intrinsic. So we gotta interleave the proof and the computation a little more, just so that we can satisfy the accessibility predicate. So a question you might ask is, how do we know that we're generating the right trees? So to answer this question, we have a notion of soundness and completeness for unfolding. What I mean by soundness, I mean that if there's a game state in the unfolded tree, then there must be a sequence of moves from the initial state to that state. And what I mean by completeness, I mean that if there's a sequence of moves from the initial state to a state, then that state must be in the unfolded tree. So we prove this, both soundness and completeness for both inductive and co-inductive trees. And this is what the theorem statements for them look like in rock. In both, we say that a game tree is in the unfolded game tree if and only if there's a sequence of moves, in other words, a path from the initial state to that state. In the paper, I talk about useful tricks for proving these theorems in rock and how to avoid certain pitfalls. Also in the paper, we show example applications of unfolding game trees. The first example that we present is a tic-tac-toe game with an unbeatable AI, thanks to the game tree that we build through unfolding. Second example that we show in the paper is a very primitive SAT solver that tries to find a model for a formula by trying both true and false for every variable, so essentially brute forcing it. Once we prove that such an assignment actually decreases the number of free variables in a formula, then we can fold that tree and find a set of assignments that make the formula true, and that is all we need to have a SAT solver. In the paper, we also discuss we have a short discussion of efficiency concerns and more clever search methods over the game trees that we built. So I want to end the talk with another possible application. Since this is mostly a PL audience, imagine evaluating lambda calculus terms as a game, where your initial state is the expression you want to evaluate, and reductions are the moves in this game. So for lambda calculus, this is going to be an infinite game, because you can have infinite sequence of reductions. So you will want co-inductive game trees. But if we were talking about simple type lambda calculus, SDLC, we may have wanted to use inductive game trees because we know SDLC is strongly normalizing. However, to unfold the inductive game tree, you would have to provide a well-foundedness proof of a well-founded relation, and that is equivalent to the strong normalization proof. Well, why might you want to reason about lambda calculi with game trees? Game trees let you look at different paths of evaluation at the same time. And if your next states function contains all possible reductions, you can then reason about what reductions are possible and what are not possible at the same time. Thanks so much for listening. If anyone's interested, the repo of the rock proofs is open sourced. Check out the Bloomberg organization on GitHub. Thanks.
So I don't know if you really if you have a question, in case you don't, Jimmy, just tell me and I will repeat it.
Okay.
Thanks for the talk.
Okay.
Can you hear me?
I can barely hear, but it's a bit unclear. I may ask for repetition if I don't understand, but okay. Please go ahead.
Okay. So my question is, when you moved from inductives to co-inductives, you did two generalizations at the same time. So you made your trees possibly infinitely deep, but also possibly infinitely branching. But for all examples, yes, you only used finitely branching games, as far as I saw.
That's correct, yeah.
Could you have gone only halfway, so only made the trees co-inductive but left the lists inductive?
Yes, I could have. In fact, the first iteration of this paper did that. And then I found that it's an easier presentation if I make both co-inductive. But also, you know, if I'm claiming to support infinite game trees, I better be able to cover all kinds of infinite game trees, not just horizontally infinite or vertically infinite. But yeah, you're right that I should have had an example. Just you have limited space on a paper. So this seemed like an easier presentation.
Hi. So thank you for the great talk. When you start talking about accessibility predicates, you have to have this little distribute function over the next of init, so as to copy the proof along with each element so that you can recurse on them. How does that impact running this code? That is, when you extract, you end up mapping the identity function over every element at every level?
Believe it or not, it's optimized away by OCaml extraction.
Any other question? Then, if not, let's thank the speaker again.
Wait, sorry, is it a question I didn't hear? I didn't understand the question. Can it be repeated?
No, it was just thanking you again.
Oh, look. Oh, well, sorry. Okay, well, thank you so much for taking the time for me. I'm sorry for all the trouble earlier. Yeah, thanks.
Thanks for joining, Jimmy.